morning, everyone. Our first speaker today is Rebecca Jin she did her RU this summer at Harvard, and she will be speaking about fabrication of bilayer suspended photonic crystal.
All right. So as she said, that's the title. As an introduction, I'm Rebecca. I go to UCLA. I did my RU at Harvard, and I worked with Eric Mazur with my mentor, Hao-Ning Tang. So first, some background on photonic crystals. Photonic crystals are made of a repeating structure of materials with contrasting index of refraction. So as an example, you could have a slab of material with a lattice of air holes in it, like this one, and this would be a 2D photonic crystal slab. So the remarkable thing about photonic crystals is that you can have certain wavelengths of light that are completely forbidden from propagating within your crystal, basically in some because of destructive interference within your materials. And a range of these forbidden wavelengths is known as a band gap, which is part of the band structure of a photonic crystal and is one of the main ways that we characterize them. So ultimately what this means is that using photonic crystals, we can control light depending on its wavelength, which has many different applications, including dielectric mirrors and basically fiber optic cables as a few. So with that said, what are bilayer photonic crystals? As the name implies, a usual conventional two-dimensional photonic slab only has one single layer, like this one, but a bilayer photonic crystal has two layers, like this one, with a set interlayer distance between the two and a controlled relative twist angle if desired. So the important thing about bilayer photonic crystals is that theoretical investigations have found extreme optical properties, but importantly, there is no existing bilayer photonic crystal fabrication process, and so none of these very interesting theoretical properties have been confirmed. So to that end, what my mentor and I have been working on is basically developing the first ever bilayer photonic crystal fabrication process, the steps of which are as follows. So we basically prepare a silicon nitride layer on silicon, which supports the photonic crystal. And then into that silicon nitride layer, we create our photonic crystals, which is the lattice of air holes, like the example that I gave. We then suspend the photonic crystal to air by etching away some of the backside material. And on some of our chips, create spacers to determine that interlayer distance. And then finally, bond two chips together to create the final bilayer sample. And so I'm just going to be talking about these steps in more detail and essentially present the process as we currently have it, although it is still a work in progress. So as mentioned, the first step is to prepare the supporting silicon wafer and our photonic crystal material, which is silicon nitride in this case. So we start with a silicon quarter wafer. Now, a quick note is that when we're actually processing these in the clean room, we usually work with these quarter wafers so that we can process many chips at the same time, but all of my diagrams are basically going to be a chip view, just for some context. So going to that chip view, we start with the bare silicon. We then grow a layer of silicon oxide before we then grow the silicon nitride layer. I'll explain why the oxide's there in a minute, but we do both of these with a technique known as chemical vapor deposition, or CVD, which in short is a way to grow high-quality thin films. And this is an example picture of a wafer in the clean room at this stage of the fabrication. So the next step is to create our lattice of air holes, or our photonic crystal. And the way we do this is with electron beam lithography, the general workflow of which is as follows. So you basically coat the surface of your sample with a very even layer of an electron beam sensitive material called a resist. And then you pattern that resist by exposing it to an electron beam in some pattern that you specify. And once you develop it, the developer material basically eats away all the parts of the resist that were exposed to an electron beam, and what you have left is sort of a protective mask that you can use along with your next process in order to pattern the surface of your sample. And so in this case, with that resist layer, we use a reactive ion etch, or RIE, which basically uses a plasma to bombard the surface of your sample with ions and eat it away. And we use this to etch that lattice of air holes into our silicon nitride layer. Oh, and a quick note is that electron beam lithography is similar in logic to a other technique called photolithography. It's just that instead of an E-beam resist, you use a photoresist, and to expose it, you use UV light. And so every other pattern except for the photonic crystal that we define on our chips, we use photolithography for. So when I mention photolithography, I'm just going to be skipping those steps because they're ultimately very similar. And one more note is that when we etch the photonic crystals, this is actually where we set our twist angle if we want to make one. So this is an example wafer with the photonic crystals etched on. And how we set the twist is we just rotate the pattern, not the chip. So that photonic crystal might be oriented that way, while that one might be oriented that way. And so we want to make sure that we take one of those and sandwich them together for the final sample. Next big step is to expose the backside of our newly created photonic crystals. And so we first etch off these bottom two layers of silicon nitride and oxide with another reactive ion etch. And then we pattern a basically back window using photolithography. And that's what that sort of patterned chip or sample or wafer looks like. And then we combine that with a deep RIE to etch through the silicon. And once we're done, this is what a cross-sectional view looks like with the back of that photonic crystal exposed up until the silicon oxide. The silicon oxide is there to basically just protect the photonic crystal from being over-etched. And so once it's served that purpose, we can etch it away with hydrofluoric acid. So on half of our chips, we want to create these interlayer spacers that can be tuned for thickness and set essentially how far apart your two layers are. And so we make them out of a photoresist called SU8 and just pattern it with the usual steps of photolithography. And the final step is to then flip and bond two chips to create a bilayer. And so we first basically perform a cleaning with bubbles of O2, which essentially makes the surface of that SU8 sticky. And we then align and bond them using a transfer station, just pressing them together to create the final sample. So that was an overview and the specific steps of our process as it is so far. This is still in development, but the important takeaway is that this is the first ever actual fabrication process that we have for these bilayer photonic crystals. And very importantly also, it's generalizable to all different kinds of bilayer photonic crystal samples. So you can pattern a different kind of photonic crystal, you can adjust the interlayer distance, and you can adjust the twist angle as needed. So future steps, we're still working on optimizing this process. We're also looking to take what are known as band structure measurements on our fabricated photonic crystals. And there's also some image analysis work that I did over the summer as well, sort of on the data analysis post-measurement side. So thank you for listening. I'd just like to acknowledge my PI for supporting this work, my mentor Hao Ning for working with me. Fan is a grad student who I worked with on the image analysis stuff. And thank you to Catherine, Sarah, and Alice for running the REU program. And thank you to all of the funding for this project. So thank you.
Do you have any questions?
Could you talk more about the applications of the fabrication?
Yeah, kind of first and foremost, these devices are interesting because they're analogous to crystal structures. So the reason why we're looking at this bilayer twist is kind of mainly an analogy with twisted bilayer graphene. So this is the photonic analog where instead of electron waves, you have light waves, and your sort of periodic dielectric constant in your photonic crystal is analogous to your periodic potential in a crystal. And so because those structures have been found to have very interesting properties, in the crystal version, we're basically looking to see if there's any analogous light properties in the photonic version. And basically with the image analysis work as well, we're looking to identify what are called high Q modes, which basically just indicates a very strong light-matter interaction, and that has applications in quantum electrodynamic studies and nonlinear optics as well. So there's a few. Yes?
So what's the typical interlayer spacing, and how does that compare to the period and size of the photonic crystal structures?
Right. So the ones that we've been fabricating, we're shooting for a 300 nanometer interlayer distance, and the spacing of our photonic crystal, which is the circular, the lattice of circular air holes, the lattice constant is 1,000 nanometers. And the hole sizes, the hole diameters are 800 nanometers. So that's sort of how, in this case, the spacing, it's very, very small. It's smaller than the periodicity.
Interlayer spacing is smaller than the lattice spacing.
Yes, it is. But yeah, this is also adjustable. And these are just the specific samples that we've been trying to make.
All right, thank you, Rebecca.
Thank you.
Thank you.
Okay. All right, next up we have Areva Amidior from MANF, and he will be talking about fabricating porous ceramic-based spacers for the thermionic energy applications.
Thank you. Thanks. Okay. All right, so I'm Areva Modier, and this summer I spent my time working with the Barkerton Group at the University of Pennsylvania on fabricating a micro-scaled ceramic spacer for thermionic energy conversion applications. Now, I guess let's start with what exactly are thermionic energy converters. They're a form of clean solid-state energy production that are composed of two electrodes, one emitter electrode and a collector electrode. And heat can be input into this emitter electrode, causing electrons to jump across this vacuum gap, generating electricity that can be used to power an external load. Now, thermionic energy converters are already a sought-after form of energy production because of the high energy density and efficiency yields that they boast. But we can focus on maximizing this efficiency by minimizing the gap between both electrodes. And what we see is that my project focused on creating a spacer to actually maintain this gap, a micro-scaled spacer, but also address 4 objectives associated with energy optimization. We wanted low thermal conductance so that we could maintain this temperature difference between the emitter electrode and the collector electrode. We wanted electrical insulation so that whatever electricity we generated from this process wasn't shorted or didn't cause any problems with our load. We wanted it to be mechanically transferable so that when we created this spacer, we could actually move it to be able to be tested on or actually fit in this thermionic energy converter. And then finally, we wanted to allow for electron passage so the electrons that are actually jumping across aren't inhibited by this spacer design. So to address those concerns, we chose a specific spacer design. We chose a ceramic-based spacer because of its natural high thermal resistivity and electrical resistivity. We chose a hexagonal structure to promote resistance against thermal compression and also allow for electron passage through this porous structure that we see here. And on the hexagonal structures, you'll notice that there are protrusions on the bottom and the top to kind of separate these electrodes in the thermionic energy converter and also promote high thermal resistivity. So this was a very fabrication-based project, so I'm going to go over the fabrication steps and go more into detail about what each step entailed. So this is going to be a side view. First, we started with a silicon wafer. We created a silicon mold. Then after that, we conformally deposited ceramic onto that silicon mold. We etched our actual structure of the spacer, and then we finally released that spacer device. So starting with the silicon mold, sorry about that. I'm not sure what happened here, but starting with creating the silicon mold, what we wanted to do is etch cavities into our actual silicon wafer that we started out with. So these cavities were going to be in a hexagonal structure that started the base of what we actually wanted to create. So first we started with our silicon wafer, which was about 525 microns thick and 4 inches in diameter. Then next we used photolithography, as talked about in the previous project. And what we did here was first we uniformly deposited our photoresist, and then using the photolithography mask aligner, we exposed our pattern of where we wanted these cavities to appear. And then we developed that photoresist again, and then using reactive ion etching, we actually etched away these cavities that we wanted to appear. And finally, we used barrel ash and sonication to clean off any excess photoresist that remained. So what we had at the end of this process was we had these cavities etched into where we wanted them to be in a hexagonal structure. Again, apologies for the slide layout here. So next, after we created those cavities, what we wanted to do was we wanted to conformally deposit our ceramic onto that layer, onto that base layer of silicon. And you can think of that as sort of like paper mache being applied on your face and then creating a mask out of that. So first we started with our silicon mold, then we used atomic layer deposition to actually conformally deposit our ceramic onto that silicon mold. Then we used photolithography again to now spin coat a pattern and expose a pattern where we wanted protrusions to appear. We created those protrusions using inductively coupled plasma etching, and by the end of the step, we actually had the protrusions that we wanted to appear. So what we have here in this image, what is shown is we have a base layer of ceramic, and then we have protrusions coming out of the ceramic that coincide with our previously created cavities. So then next, what we wanted to do is we wanted to create ribs, wavy rib structures that connected those protrusions we had previously created. So we started with our existing protrusions. We used photolithography again to show a pattern of where we wanted the protrusions and the wavy ribs to exist. And we used inductively coupled plasma etching to actually etch away most of the ceramic, and all that was left at the end of this process is these protrusions being connected by the wavy ribs that we intended to create. So finally, after this step, what we have is essentially our fully fabricated spacer, but it's still connected to our silicone layer. So what we want to do is we want to first take our silicon wafer, which is 4 inches in diameter, and separate it into coins that are about 21.5 millimeters in diameter. Then we install those coins into a xenon difluoride etcher. And what happens in this step is that xenon difluoride etching attacks the silicon that binds the actual spacer device and the silicon mold. And after we do that, we're able to transfer this spacer onto a platform for observation. And that's the main takeaway from this project, is that we were not only able to fabricate this spacer, but we were actually able to transfer it and it remains structurally intact. And if you see, these are scanning electron microscopy images. You see that we generated the structure that we wanted to actually create to start out with. We see that the hexagonal structure is intact here, and if we move on to the next image, we're zooming in on the protrusions that are being connected by these wavy ribs. And it exists in the cavity, just as we intended to create. And finally, this image here shows that this specific spacer design wasn't uniformly transferred onto our platform for observation, but we still see that it remained intact. It wasn't flat on the surface, but we were still able to achieve mechanical stability with this. So like I said, the main takeaway from this is that not only were we able to fabricate a micro-scaled spacer with about a thickness of 760 nanometers, we were able to actually take it away from its fabrication process and transfer it for observation, which means we can perform tests in the future on this. So for future work, like I mentioned, we're going to perform conductance tests, see, okay, what kind of thermal and electrical conductivity does it possess? Does it actually boast any high density yields? And also, we're going to try different alter the process parameters. For example, deposit alumina hafnium as our ceramic. We deposited alumina in this case. And then finally, change the fabrication processes. Maybe it involves using different forms of etching or different forms of cleaning, all sorts of things like that. And hopefully this will make a significant contribution into improving the form of thermionic energy conversion. So I'd just like to acknowledge a few people, especially in the Bargeton group. Professor Igor Bargeton and Dr. Matthew Campbell were really instrumental into my progress, and also Tom Slenza and Leo Liu, very helpful in the course of this project. I'd like to thank the University of Pennsylvania Singh Center RAU for making this possible, and also the Singh Center staff for being super helpful. So yeah, thank you guys for listening. Appreciate it.
Do you have any questions?
I was just curious, is Penn your home institution as well?
No, Penn is not my home institution. I go to Indiana University.
All right, well, thank you.
Oh, did you have, sorry, did you have a question?
I'm sorry.
I might have missed it, but what was the ceramic that you used initially for your tests, for like the samples that you made?
So the ceramic we used was alumina.
Anyone else? Okay.
Thank you.
Right, go ahead. Should we just advance to the next one? Okay. Next up, we have Daniel Woodruff, and he will be speaking about characterizing the conductivity and gauge factor of PDOT and PSS.
Thank you very much. So yes, as you said, my name is Daniel Woodruff, and over the past couple months, I've been working with Dr. Walsh and Dr. Ratniaki to characterize the conductivity and gauge factor of PDOT. So the goal of this project was to look at PDOT, which has been used as a replacement for indium tin oxide in things such as solar panels and touch sensors because of indium tin oxide's, it's super brittle and expensive. And so PDOT has begun replacing it because it's a more flexible and cheap replacement. And so my goal was to analyze whether these same features could be used to manufacture strain gauges using PDOT. In order to do this, I had three main objectives that I had to go through. The first was to optimize the PDOT printing recipe. The second was to characterize the conductivity over varying curing times and temperatures. And the third was to determine the gauge factor after these changes had been made. So in order to do this, we had to have consistency in the fabrication process of these samples. We did this by first using a glass slide and placing a shadow mask on top of it, which would be taped down to keep it in place, and then painting a silver epoxy on top of it, which when removed, the shadow mask would cause consistent 3mm by 3mm squares that were 8mm apart, so that the PDOT could be printed over top of it and have consistent connections. The PDOT was printed here using an Optimac aerosol jet printer, which is beneficial because, as shown in the video, it is able to print on substrates that are uneven. So as you can see on the elevated surface, it prints this clean line through onto the substrate and is consistent the whole way. This works by using a nanoparticle ink, which is loaded into the container on the left here, which is then atomized and pushed up towards the nozzle where a stream of nitrogen focuses it. And both the rate that it is atomized and the stream of nitrogen can be controlled by the atomizer flow rate and the sheath flow rate, which are essential to making clean lines as shown here. On the left, you can see a line with a sheath flow rate of 20 and an atomizer flow rate of 50, which has some splatter along the sides and some wider lines, compared to the one on the right, which has an atomizer flow rate of 50 and a sheath flow rate of 30, as much tighter, more compact 100-micron lines. So, sorry about that. And so it is very important to maintain a consistent one in order to keep consistent prints, and the one on the right is the one we used for this. So the first step was using just pure PDOT without any sort of treatment to it. And these provided resistances on the scale of 10 mega ohms and conductivities of only about 0.041 over ohm centimeters, which is a very low conductivity, and we need a high conductivity for the things that we are planning to do with it, which is why we then added ethylene glycol at a 10-to-1 ratio and printed new lines with this. We cured these at 150 degrees Celsius for various times, and this resulted in resistances dropping to only about 70 ohms, giving a conductivity up to 500 1 over ohm centimeters, which is a much more conductive material. Okay, looks like we're having some problems with the next slide. So the next step of this was to cure at varying temperatures, which we did at 80 degrees Celsius, 115 degrees Celsius, and 150 degrees Celsius. So as you can see, all these graphs follow a similar trend, but there are a couple main points that we want to look at for these graphs. The first being this initial drop at the very start. When we zoom in and cut the time in between points to half a second, we can see that it's highly affected by heat. And so as soon as they're exposed to the heat of the oven, they begin to stabilize and drop the resistance from infinite down to under 2,000 ohms within only 5 minutes of being in the oven. The second point that we want to look at is right after it begins stabilizing. If you leave it in the oven for too long, it begins to overcure, and the resistance starts to increase again because of that dependence on heat. Next, we look at the drop, which happened when we took it out of the oven. For each of these samples, we took it out of the oven and it kept recording at this point. And it consistently dropped about 100 ohms at that point. We hypothesized this is because the cooling of the sample allowed the atoms within it to stabilize, creating stronger connections and decreasing the resistance. Finally, you can see at the very end that it begins increasing over time again after it is taken out. This is mostly likely due to it absorbing humidity over time. Studies have shown that humidity can be absorbed by the samples, and that it is important to put them in a vacuum or seal them off from humidity as soon as they are taken out to cause this resistance drift to stop, which we explore more in the next slide. This is a sample that was left out in the air just to absorb the humidity. As you can see, it is a strongly linear graph, but this one increased by almost 8% in only an hour, increasing at about an ohm a minute, which is a very large problem for using these, and they have to be sealed almost instantly. So now that we have characterized the conductivity, we have to determine the gauge factor. We did this using a cantilever beam setup, where you can calculate the strain applied to the sample using this equation and these constants shown here. And the gauge factor can be calculated by determining the change in resistance while you displace the end of the beam. For a sample attached here, we did this by clamping it down in place and then using a multimeter on the right to create the strain by displacing the end of the beam, which we can calculate and graph to calculate the gauge factor. But in order to make sure that this method works, we have to ensure that the strain felt on that point on the beam is the same strain felt by the sample attached to the beam. So we had to test our adhesion method using a commercial strain gauge. So using the equation on the left here, we were able to calculate a theoretical strain gauge that should be felt based on the displacement change. And on the right, we were able to calculate the strain actually felt using the known gauge factor. And so you can see the values here for theoretical strain and experimental strain at each displacement, which, although not exactly the same, are quite similar, showing that this will give an approximate gauge factor, although it won't be completely precise. Repeating this experiment on the PDOT gave us these values here, where the change in displacement on the left gave us the change in resistance, which when graphing change in resistance over resistance versus strain, gave us the graph on the right, giving a gauge factor of 0.21, which for reference, commercial strain gauges typically have a gauge factor of about 2. So in conclusion, an atomizer flow rate of 50 and a sheath flow rate of 30 gives the best consistent 100 micron lines for this recipe, and a 10-to-1 ratio of PDOT to ethylene glycol can improve the conductivity by 12,000 times. And although the curing temperature is not super important on the conductivity, the times are very important. And so optimal times are 10 to 20 hours for 80 degrees Celsius, 2 to 4 hours for 115 degrees Celsius, and 15 to 30 minutes at 150 degrees Celsius. However, it has to be allowed to cool afterwards to improve the conductivity, but also sealed off when it is removed to keep it from absorbing too much humidity. And the gauge factor is very low at only 0.2, proving that it can bend a lot without having a large change in the resistance. So in conclusion, it works really well as a transparent, flexible, and cheap conductor, but it has limited application as a strain sensor because the resistance drift causes a specific resistance to be hard to measure, and that is very important in a strain sensor to measure those small changes in resistance. So I'd like to thank a couple people who helped me with my research. Dan Ming Wei and Ola Olawo helped me a lot. And I'd like to thank NSF, NNCI, Kentucky Multiscale, and Impact RIU who supported me through funding. Thank you very much. Do you have any questions?
Any questions? Yes.
Earlier on, you showed a video of like the printing process. I was wondering what scale was that on?
Yeah. So the scale of the, I'm not going to skip all the way through, but the printer head or the line printed?
The line printed.
Okay. So to repeat her question was what scale was the line printed on? That was actually a 50 micron wide line that was printed. Yeah, so that one in the video was a little bit smaller than these ones.
I have another question about the gauge factor. Were you expecting it to like come out so linear, and like was that the goal
So to repeat her question, she asked if the gauge factor is expected to be linear, and yes, it is. If you graph the equation used for the theoretical one and the experimental one that we compared, that's a perfectly linear line. That shows the strong relationship between strain and change in resistance.
You know why the ethylene glycol reduces the resistivity?
So to repeat, his question was, why was the ethylene glycol help reduce conductivity? I didn't explore the actual changes that it made to the material, but I would theorize that it was because it improved the connections just like the cooling did. It helped make stronger bonds between it and increase the strength of the pathways that may have been weakened by the atomizing in the aerosol jet printing process. And it just helped create stronger bonds between it. This is similar with other materials. Acetone also worked in a post-treatment method where you could apply acetone afterwards to help strengthen bonds. But there are a variety of different materials that do this.
Any other questions? All right, thank you, Damon.
Thank you very much.
Okay, next up we have Nicholas Edwards from studied RTNN this summer at NC State University, understanding the origin of absorption and emission spectra of organic materials.
I'll be more presenter friendly if I took my mask off. Hello everyone. As she said, my name is Nicholas Edwards, and as we just mentioned, we're going to be understanding the origin of absorption and emission spectra of organic molecules. Oh, is it? Okay. So before we even get started, we should give a bit of background of what we're working with. So as we know, solar cells are one of the premier or most known forms of solar energy or renewable energy. And what we would like to focus on, namely, is its efficiency. And that efficiency relies on its optical and electronic properties. We will refer to that as OEPs. If you see OEP, you know that's what it means. As well as the molecule's orientation on the single molecule scale and in film, basically molecule by molecule and then like over a series of assembly. There are other parameters that impact it as well, like energy level alignment, packing, and morphology. But what we're going to be looking at is how OEPs can be tuned using chemical engineering techniques with their molecular structure. Understanding the relationship between those OEPs and the structure of the molecules themselves is actually going to be excellent for developing new materials with better properties. Here are some examples of OEPs below, including the Stokes shift, the spectra range and intensity of absorption and emission. So at this graph here, we're going to be actually talking about what all those OEPs are. So with the Stokes shift, that is going to determine how often it reabsorbs. That is, when the photons come in, how often it gets reabsorbed and recycled and used again and again and again. This helps to convey its longevity for the organic solar cell. If you're wondering, on the graph, you'll see this right here. That is what is known as a Stokes shift. And the way you know how much it overlaps is by this down here. The closer these are, or the smaller Stokes shift, the more this overlaps, the more reabsorption occurs. Next, you will have the absorption and emission intensity spectra, and that conveys how many electrons are converted into electricity and how much light actually exits the material. So as you can see here, these peaks right here, that shows how high it is in absorption, and these show how much it actually emits as well. So this is our system of study. In this case, we're going to be focusing on Lumogen red and orange. This is what they look like, and this is their chemical structure right here. Of course, you have others like violet and yellow, which weirdly looks clear and green. Let's just ignore that. And this is down here, another example of the absorption and emission spectra. So why are we using Lumogen specifically? What is important with it? We could use anything, but why Lumogen? Well, according to scientific literature, Lumogen molecules are renowned for their superb fluorescence quantum yields and their thermal and photochemical stability in organic solvents. Basically, for photofluorescence quantum yields, how much it fluoresces, like emits light. And for thermal and photochemical stabilities, it doesn't really change much or get so disfigured when heat or light is actually inserted into the solution itself. And their molecular structure as a non-fullerene small molecule acceptor, that is an NF-SMA. If you're wondering what an NF-SMA is, basically that means it doesn't look like a giant ball of carbon. That's literally it. These don't look like a giant ball of carbon, so therefore they're non-fullerene small molecule acceptors. It also is, due to its structure, it has great miscibility, that is, it's able to mesh well with other chemicals in solution, and its rigidness, as well as its electron transfer capabilities, you see has this common little bridge here between all of them. It's really helpful for electron transfer. And this is an example of one of its applications. It can also be used as a luminescent solar concentrator. You have the light going in here, and what light is going in, it bounces back and forth, as you can see right here, until it's reflected into the actual solar cell. So here are the goals. We want to study the photophysical property of two types of Rylene dyes, that is the lumogens, orange and red, to unravel the origin of each peak, at least why they're there. And this will be done using absorption emission spectroscopy, Frank-Condon analysis, and DFT quantum calculations. So to synthesize it, we made a 10 milligram of lumogen orange and red. Were dissolved in 1 milliliter of chloroform to compose a 10 milligram per milliliter solution. This was all done in CF at room temperature. It was stirred for 4 hours, and the solution was diluted to 0.01 milligrams per milliliter solution. Now, it's very important. There's going to be 3 words I want you to keep in mind this entire time. Single organic molecule. Okay? The reason why that's so important is because it explains why we even diluted the solution to the first place. If we want to build a house, we want to make sure it's built of good stuff. So if you make a brick, you want to make sure the brick isn't brittle unless you want a house falling in on you, and I don't think anyone wants that. So we want to make sure to see how it works in single molecule by molecule. The only way we can do that in solution, since we can't pluck molecules out of the ether, is we need to dilute it to this much in order to simulate that effect. Does that make sense? Okay. Oh, wait, I skipped a step, sorry. Next, we did the characterization process with the UV-Vis absorption spectra with different samples. They were recorded with the spectrophotometer, as well as the photoluminescence spectra. That was gathered through a fluorometer. This is the longest part with the simulations. This is where we actually performed or started to perform the quantum calculations through a software known as Gaussian. And we used density functional theory, that's DFT, and time-dependent DFT, methods. We made sure to try and control as many of the parameters as possible, including geometry optimization and vertical absorption, vertical emission, just all the stuff to make sure that we have as much control over what we're looking at as possible. And there are other effects considered using a polarizable continuum model. But above all else, Frank-Condon analysis is right here. It's this formula. Now, you might be wondering what in the world in this has to deal with energy. It's that epsilon. These epsilons right here. This is the vibrational energies. Oh, sorry. And this is the to travel from the ground to the excited state, among other things. So this is the actual lumogen orange and red spectra. As you can see here, there are distinct orange in spectra, not red. Sorry, we're not there yet. These are the different peaks, and this is what they are down here. And it's important to keep this picture in mind. This is what the actual structure looks like, and this is what the Frank-Condon analysis is. It's Gauss fitting. You have the different peaks here, and again, I want you to keep how distinct they are in mind. Okay? This is lumogen red. Not nearly as distinct peaks. There are actually 1, 2, 3, 4 peaks here. But you wouldn't be able to see that with the simple Frank-Condon model. And you will see this here as well. This is what the lumogen red in simulation looks like. And there's no graph here. Where's the graph?
Time.
Oh. Sorry. Wait, what do I do? Does that mean I just...
Wrap it up.
Okay. So basically, we don't have anything here because we concluded that we needed more multi-parameter Frank-Condon analysis. So in conclusion, we were able to tell that the Lumogen orange fits the Frank-Condon model, the simple one. We need to create a new Frank-Condon model to fit the Lumogen red, and future research will focus on implementing that multi-parameter Frank-Condon model to analyze Lumogen red. Is there any questions?
Thank you. Question?
Yeah, so could you elaborate a little bit more on like how you use Gaussian and DFT to, was it like to characterize the structure or like what was the purpose of it?
So the reason why we performed the DFT calculations was to help us get the right numbers to fit those peaks. That's what it was meant for. So if we're going to go, oh dear. So this is where we actually were in the Gauss view, and we performed the calculations in the solvent CF using that simulation, and we used that to help fit the peaks, not here, here. And so using this helps us to find the different energy levels of how the different parts of the spectra. There it is. So that's why we used it, yes.
Question?
Did the TDFT give you those numbers, or did you have to fit them to the spectra?
So unfortunately, we didn't have, because of time constraints and with software training, it turns out we didn't have as much time to fit them the way I wanted to. In fact, I tried to fit, you see that peak right there? That was the most irritating part, because I couldn't fit it at all, no matter what I tried. But to answer your question, we tried to get to the point where we used those numbers, but they didn't come in time due to software problems.
They also don't usually match up that well. Did you do the geometry optimization using at the TDFT level?
So let me see.
You said that you did the calculations for the energy levels that way, but did you do the geometry optimization?
Oh.
Of the geometry?
No. So it was the calculations were performed using DFT, but the geometry optimization was performed using this. Yeah, no, that was, no.
All right. Did you consider like CCFD, for example, or anything else, or comparing to, or calculating energy levels using the hyperfunctionals and comparing to TDFT? Or?
Actually, like I said, because of, again, with time constraint, we really could not get that far. I'm getting my feet wet with this right now.
No, I've been there before.
Yeah, so I want to get there, and I will get there, just not now. This is.
That's fair.
Is there any other questions?
All right. Thank you.
Oh, yeah. I don't know how to get this one. Great. Okay. Yeah, got it.
Okay, and then to conclude today's first session, we have John Mark Page, who studied at RTNN this summer at University of North Carolina, Chapel Hill, and he will be presenting on high-efficiency, flexible, perovskite solar modules.
All right, so thank you for the introduction, Ms. Leslie. I had the privilege of studying under my PI, Dr. Jinsong Huang, and then my mentor, Shaezheng Dai, at UNC Chapel Hill as part of the RTNN program this summer. So with the high-efficiency, flexible perovskite solar modules, Nick has already kind of stated this, it's a really exciting time for renewable energy, specifically solar cells, and there are really ambitious goals for getting us to 100% clean energy, renewable energy. So according to the Solar Energy Industries Association, total U.S. electrical generation has risen from 0.1% in 2010 to nearly 4% this past year. And this past year especially, solar accounted for 46% of all new electric capacity added to the grid. But we see here in the chart here the comparison between predictions for 100% electrification in 2030. We see that, and when that's compared to the yellow baseline forecast, there's a really large gap there. So it really compels us to not only understand that solar power production must drastically increase to accomplish this 100% clean energy electricity system, but also it compels us to look for unique and creative solutions to the way that we harvest the solar power. And so some of these creative solutions or applications beyond conventional solar panels include PV solar glass as well as flexible solar modules, which is what we'll we've kind of looked at in this specific project. And beyond the actual modules that we try to optimize, we could also optimize the actual material that we use to harvest the sunlight. So promising PV, emerging PV has been the halide perovskite, which is essentially a molecule that shares the structure, has a structure derived from the crystal lattice of calcium titanium oxide. And so we see here we have the ABX structure, ABXN structure with A and B being cations that we can tune, and for the purposes of this presentation, the X ion being a halide. And so we see that perovskites are desirable in part due to their tunable band gap, the way that we can interchange all of these cations, especially being even hybrid molecules, being organic or inorganic. Their strong light absorption coefficients, high electron and hole mobilities, making them ideal candidates for photovoltaic applications. And when we look at this kind of in an industrial setting, perovskite solar cells promise more efficient solar cells with faster throughput while reducing process costs and man hours compared to conventional solar cells. So for the purposes of this presentation, we looked at monolithic solar modules, which is essentially a collection of cells, solar cells on a substrate connected in series. And when we look at this specific design, we want to really pay attention to two areas. The dead area, which is the area on the module that's wasted, that doesn't produce power, and the active area, the area that helps us harvest the sunlight and gives us the power on the module. And when we look at the primary research goal, we really wanted to optimize the flexible module efficiency. We want to predict and verify the power conversion efficiency based on varying subcell widths. Because we see in general that when we go from a single cell or a small cell to a collection of cells on a module, we almost always have power loss. And we want to minimize the power loss that occurs within the modules and the connections of each individual subcell in modules. And so, like I was just saying, we see when we look at the NREL chart here, the best research cell efficiency for the perovskite single cell is just under 26%, which is pretty good in comparison. We see all of these other cells and their reports as well. But when we look at the champion perovskite module efficiency, which is a collection of these cells, we see it dropping down to 70.9%. So we really want to decrease this gap. And we see that a single cell with specific composition will have a higher power conversion efficiency than a module with that identical composition. And this is primarily due to the photovoltaic layer, whether there may be uniformity issues, defects, things of that nature, but it's also contributed when we look at this in application of a module, the resistive losses that occur within this module. And so the latter is a much easier fix to reduce those losses than the former. And so what I really wanted to look at in this project was that each individual losses that occur within the module. And so we went through and characterized and measured, but before we get to that, we looked at the dead area loss, which we've already covered, the TCO resistive loss, which we used ITO, the P2 contact resistive loss, which is essentially created by the scribing process that connects the two electrodes together, and then the bus bar resistive loss, which connects the cell or module to the rest of the circuit. And then the total efficiency loss, which is simply the sum of all these individual losses. And then we see kind of a collection of all the parameters that we had here. So first we wanted to characterize our voltage and our current density. We used a solar simulator and a digital multimeter. We kind of plotted this out. And the graph on the right, we see an example of what a JV curve looks like, and then also how they're directly connected to the PCE, which is what we're really looking at, the power conversion efficiency. And so we were able to characterize, we were able to get an average voltage maximum power point value of 0.930 volts, average current density at maximum power point value, 21.1 milliamps per centimeter squared. And then this was over a collection of cells with an average small cell PCE of 18.2%. So we see in literature that they're above 22%, but this is for, especially with flexible devices, this is a pretty good average value for us to work with. And then we see here in the graph here how we actually calculate the maximum power point value. It's just at the maximum product of current and then voltage. We also looked at the transfer length measurement. We consider ITO to be a semiconductor, very conductive semiconductor, and then that connects to our copper electrode at the P2 scribing point. So we see that there's current crowding that occurs at the semiconductor-conductor interface, which causes a transfer length. So we were able to use varying subcell widths. Keep in mind, we're trying to find the optimal subcell width, and then we use 4-point probe measurement to figure out our different resistance at these different varying subcell widths. And so we were able to plot this resistance not quite as linear as I was hoping for. There's room for improvement, definitely. And we were able to derive our transfer length where it crosses the x-axis, and we derived a transfer length of 285 micrometers. We also wanted to characterize the dead area width and the P2 scribing width. and we were able to use the profilometer. Even though some of these scribing areas were already deposited with material on top of them, we were still able to find them using the profilometer. And we were able to find an average dead air width of 244 micrometers, average P2 width of 56.8. And so finally, we were able to put all of these equations together, plot the individual losses, and then also plot the sum. And even though we didn't have as high of a PCE, average PCE as we wanted, and also had difficulty with the transfer length, we were able to plot a rough estimate, an excellent starting point, I think, for the optimal subcell width. We predicted it to be approximately around 4 millimeters for these flexible module devices. And so moving forward, we really want to investigate this transfer length measurement because flexible modules or devices are much more delicate because we have a flexible substrate and then a real rigid PV layer on top of it. So you can think of that kind of poses some problems. And so we also want to optimize the P2 scribing conditions and consistency. We want to make sure that interface between the two electrodes is as good as possible. And we also really want to add some more solar cell measurements to increase that PCE, that average PCE, and see how that affects our individual losses, because a higher JMPP and VMPP affect that CTM loss. And then we finally want to experimentally verify the solar module loss predicted model on these flexible perovskite solar modules to see what actually is the optimal subcell width for these devices and ultimately optimize the devices as much as possible. So I would like to acknowledge everyone here. These three here are actually separate PIs with the RTNM. We're at 3 different universities. I'd like to thank NC State, Duke, UNC, also our program coordinator, the rest of the list as well, and especially the National Science Foundation for their funding for making this possible. Here's some additional references, and are there any questions?
Any questions? All right, well, that concludes the first session today. Thank you all.
What? Getting who now? South. They're like a fish with the places. For research?
Yeah, it's for my mentor's research.
Okay.
You know, but also it really is the entire time that he spent not with me, he was just reading about
I've
cells.
never heard of like me.
How was your summer? And you're moving on to
Something after college. I'm just gonna be, it needs to be something. I don't know
Okay, should we get started? 3:40. You guys ready? A wild ride through nanotechnology. So I'm Catherine, I work at Harvard, and excited to see again some of my interns' presentations, but also interns from other institutions. And Hibiki Mitsuboshi is going to kick us off. He's visiting from Japan and did his work in Nebraska.
So I think the microphone is wrong.
Yeah, I think it's just for that. Just as I'll make sure the little green light's on.
Yes.
You should be good, yeah. Excellent. And I'll give you like a 1-minute warning when you're at the 7-minute mark.
Yes, sorry. My name is Hibiki Mitsuboshi. I'm from Toyota Technological Institute, Japan. I'm a graduate student. So my topic today is pyrolysis of 2-photon polymerized foam structures. Foam-like materials has wide application like catalyst, tissue engineering, thermal protection, lightweight metals, energy storage, and for example, metamaterials. Metamaterials is the artificial foam-like materials with a structure finer than the wavelength of light, which means the structure finer than a few hundred nanometers. And this kind of materials enable to observe very fine structure beyond the diffraction limit of light. However, the fabrication of this kind of materials, which means the low density, fine features, uniform and complex 3D structure is very challenging. So we chose the 2-photon polymerization method. This 2-photon polymerization, short for short TPP, is a very similar technology as a 3D printing using the laser light. Then we printed this kind of 3D foam-like materials using TPP printing. However, the TPP printing has a limit of resolution. So in our study, we polarized the structure to obtain the finer or lower density structures while maintaining the fine features or fine structures. And also we define the shrinkage rate like this. In our study, we used the liquid resin called IPQ, like this. Then cured using TPP printing. Then we printed this kind of hemisphere structure using TPP printing. We checked the chemical status using Raman spectroscopy. To compare with these two spectra, this is from this spectrum from the liquid resin in the before printing, and this spectrum from the sample after printing. To compare with these two spectra, as you can see, the intensity of CC double bond is decreased after the printing, which means that we succeeded to polymerize this monomer using TPP printing. However, the intensity of CC double bond peak does not disappear after the printing, which means this structure after the printing is a mixture of polymer and the monomer. In our study, we determined the temperature range using this TGA result. And in our study, we optimized the maximum temperature during the pyrolysis and the pyrolysis time to obtain the finer and lower density structures while maintaining the original fine features or fine structures. Okay. So I'll show you the effect of maximum temperature. At 400 degrees Celsius, the structure shrunk to 60% of original size. And also, we succeeded to maintain the fine feature after the pyrolysis. And with increasing the pyrolysis temperature, the structure shrunk more, and the buckling of microstructure occurred at 500 degrees Celsius. And from the Raman result, we couldn't observe the CC double bond peak after the pyrolysis, which means we succeeded to evaporate the monomer from the structure after the pyrolysis. And also, we observed D and G band from the sample pyrolyzed at about 500 degrees Celsius, which means the structure was carbonized by pyrolysis. And I plotted the relationship between shrinkage rate and maximum temperature. The shrinkage rate suddenly decreased around here due to the buckling. And this is the effect of pyrolysis time. With increasing the pyrolysis time, the components of each functional groups were changed, and especially for OCH3 groups were eliminated easier than CO groups. This is because the covalent bonding energy of OCH3 groups is smaller than CO groups. And finally, at 120 minutes, all the peaks from functional groups were not detected, which means we succeeded to eliminate all the functional groups from the structure after pyrolysis for 120 minutes. I'll summarize all the data. Before printing, we could observe the CC double bond peak from the monomers of original liquid resin. Then we succeeded to polymerize this monomer using TPP printing. However, this monomer will remain inside the structure. And after pyrolysis, we succeeded to evaporate all the monomers from the polymerized structure. It is because the boiling point of monomer were 100 degrees Celsius, so we found that the monomer were evaporated during the pyrolysis process. And also we found that if we increase the pyrolysis time, we can eliminate the functional groups, especially for OCH3 groups first. Then finally, we can remove all the functional groups from the structure completely at the very high temperature to pyrolyze the structure at very high temperature. As a conclusion, we succeeded in shrinking the samples while maintaining its own fine features. And we suggest to keep the maximum temperature for pyrolysis at 350 degrees Celsius to 400 degrees Celsius. And also we found that it is possible to obtain full carbon 3D form structures if we optimize the condition of pyrolysis. And also we expect to measure, in the future we expect to measure mechanical property by nanoindication and to calculate the density of samples. This is the acknowledge. This is the references. Thank you for the time.
Very nice job. Does anyone have questions? And while folks are thinking, if you can repeat the question for the audio, for the stream, after the person asks the question. Questions? Is there a point where you went too far and burnt it to crisp? Like when you, was there a time when you had the temperature too high or for too long and it destroyed everything?
Yes, actually, if we keep at 550 degrees Celsius for 15 minutes, and also we need to change this lamp rate into 5 degrees Celsius per minute. In that case, the structure couldn't survive. Everything was gone during the pyrolysis. Yeah. So that's why we determine the temperature range using the TGA result. This material, IPQ, can do everything at around 600 degrees Celsius. So yeah, it's very important.
Other questions?
I guess I'm wondering what sort of applications do you see your specific sort of carbon foam being used in?
For carbon.
Can you repeat your question for applications?
Mm-hmm. Like the foam that you make.
If we can change the material state into the carbon, we can change the conductivity of this kind of material. So it can apply for some conductive 3D material, because with using TPP printing, we can fabricate any structure whatever we want. So yeah, we can apply for anything. Yeah.
Any other questions? Very nice. Okay, up next we have Catherine. Great name, Catherine.
Thank you. I chose it well.
Yeah. And she did her work at Harvard this summer in the research group of Kit Parker, also known as the Disease Biophysics Group.
Yes, ma'am. Thank you.
Thank you.
So howdy, my name is Catherine Faltzcraft. I'm a current student at Texas A&M University, and I spent my summer with the Disease Biophysics group at Harvard University. So first, I would like to thank the Disease Biophysics group for giving me this opportunity, especially my mentor, HB. and my PI, Professor Parker. So first to start out with, what was the focus, what was the motivation of our project? And that comes down to plastic-based fibers in our world. We have a heavy reliance on unsustainable materials such as plastic that are toxic to humans and the environment. We can see by that graph right there how much plastic is in our drinking water that we don't know because it's so small. And this really comes from petroleum-derived plastics, which historically they take a long time to degrade in nature, which leads to higher pollution. And they also come with a high cost of production. We always want to lower the cost of materials. So that was kind of our focus. When looking to make biodegradable and bioactive micro and nanofibers, we looked at two very specific points. That first one was we needed the small diameter in those fibers. Small diameter results in a high surface area. This allows us to release a higher amount of materials that may be in these fibers. If they're bioactive materials, this is really one of the main focuses. The other is that low production rate. So 3D printing and electrospinning, they do not have a high production rate, so it takes longer to produce any materials using those two methods. So we looked to the method of focused rotary jet spinning, which allows for high production rates, and we can use nature-derived fibers to make it very sustainable. So we set out to answer the question, can we use focused rotary jet spinning to make biodegradable polymers that contain active ingredients within them for further applications? Okay. To start out with, what is focused rotary jet spinning? How many of you guys have spun cotton candy or have seen cotton candy being spun before? Yeah, so we essentially took that same process, and instead of making it vertical, we turned it horizontal and added a focused airstream, and we were able to spin fibers onto something called a collector. So we used an avocado for one of them. We've made structures that look like heart valves. And so this is a high throughput manufacturing technique that allows us to spin these microfibers. So for our fibers specifically, we used Poulon, which is a polysaccharide, in water. So again, there's no harmful chemicals. It's a natural polysaccharide in water. And then we added thyme oil just to mimic an antimicrobial that can affect pathogens that may be on our foods. And so we spun it at about 1 milliliter per minute. And then this is just an SEM photo of those fibers. You can see how small they are when we spin them. And so here are kind of some of our results. We can see, so I think because of just what happened, there was the thyme oil graph right here. We can see the inclusion of that thyme oil within our fibers at that 983 region in our IR spectrum, which is not seen in just normal Poulon. And then also again at 750. This is just to confirm that that active ingredient is still there after we produce these fibers. And then we look to see, does this active ingredient affect the diameter, right? Because if it affects the diameter, there goes that high surface area, there goes the whole purpose of this. And we saw that it really didn't change the diameter at all, which is really great because we have that high surface area. And then we looked at the Young's modulus just to see the tensile strength of these fibers, and we saw that as we increased the concentration of that active ingredient, the fibers, the Young's modulus increased, which was a very interesting thing to see. So in summary, we showed that the focused rotary jet spinner can effectively produce sustainable nature-derived nanofibers, and additives can be integrated without affecting any of the properties. So yeah, any questions? Yes.
During the research, did you do any investigation on the rate of the solubility? And if so, were there any trade-offs for the durability of those fibers?
So,
Can you repeat the question?
yes. So in terms of rate of the solubility, what is the rate of solubility of these fibers? It's almost as soon as they come in contact with water, they're able to be disintegrated essentially. And we actually didn't really see a change with any of the concentration of those active ingredients within the fibers. Yes. Any other questions? Yeah.
You did mention the use of thyme oil. Could
Yeah, so we used thyme oil. It's a antimicrobial, right? So it's gonna protect, let's say, food against pathogens. So it was kind of to mimic other materials that can't protect against those pathogens for food packaging. Thank you.
And next we have Julia. Who did her research at UPenn.
Okay, thank you. Good afternoon. My name is Julia Griffin. This summer, I was part of the SING RU program at the University of Pennsylvania. I worked in Dr. Karpik's lab studying the effect of sliding speed on zirconium dioxide tribal film formation. So before I begin, I would like to thank my colleagues and the funding sources that made this research possible, especially my mentor, Parker Lemaskis, and my PI, Dr. Karpik. So this is just some background on the project. In the middle is a snapshot of your car motor. It contains bearings which allow parts to move relative to each other. Proper lubrication of these parts is essential to keep your engine running. Recently, lower viscosity lubricants have been used to decrease energy consumption. However, lower viscosity lubricants often function in boundary regime where the contact between the surfaces leads to wear, as shown on the left. This can lead to engine failure. So to strike a balance between energy efficiency and anti-wear performance, we can add zirconium dioxide nanoparticles to our lubricants. And these nanoparticles can tribosinter and form tribofilms, which protect the surfaces from wear. In our project, the goal was to try to investigate the mechanism of tribofilm formation in order to use these nanoparticles in a variety of lubricants and machines, and this has the potential to make all machines that require lubricants more energy efficient. So this is a cartoon showing the mechanism of tribofilm formation, also known as tribosintering. The three stages are induction, growth, and saturation. Induction occurs before nucleation and growth. During nucleation and growth, the organic ligands, which are the black lines on the nanoparticles, are removed due to the shear stress. So the nanoparticles agglomerate and they adhere to the steel surfaces. And due to normal stress, they tribosinter and form a dense surface-bound tribofilm, which protects those surfaces from wear. And saturation occurs when the maximum height of the tribofilm is reached. So we generate tribofilms using a tribometer. It's also called a mini traction machine, starting on the left. This machine consists of a steel ball rotating on a rotating steel disc. The disc and the ball are immersed in lubricant, and due to the shear and normal stress, the tribofilm will form on the ball and the steel disc. In our experiments, we vary what's called the slide to roll ratio, shown on the right. It's the difference between the disc speed and the ball speed divided by the average rolling speed. The reason why we vary the slide to roll ratio is because various steel contacts, they experience various degrees of sliding and rolling. So for example, in a ball bearing, it's mostly rolling, and in a gear tooth, it's mostly sliding. And as the slide to roll ratio increases, our sliding distance is also increasing. And our tests use 5% and 50% slide to roll ratio. So once we form these tribofilms, we characterize the total thickness using spacer layer interference imaging, and we determine the height using stylus profilometry. If these two measurements are different, this indicates that the steel substrate experienced some wear or plastic deformation. And we can determine the height or the depth of the steel substrate by the difference between these two measurements. If the height is below 0, there was some wear or deformation of the steel. And we can use this to determine how well our nanoparticles protected those surfaces. So these are the results from the 5% slide to roll ratio experiment. The series of images at the top show the thickness and morphology of the tribofilm over time, where the different colors correspond to different thicknesses. we can see that the tribofilm nucleates sometime between 0 and 5 minutes. It grows non-monotonically between 5 and 60 minutes. It saturates at around 120 minutes. And then the graph below shows the height of the tribofilm and the height of the steel substrate over time. And the tribofilm is in the blue or dark gray color. The steel is in the lighter gray color. So we can see that the tribofilm does grow over time, and the steel substrate experiences some wear over time. However, if we look at this point, around 60 minutes is when the tribofilm saturates, and around that time is also when the steel substrate does not experience any more wear. So we conclude, or we hypothesize, that around saturation at 5% slide-to-roll ratio, the wear of the substrate is prevented. And then these are the results from the 50% slide-to-roll ratio. Again, the top series of images show the height and the morphology of the film over time. The height also experiences nucleation, non-monotonic growth, and saturation at around the same time points as before. And again, this graph shows the tribofilm height and the substrate height over time. And we do see the tribofilm is growing over time. There is some wear of the steel substrate, but the trends change at around 60 minutes, which is around saturation of the film again. And now we see that the steel substrate, the height decreases constantly. And instead of attributing this to wear, we do attribute this to plastic deformation, since the tribofilm at saturation covers pretty much all the contact between the steel surfaces. So it's not really possible for the steel to be worn down over time, but instead it's probably plastically deformed. And then this final graph shows the tribofilm thickness versus sliding distance. The reason why we plotted the thickness versus sliding distance instead of time is because, as I mentioned in the introduction, when we're changing the slide-to-roll ratio, we're actually changing the sliding distance. So this graph shows the results from continuous and incremental tests at 5% and 50% slide-to-roll ratios, where the 5% are in the bluer colors and 50% slide-to-roll ratio is in the green. The first thing we notice when we look at this graph is the nearly 0 nanometer thickness from the 50% slide-to-roll ratio incremental test, which we saw in the previous slide. And this is very different from the 5% slide-to-roll ratio incremental test, which follows the trend of the continuous tests. So at the higher slide-to-roll ratio and at the higher sliding speed, it is more affected by interruptions in the test than the lower sliding speed. Another thing that we observe is that tribofilm growth seems to depend heavily on sliding distance, because the slopes of these graphs are fairly similar, and nucleation around here and saturation around here are quite distinct for each slide-to-roll ratio. And it does also show that at 50% slide-to-roll ratio, it takes a further distance to nucleate and a further distance to saturate. So in conclusion, whether your car bearing is operating at 5% or 50% slide-to-roll ratio under these conditions or similar conditions, your bearing should be protected from extended wear over time, so that's great. We also saw that tribofilm formation is a highly dynamic process where each step depends heavily on the previous steps and the experimental conditions. And this was shown in the fact that the higher slide-to-roll ratios needed a further sliding distance to nucleate and to saturate. In the future, we hope to directly observe the microstructure of the tribofilms and the steel substrates to better understand this mechanism and to confirm that what we're seeing in the 50% slide-to-roll ratio regime is indeed plastic deformation rather than wear. And we also hope to probe the mechanism of tribofilm removal during the growth stage by using various shear stresses. Thank you for your attention, and please let me know if you have any questions.
Questions? Anna?
I guess I have two. I'm not sure if the second one is really related, but the first one, do you have any comparisons of like what the wear is like without any of the tribofilm growth, just to like compare?
I don't have graphs in this slide, but basically the machine will seize because there is so much wear, like it's no longer a spherical ball and it no longer permits movement of the ball in the disc.
Okay. And then I was also wondering, is there any sort of like temperature dependence? I'm not entirely sure what conditions you tested your films with compared to what it would be like in machines. And so I was wondering if there is some sort of difference there, and if you know these films have any sort of different sense of formation during temperatures.
Right. So these are more in-depth descriptions of the experimental conditions. We use 100 degrees Celsius, and the tribal film formation is temperature dependent. But we are mostly interested in the effect of the sliding speed or the slide-to-roll ratio, because other people have shown that as you increase the temperature, the tribal film formation is faster. That's a good question.
Thank you. Any questions for Julia?
On your last figure, I noticed that there was a lot of clustering between like the 10 to the first and 10 to the second meter. Do you know why that like those maximum peak clusterings could occur?
Right, like we see like a maximum here and another maximum there. Is that what you're saying?
Yeah.
Yeah, so it's something we're still currently investigating like the precise microstructure at each of these points. But it's definitely showing that the changes correspond to the microstructure, and there is growth and wear of the tribal film over time.
Any other questions? Nice job. Up next we have Hannah Kemper. Hannah, are you from Montana?
That's where I did my RU at, but I'm from the University of Florida.
Oh, that's a long way.
Yeah. Okay, my name is Hannah Comfort, and I did my RU this summer at Montana State University under McKenna Landis and Dr. Anya Kunsa. And this was in the Kunsa Neuroengineering Lab. And my project is called Optimizing Nanomagnetic Force Stimulation through Geometric Shaping. Thank you. So for starters, if we exert mechanical forces on developing cells, we can induce different cellular behaviors. And each of these behaviors is a different associated force range, normally in the order of piconewtons. And so on the bottom right here, this is an example of one of those cellular behaviors. This is called axonal outgrowth. And this is where we can grow an axon in the direction of an applied force. But you can do many things. And so the idea of this project is that if we can precisely and locally control this force, then we can precisely control cellular behavior. And so how do we actually generate this force? We can insert nanoparticles, magnetic nanoparticles, into a developing cell, and then we can magnetically actuate a force on these particles and thus the cell. And we do this by placing semi-permanent magnetic elements underneath the cell. And these elements are on the microscale, and since they're semi-permanent, when we don't have the presence of an external field, they are not magnetized, and they do nothing. But when we apply an actual external magnetic field, the magnetic elements are magnetized, and we see a force exerted on these nanoparticles, and thus on the cell. And so if we can control geometric parameters of our magnetic elements, then we can alter precisely force ranges. but in previous works, they've only done simple rectangles. And so the main background here, the actual physics are not super complicated. The main thing is just that we can represent one of our magnetic nanoparticles as a point dipole. And then through this, we obtain this final formula where we can predict the force on a magnetic nanoparticle as a function of the magnetic flux density gradient. And so this is important in bold because if we know the magnetic flux density, then we know our predicted force. And so my research question is, how does the size and shape of these micromagnetic elements affect our nanomagnetic force stimulation? And so I sought to extract the highest impact geometric parameters for these micromagnetic elements on our force maps. And basically, how can we alter these to then create nanomagnetic force maps for different cellular behaviors? And so these two shapes here, this is the rhombus bar, rhombus tear, these were my most complex elements. And they were selected because they've been prefabricated by the Kunze lab. And then on the bottom right here, this is that external magnetic field I chose to simulate. And so when we look at this actual external field, this is on the millimeter scale. It's set to the size of a standard Petri dish. And when we zoom in on it, since it's such a small scale now, we're on the micro scale, it can be approximated as constant. But when we add a magnetic element, we see small deformations around its perimeter. And it doesn't look like much, but when you take the log over space, you see that these effects are quite significant on a small scale. And when we use that previous equation to compute the force map, we see these actual points of high force, which are in the range of piconewtons ideally. And this is what we want to control. And so my primary quantification of these force maps was effective force area. What I did here is I basically took the force map and then extracted all points within that map that had a force above a biophysically relevant threshold. And then I formed alpha shapes to enclose this entire region and calculated that area. And then to normalize, I essentially just divided this by the magnetic element's upper face area. And then so to do this actually in simulation, what you first do is you can design your geometry in COMSOL multiphysics and then actually simulate this, the force on the nanoparticles. You get your magnetic flux density and then your force map, and then take this data and move it over to post-processing and quantify it, do some analysis, and then basically just alter another design parameter and repeat. And so to systematically analyze these different geometric parameters, I took the line tear rhombus that I mentioned and quantified the area and aspect ratio. And we first see that the line rhombus has a much smaller aspect ratio and area than our tear rhombus. And then I designed rectangles and ellipses that had constant areas and aspect ratios to each. And so that first handles investigating those two parameters. But then we see that the rhombi both have a high number of sharp vertices and a high perimeter, whereas our rectangle is a moderate number of sharp vertices in perimeter, and our ellipse is none and a very low perimeter. And then this is what these force maps start to look like when you rotate them to align with the external field. And we see that they become very non-trivial very fast. Whereas when we start to align with the field, we start to see large lobes forming of force area. And so to further quantify this, here, these are for different field strengths, rotating these elements in space to align with the field. And the main takeaway from this is that we're seeing a very sinusoidal trend, specifically with our high perimeter and high aspect ratio elements. And then furthermore, that this trend is not really present in low fields, only in medium to high fields. And then when we take a look at field strength versus force area ratio for two different shapes, this is our line and tear rhombus. It's quite interesting because both these are high area, high aspect ratio elements, but our line rhombus is showing exponential growth with field strength, whereas our tear rhombus logarithmic. And then if we look at the impacts of area and extreme points, on the left here, this is area. And we see that for small areas, we actually get a very drastic increase on our impact on force area ratio. But after a certain point for all of these force thresholds, this effect is reduced and almost levels off and becomes linear. And then if we take our line rhombus and basically just smooth out the vertices to see the impact of extreme point intensity, We see that for both of these, the impacts are still higher than for the ellipse and rectangle, but our smoothed element is much smaller than for our sharp element. And this shows that our extreme points corresponding to sharp vertices are going to yield a higher max force and force area. And then my last simulation data I have here is for a tear rhombus array rotated 0 to 360 degrees. And what's interesting here is that it's very obviously sinusoidal, but also it's very symmetric, which is unexpected because the actual element itself is not symmetric. So you'd expect some symmetry between half this rotation, but not the entire rotation, which is quite interesting. So then I did some experimental validation using 8-micron micromagnetic particles. And what we have here is a glass wafer of magnetic elements, and then suspended in fluid directly above are micromagnetic particles. And then so at t equals 0 seconds, this is the placement of the particles without an external field. And then when we apply an external field and wait 60 seconds, this is the second image, and we see the green fluorescence has moved into frame, meaning it's on the same plane as our elements, which basically means it's been attracted to them. And then taking a closer look, we see the particles have primarily settled on the vertices of our elements. And when going in simulation, these vertices correspond to our highest force points in space. And these are called trap points, and that's a level of experimental validation we have. And so in conclusion, I found that our highest impact parameters are going to be high number of sharp vertices, vertices that are oriented normal to our external field, and major axis of the element being parallel to that field. And then we can later use these findings to optimize our magnetic element shape and dimensions to create precise forces in precise regions of space. And then in the future, we first want to do more experimental validation, specifically for our more complex shapes. And then actually reverse engineer some sort of model to where, based on what cellular behavior we want, it will pick out our geometric parameters for us. And then lastly, apply this to in vitro cell growth. And this all has applications of 10 to 15 years down the line, actually designing brain implants using these sort of elements that can have cell growth. And then I would lastly like to thank my project mentors, McKenna Landis and Dr. Anya Kunsa, and the Kunsa Neuroengineering Lab.
Questions for Hannah? What was the most challenging part of this project?
Probably grasping the biological concepts, because I'm an electrical engineering major, so that was difficult for me.
Other questions?
I might have missed it in the presentation, but I was interested, do you know what are some particular applications where manipulating those fields would be useful?
Yes, so different cellular behaviors are induced with different force areas and ranges. So for example, inducing calcium influx in a brain cell is a different force range than axonal outgrowth. You can also migrate entire cells with higher force ranges. And I've seen even cancer applications by inducing apoptosis in cancer cells with higher force ranges.
Hello, my name is David, and my research is in the fabrication of silicon micropillar arrays. Silicon micropillar arrays have a wide variety of applications in fields such as microfluidics, optoelectronics, and biosensing. Our research objectives are to first optimize the photoresist UV exposure in our photolithography process. This is just to minimize the loss of critical dimensions. And then to determine how plasma etch conditions affect the final shapes of our pillars, and adjust those etch conditions to fabricate much smaller feature sizes. So we use photolithography to create the etch mask that will be used to fabricate the pillars. And so we spin the photoresist onto our silicon wafer substrate, and then for UV exposure, we use a maskless aligner rather than a photomask, and we develop the resist to create our mask for etching. So these parts that are covered by the photoresist won't be etched away, and then we use our deep reactive ion etching process, which is a form of dry plasma etching, to etch away at the substrate, leaving these pillars. And then for examination, we use scanning electron microscopy, or SEM. Our etching process here involves flowing a normally non-reactive gas and ionizing it to make it reactive towards our substrate. And then we can bias it with radio frequency power so that the ions move down vertically, so that the etching is anisotropic and directional to create the pillars. And we pump out the volatile etching byproducts. The parameters that we control in this process are which gases we're using to etch, the gas flow rate, the process pressure, and power and temperature. So to etch pillars, we use the Bosch process, which consists of 3 steps that can be cycled over and over to etch deeper. We first flow in a gas that will create a passivation layer on the silicon. And for our experiments, we specifically use C4F8, which creates a Teflon-like polymer. Then we anisotropically remove the passivation layer by applying the radio frequency bias power, so that the ions bombard the passivation layer at the floor right of the array right here, and then we can flow in our etching gases without the bias power, since the bias power will etch away at the photoresist as well. Only just flowing the plasma in is enough to etch the silicon substrate. And then this process can be cycled over and over to etch deeper and deeper into the silicon to make taller pillars. We experiment with 5x5 arrays, and these pillars have radii of 0.5 to 5, 10, and 20 microns. And the centers of these pillars are separated by 2.5, 5, and 10 radii. And we leave 10 radii on the sides of these arrays for SEM examination. So we first investigate what happens when we etch deeper and deeper using the Bosch process that I described previously, and observe what the shapes of those pillars come like, and the bias power is being ramped up from 95 to 105 watts. This is because the ions need to diffuse downwards and longer to remove the passivation layer as you etch deeper. And after investigating what happens as we etch deeper, we adjust the bias power and optimize for smaller feature sizes. So for pillars that are etched at a high bias power, a common problem is undercut, and this mostly affects pillars that are smaller and further spaced, as shown here. All these are separated by 10 radii, and these are getting too narrow that they fall over. So what we came up with is that we lower the bias power and ramp it down from 50 to 40 watts over the course of the process, so that undercut does not occur. And we also use the much thinner photoresist that's only 0.45 microns thick. It has a pretty narrow exposure range though, and that is why it fails to separate when they're close to each other. And the smallest pillars we got were 1 micron in diameter, with an edge depth of 34 to 41 microns. This shown right here with the 5 and 10 microns. They did separate when we did the UV exposure, and although these are perfect since the pillars are still quite fragile. One of the effects that we did not expect to observe was that the etching process had an extremely high selectivity into photoresist. We found that even at high bias power, we had a selectivity of 160 to 1, and at low bias power, we had a selectivity of at least 350 to 1. Yeah. This is completely unexpected, since a typical value would be more like 60 to 1. And the possible causes we determined are that we did etch this at a somewhat low process temperature of 10 degrees C. We baked the photoresist for a long time after each photo step in the photolithography process, and to cure it and harden it. And it also may be a case that a thicker polymer passivation layer is deposited on the tops of the pillars because they're closer to the source, and it takes longer for the passivation gases to diffuse to another strange effect that we observed is that the etch rate of the silicon accelerates with depth. The opposite is observed in a deep trench etch, that the silicon etch rate would decrease with depth, which would be the most intuitive result, since the etch gases need to diffuse further. But as we see right here, the depth is curving up with the number of etch cycles that we use, and this is not likely due to the parameter ramping, since the starting and end points are the same, and it should average out. While the photoresist etch rate decreases almost linearly until it runs out. And as we see, the average etch rate over the entire process is steadily increasing as we etch deeper and deeper. And the last strange effect that we observe here is that for pillars that are closely packed, specifically the ones that are separated by 2.5 radii, and they form this ring of fin-like structures on these pillars around the array, as we can see here and right here. This only affects pillars that are closely spaced, and for ones that are separated by 5 radii, none of them form. So to explain the two effects that I just shown, we propose a hypothesis that the accelerating etch rate is due to the fact that as we etch deeper and deeper into the silicon, the surface area is increasing, which increases the capacitance between the plasma and the substrate. And because the capacitance is higher, there is a lower impedance and higher ion current. And this would lead to a higher etch rate. And to explain the effect where the fin-like structures form a ring around the arrays, we do a simulation here, although it is not entirely accurate. But pillars tend to draw the ions into the centers of the array, as I drew this breadcrumb right here, anything above here would roughly, if ions above here that are at rest would roughly be drawn into the centers of the array rather than out on the sides, and that is why the fin rings may be forming. Of course, there are still definitely a lot of complexities due to the diffusion of ions and even neutral particles. And so this is something that will need more work to support or refute. So to summarize, we fabricated the high aspect ratio pillars with an aspect ratio of approximately 60 to 1 for a 4 micron diameter pillar and an aspect ratio of 40 to 1 for a 1 micron diameter pillar. The bias power should be low and ramped down rather than ramped up, as previously determined, to achieve smaller feature sizes. And we find that the selectivity to photoresist of this etching process is extremely high, at least 161 at the higher power bias power we used, and at least 351 at a lower bias power. The silicon entry can accelerate with depth, and we've also observed the formation of thin rings around the rays of closely packed pores. And we propose that this is due to the distortion of the electric field by the pillars. We are funded by the NSF, NCI, Harvard University, and the CNS. I would like to thank my PI, Bill Wilson, and my mentor, Wing Xie. And all of our fabrication is performed at the Harvard CNS. Thank you, everyone.
We might have time for one quick question if anybody has one. You can ask it, or you can ask David during the photo shoot, which is happening now. Great job, everyone. Very nice presentations, excellent research.
Hi, everyone. My name is Skylar, and I'm a software engineering student at Arizona State University. This summer, I worked at Dr. Feynman's lab at UCSD, and my project focused on computer vision-aided automatic waveguide alignment and optimization. All right, so silicon photonics is rapidly evolving into a multi-billion-dollar industry. The applications are across these various fields. As silicon photonics, as industry demand increases for optical devices, the need for research will also increase. So with this growing demand for research, the one problem with the optical waveguide devices is the precise alignment between the optical waveguide chip and the optical fiber array. So misalignment can cause coupling loss, and we would have inefficient energy. We would have inefficient amount of light going from our input to our output. And currently, manual alignment of of these devices can take several hours, and the components are delicate and highly prone to damage. And also the types of devices that can be characterized manually are limited. So this places severe constraints on research. So as mentioned before, manual alignment can take several hours. On the right side, you can see an example of manual alignment of single channel fibers. This is much more simple to align, but even this process can take like 30 minutes. But the fibers that we're dealing with are fiber arrays, so it's a bundle of these fibers. We could also outsource the alignment and packaging portion to a foundry, but this isn't. It's very expensive because they require purchasing in mass quantities, and we don't need these mass quantities in research. And typically, foundries limit the amount of devices that you can characterize. So you might end up having like one device that you could work with throughout the entire year. But we want to have like diversity in these devices. And finally, computer vision aided automatic alignment isn't a new concept, but the papers out there on it right now are focused on devices that have significantly different shapes from ours. So we could take we could use some of the ideas, but we have to adapt some of these methods to better suit our needs. So our experimental setup consists of, on the left you could see 3D printing of fingers that hold onto the optical fiber array. So the third picture shows the fingers holding onto the fiber array, and the hexapod can be seen below that. So the hexapod would hold the optical waveguide chip, and there are two things in this image that you can't see. There are two cameras, one for a side view and one for a top view. When we look at this under the microscope camera, the only thing that we would see moving throughout the entire program is our chip, and the fiber array would remain stationary. Also, I wanted to mention that one of my mentors, Carl Johnson, 3D printed the fingers and that mount that you could see over there. So the proposed solution is to first achieve rough alignment and then let a machine learning algorithm take over to search for the most optimal position. So we just need to achieve rough alignment to have some light flowing through our input to our output. We just need to be able to sense some light in our output. So to achieve rough alignment, we need to interpret the side view and the top view a little differently. So in the top view, we would have etchings. We would have alignment marks that would be etched onto our chip, represented by those white lines. And the goal is to find that circle, the position of that green circle, and then to find the position of the red circles, which represent the corners of the fiber array, and then from there direct our hexapod with this motion. And in our side view, we have we're trying to search for the lines representing the corners, representing the edges of our chip and our fiber array. And the initial state would be our Y1 and Y2 lines being parallel, separated by some distance, and our X1 and X2 lines being parallel, separated by some distance. So we tried using the papers methodology, but the execution time was good on it. It was a little faster than the method that we'd end up developing. but we were losing a lot of details that we needed from the image through this process. So I developed the methodology laid out below. I found that the most important distinction between these two is the steps in which the binarization and edge detection occur. So in the paper, they used image binarization and then edge detection. But in our case, we did edge detection and then binarization because binarization was removing a lot of details that we needed. So these are the results. So first, we need to grayscale our image to just have less color to reduce details. And next, we apply a Gaussian blur. So this is a noise reduction step. You can't really see the effects of the Gaussian blur too much because we only used a 5x5 matrix across this image. But it removes a significant amount of noise because it's kind of smoothing out the pixel values throughout the image. And then we run our edge detection algorithm. So we're essentially measuring the rate of change of pixel intensity throughout our image. So edges would have high rates of change. So we would end up with defined edges and a darkened background. And next, we apply our binarization method. The binarization method is called Atsu's binarization thresholding. And typically with binarization, you have like a static threshold number, and anything below that number would be darkened, and anything above that would be we would make the value 255 or white. So we're just making our image black and white, and this is necessary for the line detection step. So before we get to the line detection, we just do one more method to remove some extra noise from our image, which is called morphological opening. And then we run our line detection algorithm, which we use Howe line transformation. And from here, we have all the endpoints of each of these lines throughout our image. And once we get like the etchings on our chip, we would be able to extract measurements from this image. Also, just to mention, I didn't go too much into the mathematical details behind these for the sake of time, but if you wanted to look into it, you could look at it on the OpenCV Python documentation online. So future directions, we need to etch the chips with the alignment marks and then program our hexapod to move using the measurements from the line detected images. And then our hexapod actually comes with a optimization algorithm, and they call it like their fast alignment feature. So we're gonna test that, and we also might try to write our own machine learning algorithm and just compare what the fastest method is. And once we have that, we would have a full system. So from there, we would like to allow our algorithm to adjust for different array designs and adjust our algorithm and our experimental setup to handle multiple arrays at the same time. And we'd also like to continue collecting data on alignment error so that we could also optimize the input grading footprint that's on the chip. And sorry.
That's all right. You want to reference this?
Yeah. Yeah. Thank you. Does anyone have any questions? Thank you.
We have time for one question.
Oh. Yep.
Question?
So yeah, the question was essentially why not use convolutional neural networks? It would take time to develop that and to train it. This method was much faster to come up with. And it would also probably take time to get to a point where we're getting like good edge detection results. So it's mostly like a time constraint thing. All right, thank you.
We have Haley up next.
Hello everyone, my name is Haley Thompson. I'm a senior bioengineering student at North Carolina A&T. This summer I was part of the Singh Center for Nanotechnology REU program, and my research was done under Ricardo Gottardi's research lab at the Children's Hospital of Philadelphia, where I studied cartilage formation, also known as chondrogenesis. Cartilage tissue has poor intrinsic properties to allow itself to repair and regenerate itself. Because of this, it can be a problem for cartilage-related diseases such as osteoarthritis. Osteoarthritis is a degenerative disease of the protective cartilage found at the end of your bones. When this cartilage wears over time, the friction between the joint increases, causing chronic pain. There's treatment that is currently available to manage the pain, but there is ultimately no cure. And because of this leads to the aim of my project, which is determining how much does the size of the microenvironment of stem cells lead to chondrocyte formation, where chondrocytes are the cell types that make up cartilage tissue. And in knowing what induces chondrogenesis, it can be an advancement in the production of cartilage tissue that can be used in vivo for cartilage repair therapy and for tissue regeneration for osteoarthritis. Some might ask, why not just isolate the chondrocyte cells from the remaining cartilage and culture them in vitro to cartilage? But studies have shown that when you take those cells from in vivo and culture them in vitro, the environment is a shock to the cells and causes them to de-differentiate. Because of this, we chose human mesenchymal stem cells. We chose them for a number of reasons, one being that they have a high cell proliferation rate, they're able to renew themselves, they can be derived from multiple sources such as your bone marrow, your fat tissue, synovial fluid, your umbilical cord, and they also have the unique ability to differentiate into different cell types that can then further produce different types of tissue. As you can see, the osteocytes go to bone formation, the adipocytes go to fat tissue, and the chondrocytes go to cartilage, where we want to focus on. This project was conducted in two main parts. One was the fabrication of the 3D printed nano scaffolds, where we designed them using a computer aid design software called SolidWorks. We optimized these scaffolds and then developed them. The next steps will be the cell culture work, where we take the human mesenchymal stem cells, we lift them, seed them onto the scaffolds, and then we analyze them for cell viability and cell morphology. To begin, these are the 2D and 3D images of the scaffold designs off of SolidWorks. Both were printed off with a thickness of 100 microns, and on the left is a 70 micron, and on the right is a 200 microns. These designs were then imported to Describe, where we could optimize the printing settings, where I increased the laser power and decreased the laser speed of the 25x objective lens on the NanoScribe, which is the high lithography system. As you can see, these are the images of the bright field images of the scaffolds. Once they were printed, it took about 6 to 8 hours to print, and once they were printed, we developed them in SU8 Developer for about 10 minutes. We made these scaffolds out of a polymer resin called IP Visio. We chose this resin as it's biocompatible and good for tissue engineering, but it also has a low autofluorescence rate. As you can see under the GFP filter, this is good as it has little interference when we stain our cells and image them under a fluorescence microscope. So once the scaffolds are complete, we can move on to the cell culture work, where we take the cultured human mesenchymal stem cells that are in the T25 flask. We lift them using Tripole, which gets rid of the extracellular matrix that connects the cells to the surface of the flask, and then we will centrifuge these cells, resuspend them in media, and get a cell count using a hemocytometer. We then seed these cells into sterile scaffolds at 100% cell density. The 70 micron scaffold got about 10,000 cells, while the 200 micron scaffold got about 25,000 cells. And then after they were seeded, we allowed them 1 day to attach in the incubator. After 1 day, we performed a live dead staining where we used calcine AM to stain the live cells to glow green and ethidium homodimer 1 to make the dead cells glow red. A control drop of the same volume was added to the corner of the substrate that the scaffolds were printed on to see if the cells could still attach and survive outside of the scaffold. Under the 70 micron column, you can see from the live staining that the cells had a lot of clustering in the middle of the pores. This is seen in early signs of chondrogenesis, which is really good. In the 200 micron scaffold, you can see that the cells are a bit more elongated and spread out here along more of the borders of the scaffolds, which is seen in osteogenesis for the production of bone. From the live dead staining, we were able to get a viability of these cells, and we determined that there was no significance between the conditions, meaning that the IP Visio resin was not toxic to the cells and that they were able to attach to the scaffold and survive. And so for the main findings of my project, I was able to determine that after 1 day, the cells were able to successfully attach to the scaffold and not be toxic. Next, the 70 micron scaffold was the scaffold that had the highest amount of chondrogenesis, as they had cell clustering. And even though the 200 micron scaffold had high cell viability, it had a lot of adherence along the borders of the scaffold, which is seen in osteogenesis. Because of the time constraint, our next steps in this experiment would to be continue to culture the cells past 1 day for a week or 3 week time period, where we would continue to look at the cell morphology of the cells and also the gene expression of SOX9 and the matrix deposition of type 2 collagen and aggregan to further quantify the level of chondrogenesis each scaffold is undergoing. Okay, I would like to thank my two mentors, Joseph Casilla and Paul Garrett, and my PI, Dr. Ricardo Gattardi. Also the Singh Center for this opportunity and the NSF for funding. These are my references.
Very good.
Thank you.
Good job. Any questions for Haley?
So part of your presentation, I think it was in the methodology, you were explaining a part where you resuspended the surface of media. What kind of media did you use?
We used the DMIM media, where we had TGF-beta1 as a growth factor added into it. Oh yeah, sorry. She asked what media was the cells resuspended in. Yes.
What would you do with something like that once you found a good way of stimulating the growth of this cartilage tissue using the scaffold? Would that be implantable then?
Yes, we would then, you'd ask what the next steps would be. We would then take these cells, lift them, and then implant them into the cartilage defect area and hope that the scaffold and the cells would attach.
Nice job.
Thank you.
Next we have Jada Bonds.
Hi, my name is Jada Bonds. I did research this summer at Harvard University with the Longcar Group, and I worked on the development of aluminum nitride thin films on some silicon. So at the Longcar Group at Harvard, we focus a lot on Diamond. Diamond has a lot of great qualities, one of them being its quantum memory capabilities. It's able to store quantum information in the spins of silicon vacancy centers within the diamond. So what we're trying to do is we're trying to coherently drive the spins with surface acoustic waves so that we can learn more about the quantum information capabilities and expand our knowledge within this field. That's where aluminum nitride comes in. Aluminum nitride is a very piezoelectric material, meaning that it can cause strain to any material that it's on top of when electricity is applied, and that strain can turn into surface acoustic waves. In order to get the aluminum nitride on top of the diamond, I used a method called sputtering. Basically what sputtering is you have a processing gas. In most cases it would be argon, or sometimes in my case it would be nitrogen, and the argon would release the sputtering target particles into the chamber. In my case, that sputtering target would either be a full aluminum metal target or a bonded target of aluminum nitride. And there is a magnetic field under the sputtering target that would direct the aluminum nitride or aluminum towards the substrate, in my case silicon, and deposit straight onto the substrate. Some of the parameters that I focused on changing to get the highest quality film or to speed up the deposition rate was how much nitrogen I would flow in the chamber, how much argon, the bias I would apply, if I would heat it up and how much power I would turn the machine up to, and the pressure of the machine. There are two main types of sputtering, non-reactive and reactive sputtering. Non-reactive sputtering uses a bonded target of aluminum nitride, so basically there's just straight aluminum sputtering on top of the silicon substrate. And then there's reactive sputtering. Reactive sputtering uses a full aluminum target while also flowing nitrogen and argon into the chamber. So the argon would release the aluminum particles into the chamber, and the particles would then react with the nitrogen to form an aluminum nitride film on top of the substrate. Throughout my experience, I found that reactive sputtering is a lot faster than non-reactive. If you can see here, these blue bars over here, these are some examples of the non-reactive samples I sputtered. This navy blue bar is an example of a non-reactive sample that I also applied bias with. And then the red bars are reactive samples, and you can see that they're almost 100 times more, well, 100 more faster than the non-reactive samples, while the navy blue sample is also a lot faster, which led me to believe that applying bias to a sample could speed up the deposition rate, and reactive sputtering is a lot faster than non-reactive. Reactive sputtering I also found allows for more nitrogen to be in the sample and the film quality, and less oxygen, which is a good thing because we don't want our film to oxidize. That would decrease the film quality. Speaking of film quality and crystallinity, one thing that we were really looking forward to in creating this aluminum nitride film was a high quality film and a crystalline structure. These are images that I took of through a scanning electron microscopy machine. This image on your left here, this is an image of a more zoomed out version of the aluminum nitride film. These little columns that you see, basically what I did is when I would prepare the film to be deposited, I would take a silicon chip, put it on the little sample holder, and then put an additional mask on top of that sample that had just little holes in it that would create these films. So it would be columns of aluminum nitride within just the regular silicon substrate. And so those columns are what you're looking at right now. And on your right is a much more zoomed in version of the film up to the 200 nanometer scale. You can much easier see the roughness on this film, and you can also see those little white dots, which is what we suspect to be little aluminum particles, since this is an aluminum nitride film. And that's the roughness that you can really see. Throughout all my experience, what I was trying to do is get like the highest quality film, which is like little to no holes, and a crystalline structure, and also the fastest rate. The sputtering machines that we have here at Harvard are unfortunately really slow, and at first I was working with around 30 nanometers per hour as a rate, but with my experiments, the parameters that I used, reactive sputtering, heating the target up to 150 degrees Celsius, using a 1-to-1 ratio of nitrogen and argon flow, also using a 4 millitorr pressure, a 25 watt bias, and 370 watt power, I was able to get that sputtering rate from 30 nanometers to around 100 to 120 nanometers per hour, which is really great progress for what we were doing. Moving forward, the progress that I made was great, but unfortunately, the film that I was working on did not turn out to be as piezoelectric as we had wanted it to be. And in order to do that, we could try to improve the crystallinity some more. And with that, we could try altering the temperature and the bias and the nitrogen to argon ratio when sputtering in the machine. And I think that would produce a much higher crystallinity and higher quality film that would be much more piezoelectric. Special thanks to my mentor, Eliza Cornell. She was my anchor through this whole project. She was really helpful. The Launcher Lab group, everyone in that group really helped me out with this project. Also, the Center for Nanocell Systems staff, I had to go through a lot of training to be able to do everything that I just mentioned in these slides. And of course, Catherine Haller, all the way in the back there. If we can give her a hand, she's been so incredible throughout this whole process, so helpful and just amazing. Any questions? The bigger applications is to drive the spins of the silicon vacancy centers with surface acoustic waves so we could get some piezoelectricity onto the surface of diamond.
Okay, and what would be like the larger scale?
Larger scale is pretty abstract. What we're doing in our lab group is really just to broaden the knowledge of the field of like the quantum network and quantum systems in general, really.
Okay, so with the ability to drive the spins, that like you'd be able to maybe use like whatever particle you're able to spin up, that could be like a representation of a qubit or something.
Yeah. Yeah.
And that way you wouldn't have to supercool anything.
Yeah.
Okay.
Speaking of supercooling, another process that we could try to get some more piezoelectricity would be annealing the sample, heating it up, and then cooling it down with nitrogen flowing in. I did try that once, but it was a little complicated to mention now. So, yeah. Any other questions?
All right, one more round of applause. Nice job, Jada. Nice job, group. I think we go right in. Or do we have a break?
We have a little break. Whoever's presenting in the next session, if you all would sit in the front row when you come back from break. And also maybe you have time to check your presentation. Like to do that.
I think I stay. Actually, I think I go next door.
How would we?
Okay, she's going to help you check your presentation.
Excellent.
And are you first?
I believe so.
You want to mic up now, or you need a break? How are you feeling?
All right.
Rebecca? Nope.
I'm Anna. I'm at.
Let me look. Maybe I'm on the wrong. Hold on. That was on Tuesday.
Okay.
You're fine. Anna,
There I
gotcha.
am.
You want to mic up? Hi.
Sure.
Let's see. And you're
Michael.
Okay, just want to remember.
Ready?
Is all the AV okay? Is the mic location all right? I don't know.
All right, we're going to get started. I'm very excited to introduce Anna Lee, who is our RE student at Harvard. And I would also like to point out that Daniel, her mentor, was an NNCI RE student about 6 years ago. So continuing the legacy.
Exactly. Right. So hi, yeah, my name is Anna Lee. I'm a student at UC Berkeley, and I was fortunate enough to be able to participate at the NNCI REU at Harvard this summer. My project this summer was imaging of hyperbolic plasmon-phonon polaritons in twisted double bilayer graphene. Now, what on earth did I just say? Give a little bit of an introduction. This summer I worked with 2D van der Waals materials. Those are basically crystalline materials that consist of 1 to 2 layers of atoms, and they're bonded between each layer using van der Waals interactions. They have very unique engineerable optical and electronic properties. And you can actually combine these two different types of 2D materials into van der Waals heterostructures, where you layer the different kinds of materials and you can sort of combine and tailor the kinds of behaviors and properties that you want. And the way you make these structures is by a technique called stacking. And it is very literally picking up individual layers of atoms and stacking them on top of each other. And this method offers a lot more customizability and control than a lot of traditional nanofabrication techniques like molecular beam epitaxy and atomic layer deposition. With those types of techniques, you're limited by the lattice constraints. They have to be exactly the same lattice constants in order for different types of materials to grow on top of each other. And you can't even introduce other factors like twist angles between the layers. So stacking is a very versatile tool. And this is the transfer stage that I used this summer to make my van der Waals heterostructures. And let's get to the topic or the title of my presentation. What on earth is a hyperbolic plasmon-phonon polariton? Well, a polariton is what happens when light couples with an electric dipole within a material. And a hyperbolic plasmon-phonon polariton is when two different types of polaritons, a plasmon polariton, which you can find in graphene, and a phonon polariton, which you can find in hexagonal boron nitride, when they couple together. And this type of polariton is very sensitive to the electronic environment that it's in. And it has a lot of attractive optical applications, and you can even use these types of polaritons to probe for quantum information within a material. And these sort of polaritons, they're also known as quasi-particles. They're very engineerable. You can sort of change the way they behave by modifying the structure of the material that they're propagating within, and even by modifying the twist angle of the material that you're working with. And an example of this is a Moiré superlattice. It is a periodic structure that is generated by a lattice mismatch. And you can actually image these superstructures with hyperbolic plasmon-phonon polaritons. And over here is an example of a Moiré superlattice. I simply took 2 hexagonal lattices, and the top one is a blue one, and I rotated that top one relative to the bottom red one by 5 degrees, and you can see these sort of lighter regions. That is the overarching superlattice pattern. Now, there is a couple of goals in my project. The overall goals for the lab in general was to make 2D materials and 2D heterostructures using this new transfer system, and to build and develop a standard operating procedure for this new transfer system. As for my personal project goals, I wanted to make twisted double bilayer graphene, this kind of heterostructure, using this new transfer stage. And I wanted to see if I could image the Moiré fringes in twisted bilayer, double bilayer graphene using scanning near-field optical microscopy. So this is sort of a little more detailed view of the device that I made this summer. We had the overall substrate was silicon dioxide, and then we had a bottom layer of hexagonal boron nitride that was between 15 to 25 nanometers thick. and then a bilayer graphene, and then another bilayer graphene on top of that that was twisted to about 0.03 degrees relative to the bottom bilayer graphene, and then a thinner layer of hexagonal boron nitride on top of about 5 to 10 nanometers thick to encapsulate the entire device. So this is the general overview of the stacking process. You generate hexagonal boron nitride and graphene flakes using mechanical exfoliation. It's when you use some kind of polymer tape and you remove individual layers, and then you adhere those layers to a silicon dioxide substrate. Then I determine the flake thicknesses using atomic force microscopy, which can give you a height profile of the flake that you're imaging. And this atomic force microscope image, there we go. This image corresponds to this green area right here. And the thickness of this boron nitride flake is about 5 nanometers. Oops, my apologies. And then you use a laser cutter to cut the bilayer graphene flakes to the size that you want. And this is an important step because you know that within one layer or one flake of graphene, the twist angles are all the same. So that way you can control directly the twist angle of your device by generating 2 graphene flakes from one larger one. And then finally, you assemble all of your flakes together using the transfer system. And I have some videos that, let's see if we can pull those up. So this is just a short video of the polymer stamp that we use, picking up a very thin piece of boron nitride, which is outlined in the red. And so that line that you saw moving down was actually the leading edge of the polymer stamp moving down. And then this is actually the steps that you take to release your stack onto a substrate. You actually completely drop the polymer film that it's attached to onto your substrate, and you dissolve the polymer film in chloroform afterwards. Oh. Okay, we'll go through some slides pretty quickly. Okay, and then we would characterize our stacks using scanning near-field optical microscopy, which basically takes advantage of light-matter interactions. You shoot a laser at the surface, and you can actually generate these polaritons, and you can image them. So this image that I have right here is just a piece of graphene, one piece of graphene encapsulated in boron nitride, and you see these diagonal lines are actually the polaritons bouncing off of the edge of the graphene. And you can actually tune these polaritons depending on the wavelength of light that you hit the surface with. So if you have a smaller wavelength of light, the distance between these lines will actually shrink. And so here we have an example of the second stack that I made. This area is where the twisted bilayer graphene is. And then here is the corresponding near-field image. And you'll notice that there aren't really that many features. You can maybe see these very faint diagonal lines and these bright dots, which are bubbles in the sample. And I'll get to the sort of troubles that those caused me eventually. But you can't really see any of the moire patterns that I was mentioning before. And that could result from the fact that this twist angle was perhaps too small. And as a result, the domains of the moire generated by the moire fringes are just way too big for the scanning near-field optical microscope to view. And so here is another image of that same sample, and you can see there's only these diagonal lines. But here we have the last sample that I made, and you can see this periodic repeating pattern of dots, and that is actually the moire patterns that you can image using these hyperbolic plasmon phonon polaritons. And so it was very exciting to be able to get this sort of sample because it was a very short period of time, and there are many different ways you can optimize your sample to get a clearer image, but due to time constraints, I wasn't able to do that. So the fact that I was able to image these types of optical features using this new transfer stage really shows the degree of control and the quality of the new transfer stage that was built at Harvard. And so I'd like to talk a little bit about a few challenges that I had to encounter while making these stacks. The main different issue was stack deformities, and the true bane of my existence was bubbles within the sample. You can see this is a sample that had a lot of bubbles, and these bright dots are those bubbles. And you can actually see these lighter sort of spider webbing designs that are connecting the bubbles together. That's actually caused by strain in either the boron nitride or the graphene, and those prevent these polaritons from propagating within a sample. And other examples of stack deformities that I had to deal with were surface level sort of dust particles, even remainder polymer residue. And so these are all factors that you need to take into consideration when you want to get a sample for optical imaging. So looking forward, one of the things that I would definitely enjoy and want to help out with is making an SOP for this new transfer stage. It was just finished being built just about a month ago. And so if we get a more standardized practice, we can increase the quality and consistency of the stacks that we can make. And there's also potential applications of specifically twisted bilayer graphene in nanophotonics. These polaritons that are propagating within this material are very long-lived, and they have very little energy loss. So there's a lot of interest in them for getting some integrated nanophotonics work. And there's also a lot of interest in twisted bilayer graphene for imaging and focusing. The wavelength of these polaritons that you launch within the material are actually smaller than the incident light, which means you can focus the light beam into something smaller and get something along the order of single molecule level imaging and even subdiffractional imaging. So I would like to thank my mentor Daniel for managing me as the lead mentor for this project and teaching me all about each stage of the stacking process. He's really sort of world-class for this whole process. And Dr. Will Wilson for advising and supervising me for this project, as well as Dr. Yue Luo for helping me with the near-field measurements, and the CNS staff for giving me some much-needed training and equipment usage to complete this project. Thank you. All right. Hello. So I use the Cypher AFM just to get the thickness of the materials, and I used a scanning near-field optical microscope from NIASNOM. It's not in actually the clean room facilities, but that's what I used to get the optical measurements. Yep. Oh, so the HBN, they have two purposes. One, HBN is really stable. It's one to sort of stabilize the entire device. I actually tried to cut the HBN with a laser cutter, and I cut the substrate before I cut the HBN. And it also contributes the phonon polaritons that hybridize with the plasmon polaritons in graphene. So that's what allowed us to image the fringe patterns. Actually, there has been a paper published by one of the mentors, Yue Luo. He examined twisted bilayer, double bilayer graphene, and they found that in order to get a good image of these moire fringes, you need to have a very small angle. Yes? I briefly talked about polaritons and how light can couple with electronic oscillations within a material, but I didn't go too deep into it. Yeah. Yes. I prepared the graphene using mechanical exfoliation using a polymer tape. So you would take a crystal of graphene, adhere it to the tape, and quite literally just put the tape on and then peel it back, and then each time you do that, you get a thinner and thinner layer of graphene. And then you adhere that graphene to a silicon dioxide substrate by just taping it onto the substrate and then letting it bake at about 100 degrees for a couple minutes. Sorry, could you say that again? Graphite crystal, yes. All right. Thank you.
And then next we have a video because Aristine Margarita could not be here, so we're going to play a video.
Hello, everyone. My name is Aris Rondarina, and my project was on formulating lipid nanoparticles with targeting peptides. Lipid nanoparticles consist of 4 main structural components, or lipids, which can be optimized for delivery in terms of changing their lipid components, formulation ratios, and oligonucleotide cargos. Lipid nanoparticles are ideal for RNA delivery because they can be customized for therapeutic applications. They can prevent nuclease degradation of mRNA. They can increase nanoparticle stability in physiological fluids and also increase organ selectivity, which may be achieved by adjusting proportions and types of lipids. Some FDA-approved RNA LNP therapeutics include Onpattro and the COVID-19 vaccines. In the Qualm Lab, we focus on traumatic brain injury, which affects 3 million people in the United States with a cost of about $93 billion. TBI is a multimodal disease disruption which leads to increased permeability and alterations of metabolic processes at the blood-brain barrier. Onpattro, an approved formulation by the FDA, is our gold standard formulation that we wanted to replicate. You can see they have different lipids with different mole percentages and their LNP characteristics in terms of the Z average size between 60 to 80 nanometers and polydispersity index, or PDI, which is less than 0.2. PDI is the range of sizes, so the smaller the number, the smaller the range of sizes there are. And so again, in TBI, there are disease-specific changes which occur in the microenvironment. This allows for LNPs conjugated with targeting peptides to selectively accumulate in the inflamed brain. The LNP formulation process consists of several steps, starting with fabrication of the nano mixing device, the LNP formulation, using the microfluidic mixing device, and lastly, characterization with dynamic light scattering. With the microfluidic mixing device for LNP formulation, I just wanted to give you a close-up of what it actually looked like. And so this is the actual device in real life and sort of a zoomed in look at the staggered herringbone structure used to mix the lipids and RNA together. And so the idea here is that we have 2 different phases with the ethanol or the lipids in ethanol and the RNA in an aqueous phase, and we mix them rapidly to form lipid nanoparticles. We primarily use dynamic light scattering, or DLS, for LNP characterization, and the idea between this tool is that different intensities of light yields different velocities of Brownian motion, and we can use that to determine the size of the particles. And so here's sort of a graph of what we would usually see from the data, and on the bottom right is the actual picture of the device. Here are our 3 goals that we wanted to achieve for this project. And so with our first experiment, we wanted to look at ALC formulation, comparing 2 different methods, using the microfluidic mixing device versus a pipette mixing method. And we can see here that the MMD resulted in higher quality nanoparticles in terms of lower PDI and also a smaller nanoparticle size. And on the right, it sort of sums that up as well. We have an overall lower amount of particle sizes and also a smaller PDI. And here we wanted to vary the formulation flow rates to determine how this would affect nanoparticle quality. Overall, there was a minimal effect on nanoparticle quality, and the idea between this is that we want to see if we would result in higher quality nanoparticles with a faster flow rate, which was not the case. And also, we found out that the device started to break at higher flow rates. So keeping it at a standard flow rate of 1.35 and 4.05 was ideal for lipids and oligonucleotides, respectively. When we varied the lipid nanoparticle concentrations in terms of the lipid concentration ratios, our standard ratio was 2.0 millimoles, and this gave us a Z average of approximately 75 nanometers, so the average size, and the LNPs were more uniform in size. Again, it's not a huge difference, but we can see that that was what we got. So our standard formulation lipid concentration ratio was ideal. And that sums up our first goal: vary and assess formulation procedures and parameters for impact on LNP properties such as sizes less than 100 nanometers and uniformity of sizes. Our second goal was to see if we could conjugate our lipid nanoparticles with targeting peptides. And so for this experiment, we wanted to attach a CGKRK, which expresses FAM. And so we could see the fluorescence in terms of our future studies. And we can see that we had a successful conjugation of our peptides with our LNPs. That sums up our second sub-goal: conjugate lipid nanoparticles with targeting peptides. Lastly, we wanted to quantify the amount of peptides per LNP. And so this was the sort of data that we got from the nanosite. We got concentration, and the general calculation was this: peptides divided by ml, overall divided by LNPs divided by ml. And so by having this data, we could figure out how many peptides were on each LNP. And ultimately, with the math, this is what we determined. I'm not 100% that this is accurate, but this is what I calculated with the time I had. And so that sums up the three goals for my project: formulating lipid nanoparticles targeting peptides. We could see that I was able to vary and assess the different formulation procedures and parameters to see its impact on the LNP properties. I was able to conjugate LNPs to targeting peptides and quantify the number of peptides per lipid nanoparticle. Again, I am not 100% sure that number 3 was correct, but that's what I got. For future studies, determine which cell types, we want to determine which cell types or proteins to target that are unique to the disease-specific changes to the microenvironment after TBI. We also want to discover and develop new therapeutics that can selectively accumulate in the inflamed brain. And thank you to everyone who made this possible, especially my lab group, the NSF, SDNI, my PI, Dr. Esther Kwan, my mentor, Caitlin Miyasaki, Eves, the SDNI Executive Director, etc. Thank you so much.
So you're going to have to email Eris if you have a question. Next up we have Ojak Patani, who also did his work here. Oh, you need a mic? Right here.
Just one bar.
It's just one bar.
Make sure that.
right, hello everyone. My name is Ojas Kulkarni, and I'm a junior at the University of Utah studying computer engineering, applied mathematics. And this summer I was working on a project called the simulation of glancing angle deposition with Dr. Chuang Chu, Dr. Kevin Walsh, and Dr. Seamus McNamara here at the University of Louisville. So just as a quick introduction, glancing angle deposition, or GLAD as we call it, is a bottom-up nano-manufacturing technique used to manufacture these nanostructured thin films, which have applications in all kinds of areas like optics, sensing, magnetic storage technologies, and various other fields that I haven't even thought of yet. And so these features can have a size range of about like sub a micron, and their structures depend on their application as well. So that's why, as you can see here in these things, these structures are different based on their application. So this leads me to the theory of glancing angle deposition, kind of how it's made and its design elements. So there are two types of angles that are particularly present in glancing angle deposition. There's this incident angle that the vapor comes at, and there's also a continuous rotation angle, or the azimuth rotation angle. And so as the vapor is deposited onto the substrate, the vapor that's coming from down here, it creates these nucleation sites, or seeds as we call them. And these seeds create a shadowing effect. And as the shadowing effect is created, it kind of prevents the growth of further columns that are in the shadowed region, as you can see here. And it encourages the growth of columns that are nucleation sites that are in front of the shadowed region. And therefore, a nanostructure is formed. So there are two different types of seeding patterns that are used in GLAD, natural seeding and pre-seeding. Each have their own pros and cons, where natural seeding does not require the use of any initial patterning on the substrate. But predetermined seeding needs either photolithography, FIB, or some other embossing nanomanufacturing technique to put introduce these seeds onto the substrate itself. So this leads me to the project goal for this summer, which was to develop a simulation of that, 3D simulation of that process that you just saw earlier. I wanted the user to be able to change the incidence angle, the rotation angle, and to be able to demonstrate the relationship between the alpha and the beta. As you saw in the last slide, there are two different angles present. So just some previous background on this area of study. What we found out was that the simulations for glancing angle deposition, and particularly thin films, has been conducted. But what we saw was that these simulations are very slow and kind of require the use of specific hardware like GPUs or TPUs, which are not commonly accessible. And even with these hardware acceleration units, they still required 100+ hours of rendering time, which is not feasible for a single simulation. And as you can see in these results, the results aren't very consistent either, that's why we want to address all these problems and create something that was very specific to our application. So my idea for my simulation project was to recreate the process exactly as it happens in real life, just on a smaller scale. So the particles will come in at a particular incidence angle that's set by the user and kind of land on the substrate. And if there's any initial velocity if there is an initial velocity present, and if there are any collisions that happen with these incoming particles with any other pre-deposited particles, they land at their appropriate positions, whether that be at the bottom of the substrate here or at the top of the nanofeatures here. So this leads me to the collision resolution algorithm, which was the biggest hurdle in my case, since it had to be fast enough to be able to be run for a large number of inputs, but also kind of accurate enough to be able to predict for these tiny spheres that we represented here in our particles. So as this happens, this is just a demonstration of how the collision resolution algorithm works. So the incoming particle comes in from a particular incidence angle. It has a velocity vector due to its incidence angle that it casts from its point of origin toward where it's going to land on the substrate. And if this ray intersects with any other previously deposited sphere on the substrate, a collision is detected and then registered. And when this collision is detected and registered, the position of the incoming particle is then updated to reflect the point of intersection between the ray and the previously deposited sphere. So as you can see here, a nanostructure is grown, and if there are multiple points of intersection, as you can see here, the closest one to the point of origin is chosen so that a nanostructure gets longer and doesn't necessarily form a here or like here or something. So these are just a demonstration of the growths, as you can see here in this video here. You can see the nanostructures growing at that particular incidence angle. And here it also shows the percent coverage, which is dependent on the incidence angle that is set by the user. It kind of shows how densely packed together the nanofeatures are, and they should be the same among all the monolayers that are deposited onto the substrate itself. So we also compared our simulation results with our experimental results. As you can see here, we simulated 75 degrees, 80 degrees, and 85 degrees. And as you can see here, each of these structures do qualitatively agree with our simulation results, just with a little bit of margin of error. Since this is a Monte Carlo kind of a simulation, there is a bit of randomness present in where the particles originate from. And because of that randomness, these kinds of margins of errors occur, and then we can include them in our simulation as well. So we also wanted to compare the column growth angle beta and the incident angle alpha, as we saw in this image here. And as we can see in the yellow line here, the incident angle alpha is always less than, or beta is always less than alpha, as you can see here, and which it's exactly as expected, since it was proven in earlier research in this field that beta should always be less than alpha, and that's because of a variety of factors. For this theoretical calculations, we use this equation from the same research paper that they demonstrated that particular phenomenon in, and that shows how there's a kind of a first order approximation of what the beta and the alpha relationship should be. And we observed that below 70 degrees, we just saw that they kind of created these continuous thin films, which were not necessarily useful in our case to create nanostructures. So initial seeding patterns are also an important factor of glancing angle deposition, and we simulated 3 of these seeding patterns here. As you can see, the line seedings are kind of just lines grown at a particular, with a particular distance between them. And spherical seeds are just these things with a particular distance between their x and the z positions. And spherical seeds are kind of just these things, but like wider. So we did demonstrate these in our simulations as well. As you can see in these simulations, these line seeds kind of form like a wall-like structure, but these spherical and cubical seeds kind of form these individual nanostructures, whereas a cubical seed, or column seeds as we call it, are thicker than the spherical seeds as well. So we also wanted to simulate the experimental complex structures, as you can see in this picture here. We want to simulate a zigzag, a column, and then a helix. And as you can see in the simulation here, simulation results, I just colored them so that it was easier to see. We can see a zigzag kind of forming and then a column kind of forming on top of it. And as you can see here, these white dots at the very bottom of the substrate represent the seeding patterns, but we found out that these seeding patterns don't have much of an effect on if you want to simulate complex structures. This is just a spontaneous recipe we came up with to create these experimentally, but yeah. I also wanted to comment on the efficiency of my collision resolution algorithm. We tested out 4 different collision resolution algorithms and found out that this last one right here was the fastest one, since even though their time complexities is around the same, then the number of iterations that they have to do is much lesser for this one. Whereas if you look for this one, it's much higher, and thus it reflects the rendering time as well. It's 40 seconds, which is not exactly what we wanted. So we just used this collision resolution algorithm here to use for all our demonstration and testing purposes. So just to conclude, my project goal was to simulate the GLAD process and thin film to grow thin films and these nanostructures. We did, in fact, develop that simulation in a Monte Carlo kind of fashion instead of a molecular dynamic or some other sort of simulation strategy. We also simulated these growths on different seeding patterns, like initial patterning or natural seedings. We demonstrated the outputs of percent coverage and the simulated growth angles and compared their relationship with the incidence angles. And we also developed different collision resolution algorithms so that they can be improved upon further. So yeah, I would like to thank the NSF, the Impact RU here at the University of Louisville, the NNCI, and the Kentucky Multiscales, and all my mentors for helping me with my project. Thank you. So I just use a personal computer. There's no GPU or I do have a GPU, but we didn't need that for my presentation, for my simulation. But I used Python and incorporated like a CPython package to develop the simulation. Yeah.
How long did it take for your simulation to generate?
Yeah. So I think it was on the last slide. So the question was. But the question was how long the simulation took to render. What happened there? But the simulation took about 3.5 seconds, which is very fast since we're simulating like 35,000 particles. so the question was, is the simulation scalable or is it set at 35,000 particles? It is scalable, but if we scale it less, the number of particles depends on the incidence angle. Since if the incidence angle is too high, like 90 degrees or something, there are no particles landing on substrate, so nanostructures wouldn't form at all. So we kind of need to scale that up. But yeah, it is scalable if you wanted to do that.
As the structures grew, did you have any like instability built into the stability of the structure as it grew longer and longer to do things bigger?
Stability as in?
I guess like as the particles kept getting longer and longer and longer, did you assume that the particles stayed stable, or the long hairs kind of got wobbly?
I see. Okay. Yeah. So the question was, are the features stable basically? And yeah, we don't have support for that yet. So that includes some effects of temperature and pressure that we don't include in the simulation. That's some of the future work that we're planning.
Thank you. Next we have Laura. Puerto Rico, Bogota.
Yes. Okay, so good morning everyone. I'm happy to be here. My name is Laura. I come from UC San Diego, so on the West Coast. And my faculty PI was Dr. Michael J. Saylor. My mentors were Oscar Calzada and Madeline Brown. And I had the opportunity to work with some really smart people featured here. They're like trying to be socially distanced. I don't know if you can see, but like they're having some space apart. And yeah, I'm just really excited to be here today. All right, so you might be wondering what our project is about, and I just want to start out by asking, have any of you ever gone to the gym? Raise of hands. Okay, yeah. So today I'm going to be talking about the anterior cruciate ligament, also known as the ACL. And the ACL is a ligament in the knee commonly torn through sports injury that requires a reconstruction surgery with a lengthy recovery time due to the slow and improper neovasculature formation. Because unlike other ligaments in the knee, the ACL cannot repair itself since it's surrounded by synovial fluids and lacks direct access to any exterior blood supply to produce a clot to join the torn ends. And you can see on this image on the right what that would look like. So we can see the normal ACL and then the torn ACL. All right. So therefore, the experiment's main objective was to improve the healing of surgically repaired ACL by capitalizing on its capability for revascularization. So the Avidin will be the drug used to promote revascularization, which will be used by loading into mesoporous silicon nanoparticles. And these silicon nanoparticles will be incorporated into a PCL patch intended to be surgically placed into the injured ACL region to induce a controlled and a slow release of the drug. So moving on, this is what we worked on. And I want to tell you just like a little bit of backstory of why we used Avidin. So you might be wondering like what exactly is Avidin? So Avidin is the drug that we decided to use. And we decided to use it because it's less expensive than VEGF, which is also known as vascular endothelial growth factor. And we're also using Avidin instead of V. It's less expensive, and it also has a similar size and isoelectric point. So VEGF has an isoelectric point of about 9, and Avidin has an isoelectric point of around 10.
And so these images here show the first step of the project, which was electrochemical etching. And these are just like some pictures taken on iPhone. This is nothing professional. This is just like on the phone. But we can just see like what that would look like. All right. So for the procedure, we did a couple of things. So as I mentioned, we tried to do anodic electrochemical etching according to the procedure that we can see on this right side. And then we then moved on to the avidin and the oxidation loading that we can see on the left side of the slide. And I don't know if you can see it, but we tried to use like an airbrush, kind of like the ones that you use for makeup. So we tried to do a similar process there. And then moving on, we used the nano drop that we can see on the bottom side of this presentation to calculate our measurements. And then finally, we did ELISA measurements afterwards. All right. So throughout the program, we have been looking at stability in 1 week with the goal of exploring what would happen in 2 weeks, even 3 weeks, and 4 weeks. And we're also looking into the encapsulation efficiency with the goal to increase mass loading and ensure that this mass loading is reproducible, and also to explore different methods of surface modification and oxide trapping. And we're also noticing the release to see if the dose can be maintained in a 2-week time period, because currently it's only been characterized for a 3-day time frame. All right, so here you can see some scanning electron microscope SEM pictures in the nanoscale, displaying loaded oxidized porous silicon microparticles trapped in the PCl polymer matrix. And moving on, in this data-driven analysis, we discovered that a polyprolactone patch and a hybrid porous silicon can be used with avidin. And after completing multiple trials with avidin samples, we conclude that we can use avidin to move forward with in vivo studies in animals. And the patch has the capacity and capability to revascularize the anterior cruciate ligament post-surgically, yet we would still want to see how this performs over time. So by looking at this graph, we have time in hours in the x-axis, and then the avidin concentration on the y-axis, and we can see that the patch released 4% in 3 days, since it's 100 hours. Okay. And so in this graph, we can see what an avidin patch would look like over time, with the days in the x-axis and then avidin concentration in the y-axis. And we can also see that, like, in 3 days, it was like, in 3 days, it took about 100 hours. And so currently, we're preparing to take this study into biocompatibility studies and eventually in vivo animal studies with our collaborators in the medical school, and help in drafting a protocol for animal use with the IACUC. And after establishing the biocompatibility of the hybrid patch, we are likely going to be performing a study that implants the patch into the hind limb of a rat, and we will move on to ACL model testing with rabbits. And to evaluate the patch's performance in model testing, we will utilize histology to screen for the presence of angiogenic growth factors and tube formation. And additionally, for the procedures conducted in rabbits, we will need to design a delivery system for the placement of the patch around the ACL. All right, so I would just like to thank the following people and just thank all of you for being here, and thank you for listening. Yeah. Oh yeah, sure. So we can go back. These are the scanning electron microscope images, SEM, and these are in the nanoscale, yeah. So you can see the patch. Good question. Yeah, so these images are like around 200 nanometers. Yeah.
So I was just wondering, before you tested your patch release, if you washed the patch beforehand and then tested the release.
Okay, yeah, so great question. So the question was if we watched the patch before the release and then after the release?
If you just washed it before to get rid of any surface level particles before you tested the release again.
Yeah, okay, great question. Yeah, so it was just like the wash before doing the testing. Yeah, so we didn't necessarily do that, but we'll keep that in mind for future projects. Yeah. Thank you.
It was really great in the presentation. Given that when there is an ACL tear, there also are additional bone defects that can sometimes happen, right? If you tear an ACL, then you have cartilage on cartilage, right? So does your patch also help with some of that degradation that occurs as well?
Okay, great question. Thank you. So the question was, since the ACL happens on the knee, does that also affect other areas around the knee, right? So to answer this question, I would say yes, the ACL is one area of the body. So we're just targeting this at the nanoscale, so we're getting really specific on this. And I would say we're not currently focusing on other areas of the body, but that would be a great opportunity for further research. Yeah. Thank you. Yes. Thank you.
Okay, thank you for that introduction. My name is Bethany Clace. This summer I had the pleasure to work at Duke University with the RTNN. I'm a junior at the University of Tennessee. This way you can hear me better. And this summer I worked on film synthesis and crystal growth of perovskites by melt processing. So first, a little bit of background. I'm sure you've all heard what a perovskite is at this point, but so basically a perovskite is just a crystal structure with an ABX platform. So 2D lead-2 halide perovskites are very popular at the moment for their tunable electrical and optical properties, as well as their structural stability. The main downfall with these perovskites currently is that lead is toxic. This diagram here shows 1-methylhexylammonium lead iodide. It's a compound that I synthesized this summer. And oftentimes, perovskites are formed into films so that they can be used in electrical applications. One of the main types of film formation is solution processing or spin coating. But the main downfall with spin coating and solution processing is that they use toxic solvents. Melt processing is another form of film formation that is solvent-free, and I focused on that this summer. So since lead is toxic, it's important to look for lead-free halide perovskite alternatives. Tin is the most similar to lead property-wise. However, tin does not like to exist outside of a glove box and is very volatile. So another option is trivalent antimony and bismuth halide perovskites, and they have very similar electrical properties to lead, but are less toxic. This summer, I focused on racemic and chiral 1D bismuth and antimony trivalent halide perovskites. This compound here shows tetramethylpyrazine antimony iodide, which is a long mouthful, but yeah. So for my methods this summer, I formed powders with solvothermal synthesis. I don't know if any of you are familiar with that, but so essentially you take an autoclave, which is this right here. You put your precursor solution and powder, you heat it up to above the solubility, and then as you cool, you're going to adjust the solubility and crash out a powder. So I then take that powder, I vacuum filtrate it, I grind it, and I suspend it in an anti-solvent, specifically toluene, and I drop it onto a substrate, which is shown here. So then moving on to the exciting part of this project, the hot press. So this diagram here shows the hot press. It has 2 independently heated pneumatic pressure plates. So essentially you're placing your sample and you're applying heat and pressure at the same time. So I preheat the press and then I place my sample right around here and I apply pressure. After a specific amount of time under heat, I cool it rapidly, quenching, and I relieve the pressure. These films are then characterized using optical microscopy, X-ray diffraction, UV visual spectroscopy, and profilometry. And then for the X-ray diffraction, I use Bragg's law to calculate the phase purity and crystallinity of each sample. So for the formation and characterization of the lead system films, I discovered that increasing pressure will orient grains, and immediately applying pressure will destroy your substrate. So these films are approximately 2 microns thick, and this XRD graph here demonstrates powder versus melted perovskite. And so this graph is just essentially saying that what you're putting in is what you're getting out after you melt it. This image in the middle is the film under a microscope, and it doesn't have complete coverage, but compared to the antimony systems, it looks a lot better. And then this graph over here is UV visible spectrum. So essentially the spectrum shows that the lead system does absorb light. So for the formation, moving on to the antimony systems, for the formation and characterization of TMPZ antimony iodide, the compound that I showed previously, I was unable to form films due to time constraints. However, I was able to form crystals. So I found that when you treat your substrate, specifically I used glass and I made these hydrophobic, and having increased amount of powder per substrate will improve your coverage and quality of these films. This image shows some crystals. The main thing is the hexagonal crystals shown here. And then for the formation and characterization of S-methyl-TMPZ antimony iodide, melt process crystals. S-methyl-TMPZ antimony iodide is a chiral compound, meaning that it has a lower melting point than this compound here, and is a little more comparable to lead. So I found with this compound that it decomposes very rapidly after melting. So less time is ideal to prevent degradation. And as you can see from this XRD graph, I have the powder and the melt. So essentially what you're getting out is what you're putting in. And this is significant because this is one of the first instances of full recrystallization of a melted lead-free perovskite. And then this image here shows a crystal of this compound. So for my key findings and general observations, I found that with the hot press, in order to produce better films, it's important to have treated substrates, to increase the pressure gradually, to quench by cooling and running under cool water, and to have more powder per substrate. That way you have more mass and have a thicker film. And then for the lead system films, I was able to form films using this method of melt processing. For the antimony systems, I was able to form crystals. But as I stated earlier, from the XRD pattern, this is one of the first instances of full recrystallization of a lead-free perovskite following melt, which is very significant. And I was able to form crystals by melt processing of both antimony systems. So for next steps, because of the time constraints, I was unable to form films of the actual antimony systems, but in the future, my mentor will be taking over and actually forming films of these antimony systems, and then to continue optimizing the hot press and tune its parameters so that it's easier to form films in the future and to improve the efficiency of the process. And then here are my references and my acknowledgements. Thank you. Are there any questions? Yes? Right, of course. So the question was how I quenched the films. Okay, so the hot press here, we have basically a pipe that runs house water through the independently heated plates. So instead of the water being applied to your sample, it's applied through the plate, so it just cools the plates rapidly. Yes? The question was, where does the water come from? It's just tap water. The water doesn't affect the sample in any way, it just cools the plate down. Do you want me to turn the mic off? Okay.
So these are the locations of the historic sites. Up to the north is the Ohio River, as you can see here. This forms the border of this forms the border of Indiana and Kentucky. And then you can see the Green River right here, which branches off of the Ohio River. Up here near Dam 2 is the location of the Baber Hotel. And down here is the Big Bend, which contains the Dewey's Shell Mound and the Annis Mound. You can see here there is another mound called the Carlston Annis site. That is a different site that ended up having a very similar name to the Annis Mound and ends up also being in the same sort of geographic region as well. Because of that, it's kind of confusing, but that is not the one that we're looking at. Ours is just called the Annis Mound. So also in more background into the shells themselves, the annual growth bands are formed by a layer of light, well, it's formed by two layers, the light and dark layer. The light layer represents the growth during the warmer seasons, and the darker layers represent the growth during the colder seasons. And we also focused on two layers of the shell, one being the prismatic layer and the other being the nacreous layer. The prismatic layer is this really light white layer that surrounds the surrounds the shell, and this layer is approximately 200 microns thick. It will depend depending on the shell. And on the left is just basically the close-up, and then on the right is the umbo, or this sort of like rounded area of the shell. As you can see here, there's the prismatic layer, which is really thin, and this rest of the layer is the nacreous layer. And on that picture, you can also see the sort of banding and the differentiations in color, which represent the different seasons of growth. Now, in order to characterize these shells, what we did is we mounted these shells in epoxy and cross-sectioned them from the umbo, again, which is that rounded area. We cross-sectioned them from umbo to the ventral margin, which basically is like that edge of the shell. And we then grinded them in order to produce a smooth surface. So one of the first instruments we used was the digital optical microscope. On the left is a stitched image of the whole cross-section of the shell. Here you can also obviously see the differentiation in colors going throughout. And then on the right is a closer up image and the location of where we measured the annual growth bands. These shells were measured manually using the microscope software, and we did this by hand in order to track the growth trend of the shells. Here is an example of this sort of growth trend study done in a previous journal. This is a growth trend graph of a species of freshwater pearl mussels. And as you can see, there is a downward trend overall. And that is because as there are newer growths coming in, those newer growths have to cover a larger area of shell each time, and because of that, you will see a downward growth. However, for our shells, we weren't able to see that same growth trend. In fact, the only one that actually has that sort of downward trend is the last one, which is Dewey's Shell 2, which is one of the late archaic ones. However, this could be due to the fact that the shells have variations across the years, across the seasons, and we believe that the sort of variations in that season and yearly variations likely overpowered the growth trend, as these have really small numbers of bands. As you can see, the band numbers only go from around the lower teens, so around 13 or 11 to 13, and the highest is around mid-lower 20s. This is contrasting with the other one, which ends up going all the way from 70 to 80 years old. So as you can see, there's like that sort of variation, but they're still able to fit it, and we weren't able to. So for our next instrument, we also used the scanning electron microscope. In this case, we used the backscatter electron imaging technique, so that way we can see the sort of compositional contrast between the majority of the shell as well as the annual growth bands. And to the right is a sort of close-up image, and those red dashes are where we think the annual growth bands are, and the dotted red line is where the prismatic and the nacreous layers are. As you can see, there's a sort of structural and density difference between the prismatic and nacreous layer. Here, within the SEM, we can also do EDS, or energy dispersive X-ray spectroscopy, and it's able to pick up really light elements like carbon and oxygen, and from EDS, we were able to get the approximate atomic ratio of calcium carbonate, which is to be expected as it is a shell. Here's the numbers if you would like to look at them. However, it isn't able to pick up, the EDS isn't able to pick up trace elements, which we were wanting to focus on. And so because of that, we moved on to XRF. And XRF is a form of spectroscopy called X-ray fluorescence spectroscopy. And it operates very similar to EDS, but it's able to get those lighter trace elements, or the smaller trace elements. On the left is the optical image of the shell that we were using, and then on the right are the elemental intensity maps that we got. Up to the one that's labeled CA is the calcium elemental intensity graph, and then the one on the bottom is the manganese. Obviously, the calcium one, as the shells are primarily made out of calcium carbonate, it is basically a solid color. And then we found an interesting thing in that manganese has that sort of banding structure. And then on the right is an even more higher resolution manganese intensity map, as we were trying to find sort of where the lines are, where the bands are more distinctly of the manganese graph. So in conclusion, we were able to prepare these prehistoric and historic shells for analysis and identify those annual growth bands, as well as we were able to identify those annual growth bands for the different types of microscopy that we use. And the expected downward trend that we wanted was we assumed to be due to the shorter lifespan, and the variations in those yearly and seasonal growths tend to overshadow that trend. And then we were also able to do elemental analysis for XRF and EDS. And we obviously confirmed that the majority of the shell is comprised of calcium carbonate, and that trace levels of manganese were found throughout the shell and created a banding structure. Now, in a previous study that we did, there was a journal that explained that the manganese correlated with an increase of organic and biological materials in the water habitat, as well as a decreased shell growth rate in the winter. Here are my references. Do you have any questions? Yes.
I don't know if I missed it, but when we were measuring the growth band,
Yes.
for each different type of shell, how many shells did you analyze for those growth bands?
The question was how many shells did we analyze for the growth bands. Our sample was really small, as we only dealt with an initial sample of 4, and we measured all of those. We actually had to end up excluding a sample because it had a really complex band structure, but we have a lot more shells, we just didn't really get to them.
All right, hello everyone. My name is Steph, and I worked at the University of California, San Diego on the solid state synthesis of iron fluoride nanocomposite cathode materials for lithium-ion batteries. So my project goal was to synthesize iron 2 fluoride as a nanocomposite cathode using fluoropolymer precursors and iron sources at varying ratios, and to characterize the morphology with SEM, and to confirm the presence of pure FeF2 with X-ray diffraction, and to ensure that the nanocomposites were coated with carbon to improve the electronic conductivity and improve the current energy density of the cathode material, And ultimately, we were trying to find a cathode material to improve the specific capacity of the cathode. And some of the literature that was used to determine the precursor decomposition temperatures for the reactions that I was working with were supported in literature. And so those temperatures are shown to the right. So some background design criteria for cathodes include having a operating voltage of 4.5 for this particular material with the liquid electrolyte of this battery. And capacity, rate capability, the cost, sustainability, and safety are all important design criteria. And a little bit more background on what a lithium-ion battery is. It is essentially an electrochemical cell that includes a cathode, an anode, an electrolyte, and a separator. And upon charging and discharging a battery, we get what is called lithiation and delithiation, where lithium ions passivate through the separator and the electrolyte to the cathode and the anode. And specifically with cathodes, iron fluorides in particular are commonly synthesized by the fluoridation of metal oxides or oxalates by toxic hydrogen fluoride gas, and also large voltage hysteresis between charge and discharge profiles can occur. So the factors that were considered for the diffusion of lithium ions in my cathode material were the ratio to the active material, the binding agent, and the carbon composite ratio, the particle size, and the particle morphology, or even size distribution. So the typical size that we're looking for is around the 100 nanometer scale, which means we can have a relatively porous material that allows for electron and lithium ion diffusivity. And upon lithiation, we can get a conversion mechanism, a topic-tactic phase transformation that occurs during the process of charging and discharging a battery. So going to my experiment and my work, I first reacted iron fluoride, or I reacted PVDF, which is a fluoropolymer, with iron oxide at 3 different weight ratio percents. And essentially in a furnace, I would heat the sample, the precursors, at 500 degrees Celsius for 1 hour in argon gas, an inert gas, with this temperature protocol provided here. And in this reaction, this is our baseline reaction, which is compared with an additional reaction including PTFE, which I will show in a later slide. But this reaction includes the production of, or includes HF production, which is a reactant for the production of FEF2. And there are possible side reactions that could occur. And further understanding of the reaction mechanisms needs to be discerned through thermogravimetric analysis to understand if there is the potential for iron 3 fluoride to become synthesized and if carbon acts as a reducing agent. So XRD confirmed the presence of FEF2, and specifically the 2-to-1 ratio seemed to give us the purest FEF2 from this reaction, and this was compared to XRD peaks from other literature and the ICSD database. And the morphology was characterized at the micron scale all the way to the 500 nanometer scale, and we can see we have a relatively even size distribution, and so this is a relatively porous material. The second reaction that I focused on was the thermal decomposition of PTFE as a fluorine source, and the iron source was iron oxalate dihydrate. And so there are also unknown side reactions that could occur, and so further characterization of the reaction mechanisms would enable us to determine whether or not this reaction will yield the products, the FEF2 product that we are using for this material. And here's the overall process that occurs during this reaction. So through random chain scission, the depolymerization of PTFE can occur, and at this particular temperature of 600 degrees, at this protocol, temperature protocol, we can get nanocomposite materials that are coated in carbon. And so here's further XRD analysis. Here are the baseline precursor XRD peaks, I wasn't able to do a Rietveld refinement to calculate the Miller indices, since there is not a lot of XRD data that I can compare to. And there were certain parameters, such as the lattice parameters, that I wasn't able to access. So I couldn't calculate like the interplanar spacing and to overall characterize the crystallinity. And so here on the right is also more SEM images at the 3 micron scale, showing that the carbon actually was more of a platform for FeF2 sites rather than carbon encapsulating FeF2, which was interesting. So now that I synthesized this cathode material, we needed to assess the performance of the material in a lithium-ion battery half cell, which basically means we were able to understand the specific capacity of the cathode material. And so this methodology to create the half cell takes about 3 to 4 days. And so we have our precursors, which are added to a furnace. And so then we get the material, and then through hydraulic pressing, we add it to the furnace, and then we prepare a slurry which can be casted onto aluminum, and eventually we heat this at 110 degrees Celsius, and we assemble the half cells in a glove box to ensure that there are no contaminants in the half cell assembly. We polish the lithium to ensure that when we place the electrolyte, we have an even distribution to prevent any short circuiting. And here is just the overall assembly line for the half cell. So here are the performance metrics for this cathode material. These two graphs represent a couple of the half cells I was able to fabricate. And we were getting about a specific capacity in milliamp per grams at around 600 to 700, which shows promising results for this particular cathode material. And we were able to get agreement in about 700 milliampere per grams for the second cell. And the discharge and charge rate was, for this first cell, was at C10, which is slow charging. And for this was also at C10. And then my last performance metric I was able to get is quite interesting. It reveals that there was the potential for a contaminant in my sample, possibly sulfur, from a graduate student before me. And so we see, this 2 voltage plateaus and a quasi-linear state, which compared to other literature could indicate why the performance, the specific capacity, or the ability for this cathode material to store charge was about 400 to 500 milliampere per grams. And so I would just like to acknowledge my graduate mentor, Sichen Yu, master student Junwei Gao, and my principal investigator, Dr. Ping Liu, and Dr. Eve at SDNI for allowing me to conduct this work. And yeah, that is the end of my presentation. Thank you so much.
ASMR. Don't forget. Okay. If you walk away without that, it will fall.
Okay. Okay. Hello. Is it on? Oh. Cool. All right, so my name is Mariana, and this summer I was able to conduct my experiment using the surface-enhanced Raman spectroscopy to diagnose a disease. So a little bit about me. As I mentioned, my name is Mariana Jimenez. I'm from Tucson, Arizona, and this past May I graduated from Pima Community College with an associate's in science and an emphasis in engineering. I will continue my study at the University of Arizona as a biomedical engineer undergraduate student. This summer, my REU took place in Northern Arizona University in Flagstaff, Arizona, where I was able to work with Dr. Jesus Velasquez Salazar, PhD candidate Alondra Hernandez Cedillo, and my mentor, Dr. Miguel Jose Yacoman. So a little bit about my research. So what is breast cancer? Breast cancer would be cancerous cells that form in the breast. It is a public health issue as it is present in both males and females, but it is more common in females. It is also the highest cause of cancer deaths in the world according to the records of 2020, and it is detected through a couple different ways, but the golden standard technique would be mammography, which has the sensitivity range of 72% to 88%. The way this works, it is two plates that compress the breast and exert radiation. The problem here would be that this technique is not available to anyone under the age of 40. Reason why is because the radiation can actually induce the breast cancer. Once this technique is available, females tend to form a dense tissue called fibrous tissue, which makes it difficult to distinguish the cancerous tumor with the dense tissue. So my objective was to develop a technique to detect breast cancer through saliva, measuring the celiac acid levels. So why are we using celiac acid? Celiac acid belongs to a family of about 43 different acids. However, the one found in our body would be N-acetylneuramic acid, and that's pretty much found in all our fluids from blood plasma, sweat, urine, and saliva, where the celiac acid is the highest. This also regulates our immunity, and it works as a biomarker for inflammation. According to past research, it has been seen that when cancer is present, celiac acid tends to increase. And then I was working with the Raman spectroscopy this summer. A benefit of using this is that we can use very, very small concentrations, and this would help by picking up the vibrations of the molecules. So how does the Raman work? The Raman shoots a laser to the molecule, which in this case would be the celiac acid, producing the Raman scattering. However, I am using a technique called surface enhanced Raman spectroscopy, SERS, and the only difference would be that we would add nanowires. And once the laser shoots out, it hits the rough metal, which produces a greater intensity called the Raman SERS. And for these nanowires, I used silver. The change of color indicates the nanowires being formed. Once the nanowire cooled down, I was able to go ahead and purify it using ethanol and acetone, and then I centrifuged it, filtered it to remove any small particles, and then I prepared the substrates using a 2-to-1 ratio to celiac acid to 1 nanowires. And then I was able to take these images using the SEM, or the SEM, at different magnifications. The top one allows me to take the diameter, which ranged from 80 to 90 nanometers, and then the bottom one allowed me to measure the length, which ranged about 3 to 4 micrometers. The top right corner would be the UV of the nanowires. That indicates that it is homogeneous, which is then later confirmed by the capture below it using the Raman. And then this one right here would be the celiac acid spectrum using the Raman. It ranges from 0 to 6,500. And then once I added the nanowires, it ranged from 0 to 20,000. So almost 3 times of just the celiac acid being alone. And then these would be the different concentrations. A shows the one that I showed in the previous slide, so it's from 0 to 20,000, and comparing that one to B, which is a smaller concentration, it's 0 to 18,000, which is not much of a difference. But once you compare to F, which is, I believe, 1 times 10 to the negative 6, it is 0 to 3,000, and then 20,000 to 3,000 is a huge difference. In conclusion, my results show that once nanowires are added, Raman signal does increase, confirming the Sayre's effect. And for future work, I would continue synthesizing different nanostructures and different metal material, and then also the experimental investigation, which would be using different saliva. And that's it. Yeah. So that would definitely be, so the question was if we know the baseline for someone who doesn't have cancer, correct, using the saliva. So that would be the experimental investigation, where I would test people who don't have breast cancer or don't have history of having breast cancer, and those who do have breast cancer to kind of see where it falls under. Okay, so the question was there a reason why I used silver? No, not really. Definitely in the future, I do want to work with different materials like copper or gold, but this was just testing silver.
Any other questions? All right, well, great job. Let's give them
my name is Elisa, and I'm an electrical engineer from Rose-Hulman Institute of Technology. And this summer, I worked on the project You Will Rue the Day, developing area selective processes to enable Roux-based interconnect at the 2 nanometer mode and beyond. So first, a little bit of the theory and background. So as photolithography is reaching its size limits, we need a new way to create that selectivity down at the 10 nanometer node and beyond. I mean, they were talking about, the school bus sized machines earlier yesterday that they use to try and get that precision. And we're really reaching those limits. So how else can we do it? What's another creative way to look at it? And so that's where my PI and mentors' work come in. So for those of you who don't know what atomic layer deposition, ALD, is, it is a machine that works in half reactions. And you have an A cycle and a B cycle. So first you introduce the precursor, and then it'll combine with the substrate, and then it'll create a single atomic layer, like 1 atom thick. And then you add the co-reactant, and then that'll combine with the precursor, as shown in the area over there. And so what my PI does to gain that selectivity is he, instead of doing an AB cycle, he does an ABC cycle, where first he introduces a coabsorbate. And the coabsorbate would interact with the surface that you don't want anything on. And it'll block that surface and keep the precursor and co-reactant from getting onto that surface. And then you can take it off at the end, and you get that selectivity a different way. And so that's kind of one thing that we're working on. And another thing is copper is what we typically use for wires on the nanoscale, but copper doesn't have very good resistivity elements to it as you get down to smaller and smaller dimensions. So we're looking in the future to replace copper with ruthenium at the smaller scale. So my project was kind of two things. Number one, like how do we lay down ruthenium onto a wafer? And number two, is the machine that my mentor is working on, is that going to be able to give us that selectivity, and like which co-absorbents would we use, which precursors would we use, and so on. So yeah, my project, I created, well, the goal was to create line and space patterns of different sizes on 4-inch silicon wafers using a liftoff process, and then put those line and space patterns through my mentor's machine to see if we could get that selectivity. And so, I mean, I guess everyone's been through the liftoff process here, most people have. And so the way I did it is first we layered the dielectrics on a silicon wafer. So we had two different dielectrics, SiO2 and alumina. And then spin on in-loft resist, create the mask, which is what you see up there. That's the mask pattern, the GDS file of the different line and space patterns, and then develop it and use the evaporator to deposit use the evaporator to deposit ruthenium onto the two different dielectrics with the patterns and stuff. Yeah. So the results, the mask came out very clean, but the pattern did not. Most likely due to the fact that the silicon wafer was not clean enough. There were like giant holes in the like 3 nanometer and the 1 nanometer line and space patterns. And like as you can see here, I used the AFM, atomic force or microscopy, to measure like the line and space patterns, and that's the 10 micrometer, and you can see like the difference in roughness, and it was not nearly as good. And so when I talked to my mentor as well, he said well, they're still in the process of getting a selectivity using the co-reactant. So I was not able to test that either, but I made the patterns. So yeah, and there are my acknowledgements. Any questions? Go ahead. That is an excellent question. I would love to give you an answer, but I don't actually know. Yeah, sorry. And I don't want to give you wrong information. So. Any other questions? Go for it.
Sorry, it's probably a really basic question, but why ruthenium as opposed to, you know, the rest of the periodic table? Do you know why ruthenium was chosen in the first place?
No, I don't. All I know. What? Oh, so Melanie asked why I used ruthenium. So I know that ruthenium has good properties down on the nanoscale, and it's better than copper, but I don't know if they've tested like a bunch of other materials and ruthenium was the best. That would be my guess as to why.
Any other questions? All right. Thank you very much.
Hello, does this work? Okay, yeah. Hello, my name is Michael Breger. I'm a third-year physics student at Caltech, and I worked this summer with the Capasso group and Dr. Paul Chevalier on designing a new broadband output coupler for optimal terahertz laser performance. So what exactly is terahertz lasing, and why is this important? Well, terahertz technology, so as you can see there in the first image, is actually very important. So you can find a lot of terahertz radiations in different systems, such as in molecular vibrations, protein interactions, and resonance of electrons in semiconductors. And generating terahertz radiation has been an important but difficult problem in physics for several decades. Recently, the Capasso group at Harvard developed this quantum cascade laser pumped molecular laser QPML design, which allows for tunability of terahertz radiation using a tunable quantum cascade laser source. So you can see here on the bottom, this is essentially the Q. Okay, maybe I'll take this with me. This is the QPML design. So the idea is here you have this quantum cascade laser, which was developed by the Capasso group by Federico Capasso among others, which is essentially this mid-infrared tunable source that can be tuned, that has frequency tunability by changing the thickness of various layers in the active region. And this QCL pumps this molecular gas gain medium, exciting rotational vibrational transitions within this gas gain medium, and thereby generating terahertz radiation. So and this concept works extremely well, but there is one shortcoming that is the output coupler here. So in the laser cavity, you have two mirrors. You have a very reflective mirror on one side, and you have a partially reflective mirror or output coupler on the other. So the original design was this pinhole coupler, which although it worked very well, it had only an efficiency of 30% and had some trouble with diffraction, and it was not very uniform due to diffraction, and also could only select specific modes since it's kind of just this pinhole. So the project is involved to design a broadband output coupler so that you could run over several different terahertz frequencies. And so what I did was, let me move on. So I tried it for using Python's S4 module. I ran several simulations for different designs, different thicknesses, different sizes, and different substrates. So these are just three of the designs that I used. So this is called a capacitive mesh. So I tried each of these three designs for different thicknesses, different substrate materials, and what I was simulating was the reflection and transmission, but I also had to simulate the efficiency, because without the so here is this is the efficiency at a coupling value. So it's kind of given by this non-trivial equation here, where T is the transmission, R is the reflection. And the reason I had to also measure the efficiency and the losses. So yes. Okay, sorry. I just wanted to show for everybody. Okay. Yes, sorry about that. So I ran simulations for the thickness and for the reflection and transmission for each of these designs. And I ended up choosing the circular design because it had nice regions of high reflection and low transmission. So high reflection of around 90% and low transmission of around 10%, which is what you want for a laser. So that there can be amplification of the signal within the cavity due to stimulated emission. So here's just an example. So this is how the circular mesh worked. So for this one here on the left. This is how the circular mesh performed, and you can see very nicely there is this region here of high reflection and low transmission. So this is essentially what you want from the output coupler to behave, just to be on a certain frequency range. So then I tried for different substrate materials. So I tried with silicon, quartz, and some hypothetical material with n equals 3, so n being the index of refraction. So the top one here, the top one is the reflection, transmission, eta coupling, i.e. efficiency and losses of quartz, and then of the hypothetical material. And I found that it actually nicely scales with, so you can see very nicely there is this region of high reflection and low transmission, but also varying the optical index didn't seem to change the structure all that much. It just sort of seemed to scale the frequencies. So what I saw was that for higher indices of refraction, the region stayed more or less of the same shape, but it moved slightly lower in frequencies, and it also shrunk a little bit. So the region of high reflection, low transmission was smaller and occurred for lower frequencies. And then, so I also varied different substrate thicknesses. So the substrate material was also varied. So this is just an example for quartz. And you can see nicely here, so I varied from 10 microns to 500 microns. And you can nicely see here there are these sort of fringes, which makes sense because it behaves sort of, so you can imagine like you have this sort of like, you have your circular periodic array here, and then you have this nice so when the light comes in, it can bounce first off of the silicon or the quartz, so it can go up here, but then it can also internally reflect within the material itself. So it has these so you can so it essentially acts like a Fabry-Perot interferometer or etalon, so reflecting off of each of the walls. So here you can see, so you get these kind of fringe effects. So it's a little bit clearer maybe on the bottom two, So you get this nice, so first the red curve is this baseline where you have just a semi-infinite quartz substrate, and the blue curve is where you have a quartz substrate of 399 microns, just as an example. And you can see that the 399 microns fits the baseline extremely well, but it has these sort of oscillations, just which goes to show that you have this sort of Fabry-Perot effect. So that's all more or less what the thickness showed. And so I also designed the output couplers. So using the GDSPY module in Python, I created these two GDSPY files for the circular periodic output array output couplers designs. So each of these squares here and all of them have different periodicity values. And I designed the circles so that they would be where the radius is the periodicity, so the spacing between the circles, times 0.35. So, and these two are just two intermediate steps of the photolithography process. Okay, so the conclusions, I might have blown a little bit fast there, but so what I found was that the circular design was actually the best because it had this nice large region of high reflection and low transmission, and also high efficiency and low losses, and avoided diffraction by keeping ng over lambda is less than 1. So this is just an image of after the fabrication. So what I found from this region was that the nice region of high reflection and low transmission, and also high efficiencies and low losses, occurred for R over G equals, so where G is the periodicity of the spacing of the circles, equals 0.35, and it gave this it had a nice frequency region from N times G over lambda equal to 0.8. So the output coupler should be designed with those parameters so it could work in that frequency region. And so in the wavelength region, lambda equals N times G over 0.8. So, and this output coupler design had a maximum efficiency of around 60%, which makes it an attractive alternative to the pinhole coupler, which only had around 30%. So that's, and it has, yeah, so. Any questions? Yes? Yeah, so originally, so if I can go back a little. So originally we were thinking, so this is actually done from so this sort of capacitive mesh idea was sort of an old one used for like old types of lasers. So not the quantum cascade laser tunable ones, rather it was like a CO2 laser. So originally we had thought that, oh yeah, maybe we should try to use different size circles. Maybe we should have like 4 unit cells and just like try different radii. But that sort of didn't seem to go anywhere, just because like it had to. We didn't know at the time that it had to have like a 0.35 ratio. So if you had different radii, it just sort of the light more or less just went through. So there wasn't really much reflection at all. Oh. Yeah.
But they did very complicated mathematics differential equations and found that actually if they varied the surface and they varied that shape on a smaller level, they could get less refraction within the main.
Okay, no, I mean that could certainly be a way to try to extend this. So yeah, the program that I was using for it kind of took a while just to do the circles. So was like 4 hours or 5 hours or something each. So so definitely like one way to continue would probably be to maybe try to do other ones. Although this one worked kind of well enough, so I'm not sure. Maybe later on a good extension of that would be to try some different type of structure. The reason this structure was done was because you get sort of like this electric field happening between the two, like between each of them. So for example, you can imagine like you have a, if I go a little bit forward. So yeah, so here you can imagine like you have this, like these circles, you have these circles there. So in between each of these circles, you can kind of, you get this sort of electric field between the two. So this kind of aids with the reflection. So maybe in a regular structure might make it easier for that to happen. I'm not really sure. You'd probably have to go through the math and stuff like that. But so definitely that could be something that I could investigate for sure. But this seemed to work decently enough. Any other questions?
Hi everyone, I'm Natalie Ogden and I'm studying chemical engineering at Rowan University, and my project is on the characterization and optimization of the inkjet printing process of conducting silver structures. So a quick introduction into my project is that direct write inkjet printing is a technique that's used for the fabrication of wearables, solar cells, touch sensors, and the microassembly of microrobots. Some advantages of inkjet printing are that it is a low cost of manufacturing, it has a high flexibility, and a quick turnaround. The motivation behind my project is that it would be an enhancement of the Nexus system additive manufacturing capabilities, and it would help with the fabrication of touch sensors or flexible electronics using this Nexus system. So the Nexus system is a multi-robot system and an instrument for flexible multi-scale manufacturing. Some of its advantages are that you can design and manufacture these custom printed electronics, and is also being transitioned from using the clean room to print these sensors to this Nexus platform. So you can perform all of these capabilities in one location. And the Nexus system also ensures proper control of your manufacturing process and gives you the ability to automate fabrication. So my goals for this summer were to characterize and optimize the conducting inks printing process for a glass substrate. I also wanted to determine its optimal deposition conditions and generate enough knowledge to integrate this into the automated manufacturing process. So here's my experimental setup. I was using the Nordson EFD PicoPulse inkjet printer, and that gives you the ability to control your deposition of single droplets. And some of the process parameters I was looking into and altering were air pressure, deposition height, and stroke. And this is a schematic of how my printer works. So ink flows through the fluid body into this cartridge, and in that cartridge there's a piston which is raised up, and then when it's released, it deposits the droplet. And then the materials I used were the SPI silver conductive paint, which is a colloidal solution of 5 to 10 micron silver pellets, and the Novacentric silver nanoparticle ink, which has nanoparticle sizes ranging from 30 to 50 nanometers, and the substrate I used was glass. For my data analysis and design of experiment, I used a fractional DOE and a signal-to-noise ratio, which specifies the smaller the better, meaning that you want a smaller droplet diameter. And these were my initial testing results using the SPI high-purity silver paint. And these were unsuccessful because it gave me a limited control of my printing process, deposited very irregular shapes, and clogged my printer head nozzle very often. So next I used the Novacentric silver nanoparticle ink, and these were successful. These top two pictures show some of my good quality printed structures, and the bottoms are some of my poor quality ones because it gave lots of satellites and very irregular shapes. But for my experimental setup, I used a Taguchi experimental design and had it set at 3 different process parameters and changed it at 3 different levels. And these are just some of my results, but I found the smallest droplet diameter to be 493 microns and the largest to be about 788 microns. And then here's some response tables using that data. So table 1 shows mean diameter values for all the given parameters, and table 2 gives you the signal-to-noise ratio values that I calculated using that equation from the previous slides. And then these graphs show the mean diameter versus the signal-to-noise ratio. And the purpose of these graphs is that you want the lines to be reciprocal of each other. But I noticed here in the stroke graph that they aren't perfectly reciprocal, so I think that means that there's some outside noise affecting my results. And that would be the reason why at 65% stroke, the mean diameter is a lot lower than 55 and 75%. And then these are some contour graphs showing some trends of the mean diameter depending on stroke pressure and deposition height. Some of the trends I noticed was that a decrease in pressure usually led to a decrease in droplet diameter. And also at deposition heights of 1 and 5 millimeters, I found that those typically led to a smaller droplet diameter as well. And then to further my Taguchi DOE, I wanted to test at different parameters because I thought I could get better results. So I found that printing at a 1 and 3 millimeters deposition height gave me some of my better results. So I also decided to print at 2 millimeters. And this is just showing one of the better results I got and all of the different tests I did. But for that result, I found had an average diameter of 497 microns. So the next part of my project, I wanted to print continuous lines. So after many trials, I found the best parameters were at 20 psi, 55% stroke, and a 1 millimeter deposition height. But another part of printing my continuous line is that my printer actually doesn't move, so I had to move the stage. So I decided to keep that at a constant speed of 15 millimeters per second. And then another parameter to change to print the continuous lines is the cycle time or the frequency of the depositions. So I can see in these pictures it shows a transition from droplets to an actual continuous line. But at 50 milliseconds, you can still see the droplets, whereas in 15 milliseconds, an actual line starts to form. And then another parameter to consider with these is that the step size, which is the distance between the droplets on the substrate, and as you can see, that also decreases as the line actually forms. So next, I wanted to cure my lines to test the resistance and make sure that these lines are actually conductive. So I cured them at different temperatures and times and found that temperature definitely has an effect on the resistance, but also the cure times has an effect on the variability of my results. But I found that curing at 200 degrees for 20 minutes had my least amount of resistance and least amount of variability. And then just to give a summary of my project, so I found that the SPI conducting silver paint was not a fitting material for inkjet printing. My printing tests with the Novacentric silver nanoparticle ink were successful. I evaluated the deposition quality with respect to diameter size, amount of satellites, and the regularity of droplet shape. And these are some of my better quality prints. And as you can see, the parameters were between a 1 and 2 millimeter deposition height and air pressure between 20 and 40 psi. And all three of these were at a 55% stroke. My continuous lines were successfully printed based off of these results, but I was looking for the smallest width, least amount of satellites, and straight, smooth edges with the lines. And then finally, I found that curing my lines at 200 degrees for 20 minutes had my best results. And I calculated the volume resistivity value and compared that to the expected resistivity value that the Novacentric ink provided me, and they were within the same magnitude and pretty similar, so that shows some pretty promising results with my project. But here are my acknowledgements. Thank you for listening, and are there any questions?
Do you have any questions for Natalie?
Yes. Mm-hmm. So the question was, with my continuous line, there is some debris, and do I think that will affect the performance? I don't think that will, because there's such a small amount compared to, if you remember the picture with my bad quality results, there was just so much splatter that you couldn't even actually see an actual droplet shape. Yeah, I think these are some of my really good results, that there was really a limited amount of splatter. Yes. Yeah, so that was part of my Taguchi DOE, so I think I forgot to mention this, but using these tables, I found the difference between the, so for table 1, I found the difference between the min and max of the mean diameters, and the other one, the same thing for the signal-to-noise ratios, but I found that pressure had the largest effect, and then also deposition height had a pretty large effect on the results. Yeah.
My question was also actually about the debris surrounding but maybe a follow-up question on that. I wonder, maybe there's a cleaning step, right, in order to get rid of that debris that is standard after deposition. I don't know.
Yeah, I think that could be something that they do further research with. I know the next step would be to print on like an actual flexible substrate, but based off this, I think, yeah, they would probably have to look into that as well.
Okay, let's give Natalie another round of applause.
Button up.
So where's this?
Okay, so this goes right here. Okay, next up we have Christopher Luck from KY Multiscale, and he'll be speaking on study of monolayer collapse of droplets in virtual wells and on microfabricated pedestals.
So my name is Christopher Luck, and this summer my mentor was Dr. Stuart Williams, and my research was on the study of monolayer collapse of droplets in virtual wells and on microfabricated pedestals. So right off the bat, I want to give you a brief or simple visual of what the monolayer on a droplet looks like. So there's the orange dots are these colloids, and as the droplet evaporates, they get pushed to the outside of the droplet and form a monolayer. And as the droplet gets smaller and smaller, the monolayer eventually can't get any closer together, and so it buckles and collapses in. Now, past research has focused on after this droplet evaporates, what's left behind is these web-like patterns. And so past research, they took a flat glass slide and put droplets of various brands of American bourbon whiskey, and did a lot of trying to get different samples of what these patterns look like. But there's limitations to that, as we could only get patterns out of American bourbon whiskey, and we want to do more than that. And so my research focused on is we want a platform to pin these droplets in place so we can test lower contact angle liquids, such as ethanol. As you see, this ethanol, this is a droplet of ethanol, and it does not want to stay in a droplet, it just wants to spread out on glass. So how do we pin these droplets in place? So one method of doing so is we have these Teflon wells, which these Teflon wells are basically, it's a a Teflon sticker with holes punched out into it, 2 millimeter diameter circles, and stuck on a glass slide. The problem with this is, we look up close, the edges around these circles are not very nice at all. They're very rough. But we wanted to make pedestals. As pedestals, like on a flat glass slide, there's not walls around the droplet being formed. On pedestals, that wouldn't be a factor either. So how do we make these pedestals? Well, ultimately, we made these pedestals out of SU8 2100. And there's, as you've probably heard from other presentations today and yesterday, that have also used SU8, there are many benefits to using SU8. There's a wide range of available thicknesses. We wanted these pedestals to be at least 100 microns tall to be able to hold these droplets based on past research done on pedestals. SU8 is very durable after it's hard baked, easy to clean, and it's also semi-transparent, which is ideal if we want to look at the patterns formed on top of these pedestals. And so it's just your basic photolithography process. We spin the SU8 on the wafer. SU8 is a negative photoresist, so what is exposed to UV light is what stays. And so that's the mask we use to expose the wafer to UV light. Then we develop it, and so you know the rest of the process there. And so this was our result. We ended up with very, very nice edges on these shapes. And the pedestals ended up being around 120 microns tall. But, so we had the pedestals made, and they look nice. Can they actually hold the low contact angle liquids that we need in the hole? Because that's the whole reason we made them. And so there's 2 extreme liquids that me and my mentor decided to test on these platforms, and that is water and ethanol, and we used 95% ethanol. As you saw earlier, the ethanol is one to spread out, and the water, while it's not impossible to get nice circles, they're not all like that. Like the ones in the beginning where you saw those web patterns on the cover, those are a selected few. There's a lot of variation in the shape of how these droplets. As we can see with the Teflon on the water, it's a nice droplet because it's restricted to an area. The ethanol, however, and the Teflon wells wanted to leak out of the well. I could not get the ethanol to stay in. It wanted to leak out onto the surface of the Teflon surrounding the well. For the pedestals, we can see that the water droplet looks relatively nice. It didn't go to the edges. So if we were testing a liquid and it didn't do this, and we wanted good results, we would either have to treat that surface with like plasma to make the surface more hydrophilic, or simply make smaller pedestals so it fills up. But for this is a good result. And the ethanol, or it's an expected result, as I mentioned. And for the ethanol, it filled the surface area, and the 95% ethanol stayed on the pedestal and filled it up, as we would expect. So what the takeaway from this slide is only the SU8 pedestals were able to pin the 2 microliter droplet of 95% ethanol. And so next, so we can visually see an improvement of the SU8 pedestals over the Teflon wells, but to actually know if the patterns, we want to see if the patterns formed on these 2 platforms, if there's an improvement in the SU8 patterns, if they're more consistent. And so visually just looking at these droplet patterns, there's not really much to take away. Like you can see some similarities, but in order to see if they're actually more consistent, we have to run it through an image analysis. So I took 10 images from the Teflon wells and 10 images from the SU8. And this uses a whiskey bourbon that was used in past research that we have already established. And so we go through an image analysis. Basically, the image is cropped, converted to grayscale. Then the images has to meet, the pixels have to meet a threshold to get into the binary. Then that image is blurred, and so we have an average intensity of all the pixels. Then it's divided into radial bins. And so the results from this is each images has one of these tables here, which shows a distribution of the pixels. And so all these rows here, because we're dealing with each image has about 4 million pixels in it, each horizontal row adds up to 100 pixels, with the more blacker pixels on the left, the whiter ones on the right. And so with each of these tables, for the Teflon and the SU8, we got we took the mean difference squared of each table, and that's what's represented right here. And so this gives us an idea of how much each image deviated from its mean image. And so, the larger numbers represent a larger deviation from the mean. And as we look at this table, we can see, we can conclude that the pedestal patterns are overall more consistent than the Teflon wells. And so as I showed, both the Teflon wells and the SU8 could successfully pin droplets, although with lower contact angles, the pedestals failed there. And the patterns formed on the pedestals were more consistent than the ones formed in the wells. And the impact of this is now we can use this platform to test a wider variety of liquids other than the just American bourbon whiskey. Now we can test a wider range of different liquids and volumes. I designed the photomask, yes, in the clean room made it.
I might have just missed this, but in terms of like the actual application of once you have these dissolved patterns that you see, what do you use that information for?
That's a great question. So he asked, what do we use these? We have these patterns and we see them. What are these patterns for? What does it mean? Well, there are other methods of studying and researching monolayer collapse. The problem is those methods can take like hours and hours to do. It's a longer process. With these pedestals, or with the droplets, a droplet takes around 20 minutes to evaporate. And we want to connect these droplet monolayers to how other ways monolayer collapse is studied. And so, but before we can do that, we have to test more than just American bourbon whiskey. We have to test a much wider range of liquids.
All right, thank you.
Okay. And okay. Yeah.
Okay. Next we have Saku Abe. He was visiting this summer from Japan, and he was studying at Georgia Tech Scenic. And the title of his talk is "The Stability of Titanium Oxide Hydrate in Cellulose-Based Film for Green Photonics."
Okay, thank you for introducing. My name is Yu Saku, so Waseda University graduate school student, and I'm joining in this program as an exchange program between Nanotechnology Platform Japan and the USA NNCI. So my research project title is this: so stability of titanium oxide hydrates in cellulose-based films for green photonics. So first, I'm talking about the background. Hybrid material has good advantages because it's a composite of the organic and inorganic materials, good advantages. So One, inorganic materials advantages like this, so high durability or good heat resisting property, and for example, glass or metal. And on the other hand, organic materials has a lightweight properties or high visible ray transmittance good property. So, for example, using for example polymer or wood, and hybrid materials both advantages composite materials. And especially, I focus on titanium and cellulose hybrid materials for making optical materials or optical thin film, for example. So titanium oxide has a unique optical property. So for example, using for photonic catalyst or etc. And on the other hand, cellulose is a natural material from wood, so good for the earth and good for ecology. So I try to composite these two materials, but I met some problems or some challenges. For example, mixing titanium oxide and cellulose at current processing condition is very difficult. Conventionally, as a cellulose, CMC carboxyl methyl cellulose is used for making this, but titanium and CMC hybrid solution is starting as soon getting cloudiness, so it is difficult to high transmittance optical thin film. So I'm talking about these research objectives. First, looking for good cellulose derivatives and good stabilizer to make a hybrid materials. And second is investigation of properties that affect the aggregation. And the last one is making hybrid thin film for photonic applications. So this is a method. It's two parts of the making method. First is making solution, and next step is making thin film. So in the making solution step, we mix titanium oxide, cellulose derivative, and stabilizer in water. And the making film steps, I use deep coating method for making thin film easily. So I'm going to talk about the results first. I discovered that the hydroxy cellulose HEC is appropriate for the making hybrid. So left picture is a titanium CMC, so getting cloudiness. But when I use HEC, you can get the very clear, so high transmittance solution. And by using this solution and by using deep coating method, I use a thin film. I made a thin film like this. So we can see that more clear or more high transmitter thin film you can make it by using titanium and HEC. And so yeah, so getting cloudiness, it's some materials getting crystallization. So I focus on the crystal size distribution. So CMC and titanium is peak is very bigger than titanium and hydroxy cellulose hybrids. So you can understand from this graph that the aggregation is hardly closed. And I measure the transmittance for making good high transmittance solution. And yeah, I can check that titanium and HEC solution is a high transmittance as more higher than a titanium and CMC solution. Oh, sorry. And I missed another problem. It is this: titanium oxide hybrids are not stabilized by HEC alone. So this is past study picture. Left is day 1 and titanium HEC, and right picture is day 54. So getting cloudiness, and in the film is we met same problem. So day 1 is very high transmitters, but day 11 is transmitters very lower, so not stabilized well. So I have to take a more stabilized this solution by using some method. So this is the data of the size distribution after the passage of time. Yeah, we can check that first day is good solution, so high transmittance and peak is low. But after 5 days, the peak is more bigger, so getting crystallization and getting cloudiness. So I used critic acid CA as a stabilizer to stabilize this solution. So yeah, I have to check the interaction between molecules determine solution stability and structures. So I use CA for stabilization of titanium and HEC solution. So before adding CA but if when you as a CA control surface energy between titanium or hydroxyethyl cellulose, so we can make a high transmittance and well-stabilized solution. So this is the result. So day 1 0 is no CA, and 2 is the gram per CA per gram titanium is 2 times. So we can check that about 2 grams CA per gram titanium, so it contains a high concentration of CA is getting well stabilized after day 5. And I measure the size distribution too, and so day 1 everything is well stabilized, so size distribution is very small. And day 5 is only CA contains about 1 or 2, so 2. So well stabilized solution is keep on stabilizing. So peak is very small, but yeah, for example, no CA solution is making happen crystallization, so peak is more bigger. So following slides is supporting information, so I talk about briefly. This is I measure the thin film surface information, and thin film surface is amorphous, I can discover. And this is the atomic force microscopy data. And so I can I compare before crystallization and after crystallization. And yeah, after crystallization, some changes occurred, and probably it's more harder or not, but I want to think more about this data. And this is the optical property of thin film. So we can, I measure the refractive index of titanium HEC thin film, and we can understand the high refractive index. So I expect that it is good for thin films, optical thin film application. And so this is the future works. Yeah, so I want to like this works, especially I'm interested in this. So yeah, refractive index is very important information for good making the optical thin film. So I want to, I want to keep on study about the refractive index information or getting more high refractive index thin film I make. So this is the conclusion. So I success at 3 points. First is finding good cellulose derivative to make a hybrid material. And second, investigating of the stabilizer effect by measuring size distribution of so crystal size distribution. And last one is making hybrid thin film for photonic applications. I can make it. So this is acknowledgement. So thank you for everyone, and thank you for your kind attention. This is the end of my presentation. Thank you. Thank you for your question. Yeah. Okay, let me check. Yeah, sorry, it's broken. Okay. Proper. Okay. Yeah. Yeah. It's a good question. Yeah. And to be honest, I can't discover completely, but yeah. I and my colleague discuss and CMC's molecule structure is but for stabilized and so making, for example, hydroxy bonding, high hydroxy bonding. So as soon making crystallization and cloudiness. But HEC is a different structure of the CMC, so we can prevent the hydroxy bonding, high bonding. So probably we can stabilize well by using HEC. Thank you for the question. Thank you. It's a pointer and it's a microphone.
Oh, thanks.
You're welcome.
Good job.
Okay, up next we have Frank Lynch from the MAMP site for this summer, and his title is Exploring the Centrifugal Force as a Control Mechanism for Metal-Assisted Chemical Etching.
So hello everyone, my name's Frank. I'm from the University of Scranton, and this summer I worked at the SING RU at the University of Pennsylvania. And so this summer my group was exploring this silicon etching technique called metal-assisted chemical etching. And in particular, what I'm going to present today is our exploration of trying to utilize the centrifugal force to control this etching technique. So silicon-based micro nanostructures have incredibly far-reaching applications. Just to list a few, we have our MEMS devices, black silicon, micro nanofluidic channels, resonators, and so on. And when we're fabricating these devices, particularly for commercial use, we're looking for etching techniques that are very reliable, precise, and consistent, thereby granting us higher yield in our devices and increasing our functionality. So we're really trying to achieve very specific etch profiles. So the etching technique that we're requiring must be able to give that to us very consistently. And it would also be nice if that comes at a very low cost. So that leads into the etching technique that we were exploring called metal-assisted chemical etching. And it's a promising wet etching technique that's been garnering some pretty considerable attention. And so how it works is that you deposit gold selectively on a silicon surface, and when you expose this sample to a etchant solution that's composed of an acid, in our case hydrofluoric acid, and an oxidant, in our case hydrogen peroxide, what happens is that the gold catalyzes an etching reaction only beneath the deposit of gold, thereby giving you this really nice anisotropic etching using a wet etching technique. And the reason it's so promising is because it's very simple and very low cost, unlike the more ubiquitously used etching techniques like reactive ion etching, which is most predominantly used to etch these devices. And also, it's very flexible and scalable, just because depending on how you deposit your gold, which you can do any way you want using standard litho practices, you can really achieve a whole wide array of etching profiles. And furthermore, it can even be used to etch these out-of-plane features like channels on the sidewalls of silicon trenches, which is very difficult or impossible with other techniques. So it has all these amazing benefits that we'd love to take advantage of, but the only problem is that it's difficult to control. And the reason is that as etching occurs, the gold catalyst is attracted to the underlying silicon by van der Waals forces, and as it's etching through the silicon, tiny discrepancies in these forces across the catalyst surface can lead it to tilt off course and lead to some really wild etch profiles like the ones you see on the right, which isn't really good if you want very precise and consistent etching. So a lot of research has recently been focusing on finding mechanisms of improving our control over this random catalyst motion. Some groups have been using an electric field, some have used a magnetic field to help guide the catalyst as it's etching in order to get some really nice etch profiles. And the mechanism that we explored was the centrifugal force. So what we did was we fabricated these tester chips with arrays of 1 micron gold dots. So we took our silicon wafer, we patterned it with we spun on our resist, we patterned it with arrays of holes, deposited gold evenly across the entire sample, lifted off the excess, and we're left with these chips with arrays of gold dots. And so we spun them in centrifuge vials full of our etchant solution, and we spun them at various different relative centrifugal forces to explore how this is affecting catalyst motion. So the goal was to use the centrifugal force to kind of make these catalysts stay moving in our preferred etching direction. And if we find that we're able to do that, what we could possibly do is, say we're etching in a centrifuge, we could tilt our chip through our etching at different points such that the centrifugal force acts at different angles relative to the chip surface, thereby moving the catalyst in different directions, giving us some really complex and interesting etch profiles that are impossible with other techniques. So that was the goal. And now we'll get into what actually happened. So on the left, we have our control trial. So 1G on a lab bench. And we're able to etch about 8 microns deep in 20 minutes. So about 400 nanometers a minute, pretty aggressive etching. But as you can see, it's kind of wild. Some things are kind of moving sideways. Some are going into the page, and you can't really see where they're going. But once we put them into our centrifuge, something really crazy happened, because regardless of the relative centrifugal force, so no matter the g-force, no matter the angle at which the centrifugal force is acting, and no matter the duration of the etch, etching was entirely prohibited under centrifugation, which was really, really strange, and we didn't know what to make of it at the time. So the first hypothesis we came up with was that it could be that the centrifugal force is so high that it's putting excessive pressure on the gold catalyst, such that it's reducing the area between the catalyst and the silicon surface that's required for mass transport to occur. Because in MACE, we need 3 things to happen. We need the oxidation of the gold by the hydrogen peroxide. We need the charge transport of the hole into the silicon, oxidizing the silicon. And then we need HF to access that interface between the catalyst and the silicon to etch away that oxidized silicon. So it could be that this G-force is just so high that it's pressing the catalyst up against the silicon, not allowing this mass transport to take place. And there's a really elegant way that we can test this, and unfortunately we did not have time to. So by altering our methods of gold evaporation onto our silicon surface, we can actually achieve a nanoporous catalyst morphology, whereby we have these tiny nanochannels running through our catalyst directly to the silicon surface, thereby alleviating this suspected lack of mass transport that we thought was taking place. However, what's calling this into question is that even on the perimeters of our gold dots here, we're not even seeing any etching there, where HF has total access. So in the end, we're kind of scratching our heads thinking of other ways of what's happening under centrifugation such that our etching is prohibited. Because at 1G on a lab bench, we're having really aggressive etching, but once you put it up to maybe 12G, everything is prohibited. So in the end, we're looking to do a bunch more tests to see what exactly is going on. But we thought we'll come out with a pretty simple, straightforward solution, but we ended up with more questions than we started with. But again, any research into this etching technique is beneficial towards promoting its more widespread utilization and taking advantage of its many benefits. So I'd like to acknowledge a few people. So on the picture on the right, that's my PI in the back, Dr. Pat Watson, and my mentor is in the front left, Tori Dong. And they were great and helpful throughout this entire process. And I'd also like to thank the Singh Center RU for providing me this opportunity, and to the Singh Center staff for all their training and help throughout this process. And of course, the NSF for funding. So thank you.
Do we have any questions for Frank?
Yes. What's that? Gas-based? Gas-based? Oh, it was in solution. So it's a wet etching technique. Mm-hmm. Yes, I see what you're saying. We did not attempt that, but at the same time, when we put these chips inside these centrifuge vials, there's definitely contact being made. And so the fact that it's not even etching a tiny bit calls into question what's happening there. Does that answer your question? Okay. Thank you. Yes?
So you have the layer of silicon, then you have a layer of the photoresist, and you put the gold on top of the photoresist, correct?
So we pattern our resist with holes. So it's like a stencil almost. So once we deposit our gold, some of it gets caught on top of the resist, and others allowed through to deposit onto the surface. So once we lift off, we have this gold directly on the silicon. Mm-hmm. Thank you.
Anyone else?
Yes?
Do you see that possibly used with other etching techniques?
Yeah, that's a great question. So he was asking if MACE could be used in coordination with other etching techniques. And actually, my main project at the start of this summer was trying to etch on the sidewalls of silicon. And so what we did was we actually used deep reactive ion etching to create these trenches and then use MACE for its ability to etch out-of-plane features to deposit gold at an angle onto the sidewalls and use those to go outwards. So yes, it can be used in coordination. Yeah, that's a good point. Thank you.
All right, let's give Frank another round of applause.
It's the video next. It's the video next. What should I do with the mic? Oh. Thank you.
Do you just stick this in your pocket?
Yeah, just.
All right, cool, thank you.
Our last live speaker for today is Gavin Fowler, and he studied at KY Multiscale, and he'll be presenting on optimization of ultrasound fields and acoustic fluidic channels for microbubble enhanced molecular delivery to cells.
All right, thank you. Okay, my name is Gavin Fowler, she said, and this summer I've worked here at the University of Louisville with Professor Jonathan Kopacek. My project has been the optimization of ultrasound fields and acoustic fluidic channels for microbubble enhanced molecular delivery to cells. So basically what I've been doing this summer is I've been working with a microfluidic device. And in this device we're putting a mixture of microbubbles, nutrients, and T cells where they're exposed to ultrasound technology. The combination of ultrasound and microfluidics is called acoustofluidics. And inside this acoustofluidic system is an ultrasound transducer. That is what transmits the ultrasound signal. Now, when going through our device, the nutrients start and they travel through our channels. And it is there where they are introduced to the ultrasound signal. And that happens around this area right here. So when they're introduced to ultrasound, this causes the microbubbles to pop, which pokes little tiny holes in the T cells, which allows for the delivery of the nutrients to the T cells, basically superpowering them to fight diseases such as leukemia and other blood-based diseases. So previous studies have shown that the more microbubbles that are popped in our experiment, the more drugs that will be delivered to the cells. And the way we pop microbubbles is having a certain ultrasound pressure on the bubbles. So if we increase the ultrasound pressure, more bubbles will be popped, and that will lead to more drug delivery. So my goals for this summer were to test and map out the ultrasound fields for different materials, and then to use these graphs to create to create new 3D printed designs based on them, and then to use acoustic attenuation to test the efficiency of them, and finally to test and to see whether or not ultrasound reflection was important. So some of the methods that I used, there were three main ones: mapping out the ultrasound field, acoustic attenuation testing, and ultrasound reflection testing. First one we're going to look at is how I mapped out the ultrasound field. So to do this, we had a 0.2 millimeter hydrophone needle, and that's this guy right here, and he was the receiver. And then our ultrasound transducer, again, the transmitter, is located right here, directly across. These measurements were taken in two different materials, aluminum and water, at a tenth of an inch, anywhere from 0 to 5.5 inches away from the transducer. Then we converted this to a millimeter distance. And through this, we were able to find the minimum and maximum ultrasound pressure areas for each material. Moving on to the acoustic attenuation testing. So this is basically how we test the efficiency of our design. This has a number scale, with 0 being the best and any high number around 6, 5 or 6 area being the worst. And so the way the system works, this is it right here. We have two ultrasound transducers. One is transmitting the ultrasound, and one is receiving the ultrasound signal. And so what we do is we stick a cuvette in between the two transducers, and this has a certain amount of microbubbles inside of it. And so we stick it in there, and the ultrasound travels through, but some of it doesn't get all the way through because it's blocked by the microbubbles and reflects back off of it. So different amounts of microbubbles reflect different amounts of sound. We're able to get a quantitative measure of this, hence the 0 to 6 measurements. So finally, we're going to look at the ultrasound reflection testing. So the way this works, well, actually, first we're going to go over how ultrasound reflection works. So it is like an echo. So say you yell in a canyon, you're going to hear your voice bounce back to you. So this is basically the same way for ultrasound reflection. So if we look right here, this is the ultrasound reflection at a specific spot. And so that initial big bar right there, that's like your initial yell. And the smaller bars after that are your voice that you hear coming back to you. So the way we tested ultrasound reflection is we submerged our system underwater. So the ultrasound waves would travel straight through our device and not reflect back into it. We did this at 120 millimeters, at 0 millimeters, and then we brought it above the water so that it would reflect off the air on the other side and come back into the device. So we're going to look next at my results and conclusions. So of my 4 goals that I set for the summer, all 4 were successfully completed. So we're going to look at the first goal first. So this was to map out the ultrasound fields. This was for aluminum and water, and we got graphs, good graphs for both of them. As you can see here on the left is our graph for aluminum with the maximum ultrasound pressure at about 40 millimeters away. And then on the far right there is the field in water, and that maximum pressure area is about 120 millimeters away. Now, we're going to move on here and look at a combined graph of both of them. So while both were able to be graphed successfully, the field in aluminum was much better overall, being almost 80 millimeters closer to the ultrasound transducer located here at distance 0, and being almost 35% higher in ultrasound pressure. So next was my second goal, which was to create graphs based on both of these designs. Or not create graphs, create designs based off these graphs. And so this is my design based off the graph of water. And it's designed this way because of the graph. And so the maximum pressure is about 120 millimeters away. And our ultrasound transducer is located there at 0. And so our microfluidic channels are right in this area, lining up directly with our maximum ultrasound pressure. And then the next design is our design for aluminum. This was basically designed to sandwich an aluminum block in between the transducer and the microfluidic channels. So it looks somewhat like this. So the aluminum block would be right there, and because the aluminum block, its maximum pressure field was about 40 millimeters away, but that is just on the other side of the aluminum block. And so that's where we put our microfluidic channels. And then, so this is basically the efficiency of how these systems did. So we had both of these systems compared to a control test. And so this was about 5.3, and that range was really bad. If you can remember from earlier, our attenuation measurements was from 0 to 6, and so about a 5 is really bad. So that was the control, no ultrasound whatsoever. And then when compared to the system in water, it was about 3.2 or 2.7 in that range. So still not the best, but when we compare it to the system in aluminum, that was around 0.8, and that was a fantastic measurement because that ended up being our best design by far. So moving on to our final goal, which was to assess whether or not ultrasound reflection was important. So to do this, we had our 3 different measurements, 2 below water and 1 above water. So this was again compared to our control measurement, and these first 2 lines you're going to see following this control measurement right here, those are our measurements done below water with no ultrasound reflection. And this ended up being about the same as the control, meaning little to no bubbles were popped in the experiment. So this was not very good. But then as soon as we brought it above the water, it got a value of about 3.7 with just air reflecting the bubble or reflecting the ultrasound back into the system, which was very promising because it showed that indeed ultrasound reflection was needed for our system. So in the future, this project may advance acoustic technologies to help improve cancer treatments. And I'd like to thank Impact NG REU as well as the University of Louisville for this opportunity. And thank you guys for listening. Are there any questions? Yes? Exactly. Yes, sir. So he asked if it was for cell immunotherapy treatments, and that is exactly right.
All right, let's give him another round of applause.
I'm Melanie Claire Mallison. I am the coordinator for the Cornell Nanoscale Science and Technology Facility REU program. And we are starting very late, but I'm still going to give you each your 12 minutes. And we'll just see what happens. I have a couple of notes, though. When you get to 1 minute left on your time, I'm going to stand up, and that's your signal to wrap it up. Is the audience mic'd?
Like the audience in here?
Yeah, so if they ask questions, they should probably repeat the question, right? So that, yes, okay, so repeat the question, because otherwise someone says, did you use thus and such in your process? And you say, yes, and no one knows what you're saying yes about. So for the video, be sure to repeat the question. And also, when you're speaking, well, you're going to have to, there's no laptop, so you do what you do. But don't wander too much. Okay? So, with that, oh, also, just so that you know, I'm a theater major, so I'm just going to say your name and have you come up, and you can introduce what you're talking about and where you're from and all of that sort of stuff, because I'll just murder it if I try to do it. Okay? Okay. So, Chelsea, come on up.
Like right here?
Okay. And even though you're mic'd?
Gotcha.
Okay. Let's go. Let's start. Yay!
Greetings, I'm Chelsea Latham, a second-year mechanical engineering student at Florida A&M University, and this summer I had the pleasure of working at the University of Louisville with Dr. Kate and Kavish Udan on the development and characterization of 3D printable conductive polymer composites for application in tactile sensors. So a little bit of background on my research is that tactile sensors have gained a lot of attention and popularity recently due to their various applications, ranging all the way from health monitoring sensors to robotics. General criteria for these sensors is that they are strong, they are flexible, and able to undergo high strain with little to no deformation. Now, these do come with challenge because these sensors utilize long production times, expensive manufacturing technologies, and are complex in nature. So the need we want for this is that we want an inexpensive way to create sensors and for them to be adaptable as well. So our approach to this problem is 3D printed tactile sensors with a conductive polymer composite. So this summer I've been tasked with developing and characterizing this conductive polymer composite. So for ours, we have the addition of graphene in various concentrations so we understand the effect that it will have on us. So this alternative is also anticipated to reduce production times and costs. So some goals I had for this summer was to develop a sensing material that could be 3D printed, to print these sensing patterns, understand the effect graphene has on the properties, and eventually develop a fully 3D printed sensor. First, we began with filament development. The two materials we used were a polymer matrix in pellet form as well as graphene powder in various concentrations. To mix this, we used torsional compounding with the IntelliTorque Broadbender high shear mixture at about 150 degrees Celsius with a torque of 50 revolutions per minute. After this was mixed, we were able to chop it into pellet form conducive for filament extrusion. It was extruded at the elevated temperature of 150 degrees Celsius through a die of 1.75 millimeters. Next, we began filament characterization, starting with physical properties. We measured the density and took SEM images to note the surface roughness. Based on the data we collected, it was noted that with the increase in graphene content, there was an increase in density as well as surface roughness. Next, we began electrical properties, starting with a resistivity. We used the 4-point resistance measurement, and as we prepared the filaments, we cut them into about 1.7 millimeters and measured the diameter and took the average of that. Once we measured this, we noted that there was a decrease in the resistivity with the addition of graphene, meaning that with the addition of graphene, there was an increase in conductivity. Next, we began printing. We used the Pulse XE 3D printer to print sensing patterns on Kapton sheet and an off-the-shelf substrate. The prints were all about 225 degrees Celsius for the nozzle, 55 degrees Celsius for the bed temperature at speeds between 10 and 20 millimeters per second. This was relatively the same for all of the filament concentrations. Continuing to the electrical properties, we measured gauge factor with the test condition of 3-point bending. The gauge factor we observed was about 20. To put this in some perspective, metallic strain gauges usually measure at only about 2, so this is 10 times the average, which was a great gauge factor we observed. And the measurements we took were from the 6 weight % 3D printed sensor. And the last characterization was the thermal property. We did a TGA test for this. It was noted that after about 300 degrees Celsius, decomposition began. This also was used to verify the graphene content we put in each of the filaments because the polymers burn higher at a lower temperature than the graphene does. So in conclusion, we were able to meet our goals of developing a sensing material that can be 3D printed. We were able to print those sensing patterns, and we gained insight into the effect graphene has on all of these filaments we created. This essentially gave us a better understanding of which concentration would be ideal to apply to a fully 3D printed sensor. So in the future, we are planning to do more testing by getting the gauge factor measurements for the 2 and 4 weight %, also a DMA analysis of the composites, and eventually develop a fully 3D printed sensor. To finish up, I'd just like to acknowledge everybody listed above. Without this wouldn't be possible, and thank you to all of them. Are there any questions?
Temperature and heat strain, like what was that like with your device? Like I know you have some kind of strain where the heat will make the device not work or not work as properly. Do you have anything like that?
Okay. So if I'm understanding your question right, you asked if there was like a heat strain to the device. So may I ask you, what device specifically? Are you talking about the 3D printed sensor or the? So the 3D printed sensor, there was I don't believe there was testing done on that. So that's something that we'll probably be looking into in the future with this project. But thank you for your question. Yes.
Can you expand a little bit more on why you chose graphene?
Okay. So her question was, why did we choose graphene for this project? We chose graphene because It is a very promising material. There's not too much research done on it. Originally for this project, we were supposed to use another material, but there was, graphene just showed a lot of promise with its conductivity, its high strength, and many other properties it had. Any other questions?
One more.
So, as I understand, you made the filament.
Yes.
You didn't go into detail on it, and so I apologize. And you're mixing graphene into the filaments. And how was that to make the filaments? Because usually trying to extrude that material is quite difficult, and especially if you have something like you're mixing in particular, it's like you have this heterogeneous material essentially. How was that to do with just the actual process of making that filament?
So the extrusion process?
Yeah.
So his question was, how was the extrusion process with graphene? It was, for the printing, I will say that it did get clogged sometimes, so it was a lot of cleaning back and forth with it. But relatively, it was very printable. Just gotta make sure you're cleaning that machine, because when it got backed up, it wouldn't come out at all.
Okay, thank you. Remember, other questions can be taken to Chelsea at her poster, during the poster session. Okay, thank you.
Thank you.
Next up, we have Aaliyah. Oh, she's gonna, how do we change to the next presentation?
Clicker. It should just automatically go to the next one.
All right. So you want to attach that to your jacket. Yeah, on this side. Sorry.
That's not mine.
Do you know which one?
Should we just switch since Ryan's next, or she's Aaliyah Beckford? Superfluorescence of hybrid. Nope.
Just, I guess, come to my poster.
No, you're not off the hook, yeah. Oh, nice try though. She's just trying to keep us on schedule. That's all. Do you remember what you called your presentation?
Did Anna respond when you submitted it?
No, she did not.
It was submitted after 5 p.m. last night, so it may not be in there. I'll go find it.
So should we go with Ryan while we're looking for?
Yeah, I'll go talk to Anna.
Sorry. Ryan, there's a mass exodus for some reason, but it's not you. So, next up we have Ryan. Please introduce you want to put the microphone right here in your jacket.
Here.
Perfect. And even though your microphone, talk louder.
Can everyone hear me? Okay. Good. Okay. Hello. My name is Ryan Toulousan. I'm from the University of Illinois at Urbana-Champaign. I'm a rising junior in biomedical engineering, and I did my research at Shine Laboratory at Northwestern University on detection and modeling of water contaminants using microcantilever-based biosensing platforms, which is a mouthful, but we'll get into it. So, just as a general overview, we'll be going through the multifaceted problem that is water contamination. We'll be looking at how we could use current biosensing technology to address the lack of accessible testing options. We'll look into MOSFET embedded microcantilevers as our solution, and we'll look into this MATLAB's machine learning functions and how we use that to create a prediction algorithm using our data. So to start off, water contamination. Water contamination is, as we all know, very bad, right? So water contamination includes things like chemical contaminants, heavy metals, and antibiotics, right? So in terms of exposure, 56% of Americans were exposed to greater than 1 parts per billion of lead, which is a lot. It's greater than the EPA standard. In terms of inaccessibility, at-home tests for heavy metals are priced at $90 to $200, which is very expensive. Health risk, everyone knows, heavy metal poisoning causes a lot of different diseases, such as an increased risk of cancer, and marginalized communities are more likely to have water systems that are in violation of the law, and they usually take a lot longer to be fixed. Another one that I didn't mention is antibiotics in the system, and microbiomes or like biomes in general. They tend to have like a chain reaction because they kill all the tiny bacteria, which affect everything above it. So, our research question. How can we utilize current advancements in biosensor technology to develop a scalable, cost-effective, quick, and practical test for heavy metals and other chemical contaminants? The solution: MOSFET embedded microcantilevers functionalized with small oligomeric DNA sequences. Another mouthful, but let's get into the methodology. Oh, well, so here's just a quick picture of it. Okay. So let's just have a laser. So what happens here is we have a silicon nitride cantilever, and that's coated with gold, and we have a MOSFET that has 3 prongs: a drain, a gate, a source, and a drain. There's a constant voltage applied to the gate, and then our source and drain prongs are connected. Okay, so what we're going to measure is the current that goes through the drain. From here, we have, these are our small oligomeric DNA sequences. They are thiolated at one end, and sulfur, thiol is sulfur. Sulfur and gold has a very good chemistry, right? So they want to bind to each other. And when we introduce, we're going to introduce this thing called an allosteric transcription factor, or ATF. And these allosteric transcription factors are specific to an operator sequence that we embed into the DNA. So when we attach the allosteric transcription factor, or when we introduce the allosteric transcription factor into the system, what will happen is they will bind to the DNA, and because the allosteric transcription factors are pretty big, they will kind of repel each other, which results in adsorbent-induced surface stress, which also results in deflection. And that deflection creates point defects in our cantilever material, and those point defects trap the electrons and thus decrease our electrical current through the drain. So we want to, after that, we then introduce the contaminant, and that contaminant, or the ATF has a higher affinity to the contaminant, and when it unbinds from DNA and binds to the contaminant, it will result in reverse deflection, or it will reduce the deflection, and that will increase the current. And yeah, just another picture. So right now, this is our preliminary results. We didn't really get to test the methodology behind the actual MOSFET technology, but we wanted to test how effective the microcantilever is in looking at deflection and debinding. So we started off with looking at different concentrations of TET-R. So TET-R is going to be our allosteric transcription factor. TET-R is a tetracycline repressor protein that binds to the DNA. So we noticed that at higher concentrations of TET-R, right, so 1 micromolar or 5 micromolar, we noticed that there's a greater amount of deflection at around -80 nanometers. So since that goes along with what I was saying, if we attach an ATF, it'll attach to the DNA, and that'll create the deflection, right? And you can see that. And just to optimize the materials that we had, we wanted to use a 1 micromolar for our debinding experiments. And then when we got to debinding experiments, we introduced the tetracycline. Go over it again. The tetracycline is introduced, and the TET-R will unbind from the DNA and bind to the tetracycline. So at greater concentrations, there's more debinding because there's more unbinding of the allosteric transcription factor. We also noticed that we could detect the presence of 0.001 micromolar of tetracycline, which is like 0.4 parts per billion. And it's significantly different from the carbonicillin. We also have, this is our MOSFET data, like a preliminary MOSFET data. So we still need to do more tests, but we noticed that as we had greater concentrations of TET-R, our current also was lower compared to our like air or buffer concentrations, which were a lot higher for deflection. And then from there, we want to test debinding, and we noticed that at greater concentrations tetracycline, there's going to be more unbinding, and we also had a greater current, which matches what we were predicting. So in terms of our prediction algorithm, we wanted to kind of further our ability to use this for commercialization. So what we wanted to do was use MATLAB's machine learning algorithms, specifically FIT-C-SVM, which is a support vector machine that takes classifying data, binary classification data. So since it takes only binary data, we had to separate the different ranges, right? So what we're going to do, we're going to train the data, train the machines with data sets for each specific range or specific machine that we had. So anything that's correlates with greater than 0.001 micromolar, we're going to say that's +1. Anything that's less, we're going to say that's -1. And we're going to do that for each machine. Eventually, we're going to train it. Oh. Okay. Okay. Well, so we train all the data, and then we introduce this new deflection or debinding value that we want to kind of predict. So what's going to happen is going to bounce around through all these machines and try to see, oh, does it fit in this one? Does it fit in this one? And eventually it'll find one that it likes, and it'll go in, and then it will output, the machine will output a specific message, like saying the level of contamination for tetracycline is between 0.1 micromolar and 1 micromolar. So in conclusion, from our data and other studies, we can conclude that this technology is suitable as a potential at-home testing alternative for water contamination. Current testing is also being done on heavy metals such as lead and cadmium, and so far we have seen similar results. However, we still need to keep working on those. From both the optical and electrical data, we can conclude that we could detect the presence of tetracycline contamination from 0.001 micromolar and greater. Again, that's like 0.4 parts per billion. The machine learning predictive model has been successful in predicting the level of contamination. However, we do need to continue giving it more data to make it more robust. And our main goal is, if commercialized, public involvement in the testing process may result in increased regulations and greater access to clean water for all demographics. And here are just some acknowledgements. And yeah, that's it. Any questions?
Do we have questions for?
Yes.
Oh.
I just want to say that is a very fascinating, unexpected application of semiconductors. I would not have anticipated something like that.
Yes.
So these sound like they're going to be very disposable. So this would be like this wouldn't be for continuous testing. This would have to be for like periodic testing, right?
So right now, Oh, sorry. So his question is whether it will be disposable or reusable, essentially. And right now, they are like very disposable, but we hope to find this way to kind of unbind the ATF through like some washing method, and then we could have, say we have like this handheld device, we could have the user input their own like, or we give them little tubes of like ATF, and it'll go through, and it functionalizes for around 12 to 15 minutes, and then they could put their own water sample inside, and that also takes around 12 to 15 minutes to get a full readout. So right now, it's disposable, but we hope to, since we want to commercialize it, we hope to make it reusable and very accessible. So they only have to like purchase one and maybe like little refill cartridges of the ATF and whatnot. Yeah.
Also, did you do any comparisons to any sort of reference methods for measuring the? So when you compared your samples, I assume of your what was it, tetracycline?
Yeah, tetracycline, the antibiotic.
You compared that, right? You did some sort of like probably got some sort of lab standard and you diluted that, and then used that to your test, correct?
Yes.
Did you also test those same standards using an established method?
We did not. Yeah, so the question was, did we test using an established method or just something that has been used before? And we did not do that, but that's more because we're trying to prove that this concept can work and can be further tested on, if that makes sense. Yeah.
So with that, I will remind folks that you can speak to Ryan, right?
Yes.
At his poster, and we will move on to our next speaker. Thank you again. Okay, up we have Daniel.
All right, everyone. My name is Daniel Duke, and this summer at Duke University, I conducted structural and band-level alignment investigations of cesium-lead bromide, graphene, and cesium-lead iodide heterostructures via first principles calculations. Okay, so my background and motivation. Whoa, there we go, okay. So first off, halide perovskites are a specific type of material that is characterized by their crystal structure, as shown by this schematic here. No. There we go, that's the right button, okay. So by this schematic here, it has the structure of ABX3. So this is a very promising material in many applications, but primarily for photovoltaics. So for example, figure 2 here demonstrates the immense amount of research that's been put into this material in the past decade or so. So this is a citation to the first perovskite solar cell paper of the past since 2009. And then this figure here, figure 3, demonstrates immense progress that is made in perovskite solar cell efficiency in recent years. So you can see recently they've reached up to above 20%. So what specifically I looked at was perovskite graphene heterostructures. So heterostructures are combinations of multiple materials, and they have the advantage of when you combine multiple materials, each with a different absorption spectrum, they can absorb much more light, a broader category of light. And so what that does is it increases your efficiency of your solar cell. So figure 4 demonstrates a perovskite silicon heterostructure that achieves a power conversion efficiency of greater than 20%. So the heterostructure that I specifically looked at is a cesium-lead iodide, cesium-lead bromide heterostructure. And the issue that you have when you combine these two perovskites is that they will tend to interdiffuse. And when they diffuse into each other, you end up muddling up the individual properties of the perovskites, and you don't end up with a high-efficiency solar cell. So you need some kind of boundary layer. In our case, we tested out the use of graphene that will prevent this interdiffusion, and ideally this boundary layer will have some charge transport properties in order to aid in the function of the solar cell. And so figure 3, that is a literature perovskite solar cell that was made. We used this graphene as a charge transport layer. So in summary, my project objectives were to simulate the interaction of a cesium-lead bromide and cesium-lead iodide with graphene, and examine the impact of the interface plane, the interface angle, and the strain on the mechanical and electronic properties of the heterostructures, and determine if graphene interfered with the perovskite charge transport properties. There we go. So the methods. So there are 3 main stages from our project. First off, I relaxed the individual and perovskite graphene unit cells. And then in my second stage, I assembled some supercells and examined the effects of supercell assembly on the materials. And then the final stage was relaxing the supercells and running the band structure calculations. So my computational methods, I use density functional theory known as DFT. If any of you guys are familiar with that, I use the PBE functional as implemented in FHI Ames. When I created these supercells, I had to generally play this balancing game. And if you're not familiar with the term supercell, it describes a combination of different unit cells that still retains that repeating boundary condition. So this game I was playing was you can either choose a smaller supercell, for example, this one right here, and you're going to end up having a greater strain on the individual materials. However, it's a small supercell. You're going to have less atoms to simulate, so it's be computationally inexpensive. Or you can kind of tend to choose a much larger supercell, which is going to have less strain in general. So for example, this only has about 2% strain on the individual materials, but you're going to be very computationally expensive. It's going to take a very long time since there's a lot of atoms. And so I developed this, or I found this method in literature to evaluate this strain that I'm putting on materials, known as the Green-Lagrange tensor. And it gave me a very detailed way to look at both the normal strain and the shear strain that I was applying to the material so I can choose what supercell to use. There we go. This first stage was the relaxing the individual perovskite and graphene unit cells and comparing that with the experimental structure to make sure that they were valid results. So as you can see in this figure here, the difference between the simulated structures and the experimental structures are within 2% in every direction in all the unit cells, suggesting excellent agreement with the experimental results. So moving on to the next stage, that would be studying the effects of that supercell assembly on the materials. So when I create these supercells, in order to have the boundaries align with the different materials, I have to strain those materials some. And so I did an investigation into how much this strain affects the total energy of the material. And so we can see, if you take a look at the legend here for these two graphs, is that the graphene, this gray line, those all the values are divided by 10 and 20 for the normal strain and shear strain. So what that's telling me is that the graphene responds much more strongly to that strain than the perovskites. And so when I created my supercells, I strained the perovskite and I left the graphene alone. And what we can also notice is that for the normal strain and the shear strain, the percent strain, if it's less than around 2% for normal and about 1 degree for the shear strain, I have a pretty minimal effect on the energy of the material, which means I can safely strain to about that amount and it shouldn't affect my results too much. There we go. Okay. No. Okay. Okay, here we are. So the next thing I looked at when I created that supercells is the surface at which the perovskite interacts with the graphene. And so I pretty much have two options here given the symmetry of the geometry and the perovskites. I can either have the lead halide surface or I can have a cesium halide surface. And so I kind of needed to figure out which one of those surfaces it's more likely for the graphene to adhere to. So the calculation I did there, first off, was the absorption energy. So this is simply the energy released when the graphene adheres to that perovskite surface. And I found that the lead halide surface has about a 25% higher absorption energy than the cesium halide surface, which means that this surface is more likely to adhere with the graphene. And this agrees with several experimental and simulated results in literature for different perovskites. Other thing I looked at was surface energy. And so this basically tells me that based on the chemical potential environment, when I create the perovskite, which surface is more likely to form. And so I'm working with some experimental collaborators at NREL, and basically they are working on making the perovskites, and once they tell me the chemical potential environment that they are using, then I'll be able to use this graph here to kind of determine which surface will be more likely to form. Okay, so moving on to the very last stage of the project was the band level alignment. The Fermi velocity is a way to basically check and make sure my band level alignment results were reasonable. So it's very well known for graphene in literature. So it's generally in between these two values here. And basically, I calculated those values for several of the supercells I created, and I found that my values for the band levels, the band structure of the graphene, was consistent with these literature values. And I also saw that the lead halide surface tend to lower the Fermi velocity significantly more than the cesium halide surface. That again indicates that there's more interaction between the graphene and the perovskite when I'm looking at that lead halide surface. So this is my, this is my, the main result of my project, so the band level alignments for the cesium lead iodide and the graphene supercell. As you can see, I did 2 supercells here. I have the cesium lead iodide with the lead halide surface, and then the cesium lead iodide with the cesium halide surface. And what we can notice that for both of these band structures, the direct point of the graphene, which is the center of this X here, that's the part of the graphene band structure, it lies in between the valence band and the conduction band for the perovskite. And what this tells us is that when electrons are trying to jump from here to here, or vice versa, they can use the direct point of the graphene as kind of like an intermediate step to get from point A to point B. And we can see that it lies in the middle for both the cesium halide surface and the lead halide surface. However, we can also notice that the direct point position in that band gap is pretty different depending on the surfaces. And so that indicates that there's a pretty strong interaction happening that depends on what surface of interaction is happening between the graphene and the perovskite. Okay, so my conclusions of my future work and summary, I found that perovskite normal strain within 2% and shear strain within 1 degree minimally affects the energy of the materials. I also discovered that the lead halide surface is more likely to interact with the graphene, and then the graphene direct point lies in between the conduction band and the valence band of the perovskite. And then the perovskite surface of interaction changes that position of the direct point. So my future work is evaluating the electronic structure of this massive heterostructure here, which includes the cesium lead bromide, the graphene, and the cesium lead iodide to predict charge transport properties and the potential for use in solar cells and LEDs. And then also, once my collaborators at NREL are done, to compare my my simulated work with their experimental work. So, acknowledgements, Duke University Research Triangle, funding by NSF, and I use the Perlmutter supercomputer at NERSC to run these calculations. So, any questions? Yeah.
So it was a great presentation, and then one of the things I jotted down was when you were comparing the amount of strain between the different varieties, why do you think it is that the graphene responded more severely compared to the other two?
So the question was, when I was testing the strain for the different materials, why did the graphene respond more severely to that normal and shear strain? So my guess is that the bonds are significantly shorter. So on the order of like 1.6 angstroms as opposed to around 3 angstroms for the perovskite. And so those bonds are shorter, and they're also they're pi bonds. I don't know if you're familiar with organic chemistry, but they're pi bonds. And so there's simply more electrons in those bonds, and they're just bond tighter. So you have to strain those much stronger bonds, and thus they don't want to be strained as much.
Okay, let's thank Daniel again. Next we have Stephanie, and I want Aaliyah to know if she's still here hiding behind. Yes, that we will have your presentation after Stephanie, okay? And it seems that the remote control works best if you point it right towards the middle of the screen. Hi. Sorry. I don't mean to be rude.
Hello, everybody. My name is Stephanie Wang. I'm currently studying biomedical engineering at Case Western Reserve University. And this summer, I was at the Shine REU at Northwestern University. So today, we will be looking into the adsorptive properties of tea and how that can be applied to purification of our drinking water. Okay. So lead pollution is a big problem in our world today. Lead exposure can increase risk of cardiovascular diseases, kidney diseases, and also stroke. And so that's why it constitutes up to 1% of the global burden of disease. And so there's a big need to decontaminate our drinking water, especially since for children around like 60% of their total lead exposure can be attributed to water. So why are we looking at tea? Well, it is actually the most popular beverage in the world after water, and so this makes it a good adsorption candidate that can be used globally, and it has a lot of widespread use. And so previous studies have showed that waste from tea manufacturing companies actually can reduce the lead in our water. So we want to look at unused tea leaves and also the tea bags that are commonly used to brew your to package our tea leaves and how that can affect remediation of lead. Just some background on tea. Camellia sinensis is the tea plant, and so that's where you get all your derivatives of true teas. They just differ in their processing methods, and then herbal teas have other plants infused in them. Okay, so we want to do some multimodal characterization of our tea leaves, and first up we have some SEM and EDS. So here we have a black tea leaf that was put into leaded water samples, and at increasing magnifications you can see that there's a lot of ridges and wrinkles on our tea leaves, and this shows that it has high surface area and making it a good candidate for adsorption. And then to the left, this is just our EDS spectrum showing the peak of lead for our tea leaf. So other characterization, we want to compare the different types of teas, bags, leaf size, and brewing methods. And then we can also create an adsorption isotherm for our various equilibrium measurements. And then after that, we will perform some kinetics experiments. So bringing it all together, we can then create a prediction model for the amount of lead that can be remediated from our water using tea. Okay. So this is like a general methodology for our equilibrium experiments. Basically, we have water samples with a starting concentration of lead, and then we add in our tea leaves for 24 hours and let them agitate on a shaker table. And then at the end of our experiment, we can measure the concentration of lead in our water using ICP-MS and ICP-OES. And then just to zoom in on our tea leaf, we can see that the lead molecules are physically bonding to the surface of our tea leaves, and this is known as physisorption. Okay, so these are our initial equilibrium results. So here we're comparing final lead concentration versus the size of our tea leaves, tea types, and our bag material. So for leaf size, we would probably think that decreasing the size of our leaves results in higher surface area to volume ratio, so more lead remediated. But actually the difference is not too significant. As you can see in this bottom left graph, it's showing the amount of lead absorbed onto the tea leaf per gram of tea. And so the difference is really like a 98 versus 94% of lead remediation. So this is good because that means that we don't have to all be grinding our tea leaves to get the maximum effect. And then we're also looking at the different tea types. Chamomile, as we can see, had the highest ending concentration of lead, so it performed the worst. But our different Camellia sinensis teas across the board had pretty similar results. So we will be looking more into black tea and white tea for our future experiments. And then for bag materials, we can see that wood by far outperformed the other bag materials that we tested, and so we will also look more into wood later. Okay, so the previous experiments were all at one starting concentration of lead of 1 ppm, but we want to also see what happens when we increase our starting concentration of lead or decrease our starting concentration of lead. And so this is where we get our adsorption isotherm. And this is really good because even at low concentrations of lead, so let's say you're in an area where lead pollution is not that bad, but there could still be some trace amounts. And so tea is still able to absorb some of the lead even at those very low concentrations. So that is good. Okay, so we're not always going to be at equilibrium. So that's why we have this data here where we measure the concentration of lead in our water at increasing intervals of time. And so as you can see for the bag kinetics, we have our pretty expected results. The room temperature and heated samples reach around the same equilibrium value, but for our tea kinetics, there was some unexpected results where the different conditions that we tested, like room temperature, heated, and then the stirred room temperature sample, they seem to reach different equilibrium values, so this will definitely be a future point of study. And now we can model a pseudo second order kinetic fit onto our kinetics data, and this just makes it easier for us to extrapolate our data by fitting a linear equation onto it. So now we have all these pieces of information. We have our tea to water ratio, our initial concentration of lead, and the time we used to brew our tea. And then from our Langmuir parameters, we can get the percentage of tea that's remediated at an equilibrium. And then from our pseudo second orders, we can get the percentage of tea that's remediated at a certain time. And so we can use all this, and then we can create a model that predicts the percent remediated as a function of any two of our inputs. So here for black tea, these are just some contour maps that I created demonstrating our model. And so we're varying time on our x-axis and also the amount of tea per cup. And I chose up to 3 grams because that's the average amount of tea that most people use for their brewing. And so on the right of each graph is a color bar showing percentage in decimal form of how much lead has been removed from our water. And so we have some more examples for black tea. We still have tea per cup on the y-axis, but here we're varying the initial concentration of our samples. And so as you can see from our color bars, around 25% of our lead is being remediated at 7 minutes. Okay, so just to summarize, we wanted to do this experiment so we could get a better understanding of tea's benefit for public health and also look into a feasible, cost-effective way to remediate lead that can be used all over the globe since many people enjoy drinking tea. And then I was also able to model factors that affect lead remediation by tea. So for some future study, we will want to look more into the adsorption kinetics, as I mentioned earlier, and also incorporating both tea and tea bags into our model because the previous contour graphs were just showing black tea. And then we can also look at other beverages for water purification, such as coffee. And lastly, we can design nanoscale coatings that are food safe, and we can put these on our tea bags, or you can put these in the cups that we drink our tea from, so then we can optimize the amount of lead that's being remediated. And thank you.
First, I want to say I'm going to start drinking tea. Are there questions for Stephanie? Yes.
This is all for Berkeley, but we will go our youth program. So I'd like to ask, based on the research, which type of tea should I drink?
Definitely not chamomile. that was the only flower tea we tested, and it remediated the worst. I would say like your true tea types are pretty good across the board. So like black tea, green tea, white tea, oolong tea, pu'er, stuff like that. Yeah.
Other questions for Stephanie?
That was a really great presentation, so interesting. I was thinking, so in the study we were kind of measuring the absorption levels by steeping the tea leaves, right? Do you think that how this would be impacted through like agriculture, how those tea plants and water, and particularly with the chamomile, do you think that by watering those plants, does that go into the leaves itself?
So you're asking whether by watering plants with water that has lead in it, whether it will go into the plant.
The leaves that we consume?
So basically how adsorption works is that the lead molecules will go onto your tea leaf, but once they're there, they won't come off back into your water. So I don't think you have to worry about drinking tea and drinking the water. Yeah. As long as you don't consume the tea leaves. Yeah. So with matcha, you have no hope. But
So just read your tea leaves.
yeah.
Okay, thank you, Stephanie.
Thank you.
And again, what questions can come to her poster? And it's going to take a moment, but we're going to, oh no, it's not going to take time at all. There she is right there. So again, yeah, because you're going to put the microphone basically right where that is.
The number on the program, the number of the presentation is the number of your poster. So it said that the conversation starts with the poster presentation. The boards start with a C, so it'll be C1, C3. That's how you can find that.
So it's using forward.
Pointing towards the computer. Okay.
All righty, folks. We have our last but not least presentation.
Yes.
Take it away.
Hi everyone, my name is Aaliyah Beckford. I'm a physics major at Wellesley College, and this summer I have the opportunity to do research with RTNN at NC State University, and my project is called Superfluorescence of Hybrid Halide Perovskites in an Optical Cavity. So before I talk a bit more about my project, I would like to give some background information on some key concepts necessary to understanding my objectives. So what are perovskites? Hybrid halide perovskites are an emerging class of semiconductor materials known for their applications in optoelectronic devices, photovoltaics, LEDs, and lasers. They have the ABX3 structure, where A is a 1+ cation, the B side is a 2+ cation, and the X side is a halogen anion. And for my research specifically, we focus on their applications in lasers. So what are lasers? Lasers are devices that are able to amplify an incoming radiation and release coherent laser light. Coherent laser light meaning that the waves are in the same frequency wavelength and are constructively interfering with each other. So there are three main components for a laser. One, you have the pump. Ooh. Okay, one, you have the pump, which is what sends the incoming frequency in, and that could be electrical or optical. Then you have the gain medium, which is able to amplify that frequency. In our case, our perovskite would be a gain medium. And then you have what is called an optical cavity, which is two mirrors that are able to bounce the incoming frequency back and forth, which reduces the amount of power loss in the system and just increases the amount of light that is outcoupled. And there are many designs for the optical cavity. This is one of them. But the one that we use is called a distributed feedback cavity, which means that it is incorporated within the making of a perovskite thin film within itself, which means that we basically use a pattern glass substrate, and that pattern on the substrate is able to bounce the light back and forth and get the resonance that we need. And for the distributed feedback cavity, you have the height. You can also use different pitches, which is just the distance between each peak. Okay, so why are perovskites a good gain medium for a laser? One, they are solution processed, which means that if you have the right ingredients, it's fairly easy to be made. Two, they're color tunable. So by tuning the X side of the perovskite, you can get different emissions wavelength and different colors. They have a narrow band, which just has to do with the width of the peak, which makes them monochromatic. They have a high photoluminescence quantum yield, which means that a lot of photons exit from the perovskite after being excited. I don't know what the spacing is weird. So a special property of certain perovskites, like cesium lead bromide, is superfluorescence. And superfluorescence is basically when all of the dipoles in the system spontaneously align in the same phase, and upon relaxation, they release a high-intensity burst of light. And as you can see down here, for a superfluorescent material, the emissions is a lot higher. It's almost like 10 billion times higher than a light-emitting non-superfluorescent material. So, yeah, it would be good in our case if we could harness the superfluorescent materials for lasers. Okay, so the objective is that for superfluorescent material in an optical cavity, in this case it would be a DFB cavity, it would take a lot less bounces back and forth to achieve polarization compared to a material that is not superfluorescent. So there are two objectives for this project. That is supposed to say two. There are two objectives for this project. The first one is to optimize superfluorescent material cesium lead bromide in the DFB cavity, so we get the most high intensity emissions possible. And two is to study the polarization buildup time of a superfluorescent material in a cavity. So how long does it take for the dipoles to align in the same phase in a superfluorescent material in a cavity? So for the method, perovskite fabrication on a corrugated substrate, corrugated meaning pattern substrate like the DFB cavity that I showed previously. So we start with the corrugated substrate, then we add our perovskite solution, in this case would be cesium lead bromide, and then we spin coat at 3,000 RPM, 4,000 RPM, and then we add an anti-solvent drip, which basically helps the perovskite crystallize better. Then we anneal it, which fully helps the perovskite crystallize. As for the DFB fabrication, like how do we get the pattern onto the substrate, we start with what is called a silicon master mold, and that is basically a silicon wafer that has the pattern on it, achieved from photolithography. And then we put a polymer on top of it called PDMS. We heat the polymer, and once it's fully set, we could just peel it off. So now we have like a jelly stem that took the shape of the silicon master mold. So now we have a glass substrate, we add an epoxy, then we put the PDMS stamp on top of it, we cure the epoxy. So once the epoxy is fully cured, we can now peel the PDMS stamp off, and now we have the pattern substrate, and we can spin coat the perovskite on top of that corrugated substrate. So that's what we have right here. And as for characterization, we use what is called angle resolved emission spectroscopy, ARES, and that basically measures the photoluminescence at different angles from a -90 to a 90-degree angle. And what we observe when we do ARES is what is called a cavity pitch crossing or cavity resonance, and I will explain what that means later on. Okay, so this thing right here is the PL zone, and these two things are the cavity resonance that we talk about. And there are two things that we look for when we do ARES, is we want the cavity resonance to cross exactly at a 90-degree angle, or at the normal right here, and we want it to lie directly on top of the PL zone, like right here. And that basically gives us the highest intensity possible, the highest intensity emissions possible. Like if you see right here, it's like really intense. So first we experimented with different cavity pitch. So we tried 200 nanometer cavity pitch. Doesn't necessarily cross exactly where we want it to. we did 350 nanometer pitch, and that is just way off. So we did 300 nanometer pitch, and that is the closest to where we wanted to. We just needed to bring the energy at where the pitch crossing happens down, so it lies directly right here. So the next thing that we did was experiment with the film thickness, and by to make the film thicker, we spin coated at a slower RPM, and that is able to bring the cavity pitch, the cavity resonance down to lie directly on top of the peel zone. So as you can see, it's very intense compared to what we had previously. So now we've observed how experimenting with the cavity pitch, film thickness affect where the cavity resonance lie, and ideally we want the cavity resonance to fall directly on top of the peel zone and cross exactly at a normal angle, so we have the highest intensity possible. And we need to do this by using Bragg's equation, which states that N effective over the wavelength is equal to 1 over the cavity pitch. N effective is the refractive index, which also correlates to the film thickness, the wavelength, and then you have the cavity pitch. So we knew that we needed to bring the energy down for the 300 nanometer pitch. We needed to bring the energy at which the cavity resonance happens down, which means that we needed to increase the wavelength because wavelength and energy are inversely proportional. So to increase the wavelength, since N effective and the wavelength are directly proportional, we increase the film thickness, which increase the wavelength if we keep the cavity pitch constant. So that's how we knew to do that. So far, we've optimized superfluorescent material, cesium lead bromide, in the optical cavity so we get the highest intensity possible. I mean, there are more things that we could do, like maybe try different cavity pitch, like maybe between 290 nanometer cavity pitch and 300 nanometer cavity pitch, and like maybe experimenting with different spin speeds to see how that affects. But in our case, we do have the highest intensity that we could possibly get. So the next step is to further characterize and look for superfluorescent behaviors in order to ultimately understand how this buildup time happens in the cavity. This is the acknowledgement. Any questions? Yes.
Wonderful presentation, by the way.
Thank you.
The question that I did have was, you were talking about your amplification, like the light amplification, like what causes the optical amplification inside that medium? Is it purely electronics based? Such as, like, I know silicon has such a band gap where the reflective light that comes into it is going to have sort of a, I'm sorry, do you kind of understand what I'm asking?
So you're asking why does the amplification happen in a perovskite? Like,
What's called it?
I think it's just the properties of perovskites. It's just able to amplify it, and you know, it's just been proven to do it, I suppose. I'm not sure like the science behind it, you know, but it's just the properties of perovskites that is able to amplify the incoming frequency.
Yeah, so if I understood correctly, you spin coat onto the epoxy that's on the glass.
Mm-hmm.
So do you know if the epoxy has any effect on the film?
So she's asking if the epoxy has any effect on the film when we spin coat the perovskite. It does, because epoxy is very hydrophobic. So we have to go through measures, like we use a UV ozone to make it more hydrophilic, but more often it doesn't really work. So when you spin coat, it kind of clumps up, so you do see like different spots where it's like brighter or where it's dimmer. So we do have to do this like many times so we could get like actual films that we can measure on. So it does affect it a little bit, but it's possible to get data from it. So I'm sure there's like more work being done to maybe optimize how we can get reproducible films from this. Yes.
Okay, great presentation.
Thank you.
Just thinking back on the idea of the film continuity, have you thought of potentially thinking about other patterning methods to be used in this work? I know stuff in my lab that we talked about before has done some E-beam
well, the micro pattern scale to look at PL?
Yeah, so she's basically asking if there's different patterning methods that we can use. Yes, I'm sure there are, and maybe there's something that is easier as well, because I said we start with the silicon master mold, and we use photolithography to get the pattern on it. It's a very complex process, and it takes a while, so maybe different methods are less complex and take less time, so it is possible that we can look into different patterning methods.
Okay, next thing.
Huh?
Forget your name, Jen.
Oh, yeah.
All of our speakers listening. And again, remember that you can go and find their poster. And Anna just announced that your poster is your session plus your talk number, correct? Yeah. Okay. So now you know where to put.
Well, great. We might as well just go ahead and get started. So good afternoon, everyone. My name is Tirza Abbott. I manage a core facility at Northwestern University. We are part of the SHINE resource. And I'm very excited to be here and learn about all of the hard work that you've all done this summer. So let me just pull up my notes. So you will have 8 minutes to give your talk. I will give you a 1-minute warning. I'll hold up my hand and say 1 minute, okay? And then we'll have a 2-minute questions section. So first up, we have Katie Brune from RTNN. So Katie, you want to come on up here? And you just need to clip on this microphone onto your laser there.
Okay.
There's the pointer. And so this is not for the room, it's going to be for the broadcast over Zoom.
Okay, great. Awesome. Well, hello everyone. My name is Catherine Brune, and I am a senior at the University of Rochester studying biomedical engineering. And I worked as a part of the Cahoon group at the University of North Carolina at Chapel Hill, discovering the crystallinity and morphology changes in layered hybrid perovskites post-aminoefflorescence. So first, more generally, hybrid perovskites, or HPs, as I will call them throughout this presentation, are an inorganic organic material with an ABX3 structure, with the corner-sharing inorganic BX6 octahedra and A organic cations sitting in the interstitial spaces. In my work, I focused on the butylammonium lead iodide, which is a 2-dimensional layered perovskite. I also have used the traditional 3-dimensional perovskite of methylammonium lead iodide, which have both the representative schematics and SEM images on this slide. HPs also have many potential optoelectronic applications, including solar cells and lasers. Just to talk a little bit about some of the vapor phase techniques, they allow us to have better control of conditions in which HPs and other materials are made. In our chemical vapor deposition system, or a CVD, we have precise control of changes made to layered or the Ruddleston Popper, known as RP, perovskite films. This is highly desirable for creating large grain perovskite films, which improves device performance by reducing the crystalline interfaces and lowering defect density as we control the crystallization process. So just to further elaborate on that method, we use a process that's called aminodeliquescence efflorescence. Generally, dedeliquescence is the phase transition process when the humidity point is surpassed, causing spontaneous condensation and creating a super solution. Efflorescence is in fact the reverse process of that. When the humidity point drops below said the critical value, we have the recrystallization of our salt. So when looking at RPHPs that are a butylammonium lead iodide, we are inducing aminodeliquescence using a butylamine atmosphere. So basically, my talk is about preferred crystalline orientation in these RPHP films, which refers to hybrid perovskite distribution in even sheets as seen in the spun cast film. This differs from what we can create using the vapor phase techniques, which makes crossing sections of layered perovskite with no preferred orientation.
our main goal was to determine conditions of aminodeliquescence efflorescence of these RPHP films in order to create both ordered and disordered films. We also hoped to determine if there was a dependence on any specific parameters, including substrate temperature and pressure, which I'll describe throughout this particular presentation. We hope to control the crystallization process influencing the nucleation and growth rates of our RPHP crystals, and as well as the location of nucleation on different potential interfaces, such as the liquid-air interface, the liquid-to-solid interface, and also potentially homogeneously within the liquid. So, sorry. Okay. Oh no. I'm so sorry. I don't know why it's not going. Okay, so these are one potential factor of RPHP crystallinity post-aminoefflorescence is the temperature of the substrate in which the recreated film is being made. To see temperature's impact on preferred crystalline orientation, a temperature sweep from room temperature to 80 degrees Celsius was completed, and X-ray diffraction data between our aminoeffloresced films and our spin-cast counterparts were compared. In situ microscopy helps to elucidate changes throughout the aminodeliquescence efflorescence process, which we can determine as the focus of the camera was on the liquid-air interface, so we can see different nucleation types. These are videos that I'm not sure if they're working at the present moment, but they do showcase the change in the nucleation as well. As the temperature increased, the orientation as seen by the X-ray diffractograms becomes slightly more preferred as the peak intensity and level of noise changes. Additionally, as seen in the SEM images, the crystalline grain size is increased. But I'll talk a little bit more about how this is not always just one factor that we're looking at. Another potential factor that influences crystallinity was overpressurization past the critical deliquescence point. Using films at a set temperature of 50 degrees Celsius. Oh, there we go. Now we see deliquescence and efflorescence. We did a sweep of pressures both past and at the aminodeliquescence point. This process of increasing pressure did not seem to impact preferred crystalline orientation up to a point. Once passing a specific pressure threshold, in this case around 60 to 80 torr, there seems to be an increase in the amount of non-preferred crystalline orientation. And then while these previous two factors were studied solely on FTO, we also investigated the impact of substrate on the aminodeliquescence efflorescence process. When looking at microscope glass, we see that the structures are of a similar star shape to that on FTO, and you would see that on the video as well. And with silicon, we see a slightly different shape, more of a bow tie shape. But with both of these substrates, as seen in the lower left-hand corner, these films lacked a lot of continuity and were de-wetting from the substrate, which prohibits us from getting the set X-ray diffraction data that we normally use. With some further discovery, we hope to resolve some of these issues and further understand substrate dependence on RPHP post-aminoefflorescence. So then, additionally, we performed electron backscatter diffraction, or EBSD, to determine exact crystalline orientation. Using the 3D films as a proof of concept, we were able to replicate the previously collected data on smaller grains than was published by our group of around 50 microns. But when looking at some of these RPHP films, we were unable to detect crystalline patterns. And so this makes us believe that we're not actually seeing some of the large grain crystals like we thought, but instead we were seeing some of the just larger grains being made up by these microcrystalline structures. So throughout this work, it's really difficult to draw singular conclusions that impact crystallinity, given that all of these factors of temperature and pressure really are intertwined within the aminodeliquescence efflorescence process. So therefore, a combination of those factors will impact the preferred crystalline orientation over time. I started to study some of the evacuation rate of my the butylamine atmosphere, and I've started to see a trend of having faster evacuation rates, creating more ordered films, but this would need further investigation. So thinking further, in addition to determining the conditions for making large grain RPHPs, we hope to elucidate some of the substrate dependence issues as well. I'd like to thank my mentors, Alicia Bryan and Lorenzo Serafin, as well as my PI, Dr. James Cahoon, and I'd like to thank the NSF and the RTNN for this amazing experience. Thank you so much for listening, and I will happily take any questions. Like the star-shaped ones? Yes. Yeah. Sure, absolutely. So Maria's question was asking the size of those grains that we're seeing, and those are between 20 to 50 micron in size. So they're pretty large grains. But in reality, when looking at these, the butyl ammonium lead iodide films, based on EBSD data, it's more likely a series of microstructures of the perovskite and some lead iodide mixed in, rather than just straight perovskite to single grains. So we're working to try and get better conditions in order to create those single crystal grains.
All right, well, thank you very much.
Thank you.
Let's see. Yep. All right.
Can we have your attention for Sean, please? Thank you.
Good afternoon. My name is Sean Anderson, CNF, Cornell University. I'm studying electrical engineering at Morgan State University, and here I'm going to be talking to you this afternoon about coplanar microwave waveguide resonators. All right. So we're going to get into what exactly we're doing here. So we're trying to create an ensemble of spins, basically that have the ability of driving and sensing. We're trying to create a on-chip microwave resonator that has the ability to sense and drive an ensemble of spins and semiconductors. Right? Now, what does that really mean? So basically, we made these really small nanoscale devices, which have a finite length to them. So if you can imagine like a coaxial line, such as the thing that goes inside of your modem, that's around 2.4 to 2.5 gigahertz. We're doing something along that, right? And so we make this channel, which is our transmission line, at a resonant frequency of whatever microwave frequency that we're sending inside. And we'll get into a little bit more about the device physics in just a sec. So we got 3 devices that we made on our sapphire wafer. Notice I didn't say silicon wafer. So the sapphire wafer contains a 2 gigahertz resonant frequency, which has the longest length, 4.1 gigahertz resonant frequency device, which has the mid length, and another resonant frequency of 8 gigahertz, which has the shortest transmission line length of them both. Then we have a capacitively coupled
gap right here. And essentially, because we're sitting in a microwave frequency inside of our microwave resonator, that's also going to cause some inductance. So now we got two parameters. I don't know if anyone here is electrical savvy, but we have inductance, we have capacitance. That gives us a perfect gives us a perfect recipe for resonance. All right. All right. So basically, what's happening? We have this technique called electron spin resonance spectroscopy, by which it's a technique that detects the transitions induced by the electromagnetic radiation between the energy levels of electron spins in the presence of a static magnetic field, B naught. Now, that's a DC magnetic field. Basically, you guys heard me mention spin. Well, I can equate that to how the Earth spins on its axis. So just like the Earth spins on its axis, an electron will not necessarily spin, but its field lines will radiate outward, starting and collapsing on itself. It repeats this cycle just as the Earth spins 24 hours a day, 365. Essentially, what's happening is inside of our thin film, which is sitting on top of our sapphire and our niobium. I'm going to get into niobium in just a sec. That's a superconductor that we're using. Essentially, we're detecting the spins inside of a thin film that we are sampling. What that means is we're basically measuring the material, or we're measuring the magnetic response of what's happening inside of our thin film material. And what happens once we do that, we can basically gather more information about the material that we're sampling and basically get new or novel material to study more, basically to study new materials or to figure out what they're good for. Sweet. So I have a little bit more about the device physics here. We send a microwave frequency inside. Imagine that's our 2 gigahertz going inside. What's going to happen is right here, where you see that epsilon naught, the energies are going to become split between the plus energy and the minus energy. As that microwave signal comes in, as h bar omega is equal to delta epsilon, that's basically the energy that our electrons pretty much are seeing, except that one is positive, the other is negative. Now, right here, you're seeing our field strip lines. Basically, these are transmission lines which are coated with niobium. Niobium, again, as I said, is a superconductive material. We have sapphire on the bottom, niobium, and then we have our thin film that we're actually measuring on top. So that's just an aerial view of what's happening here on this 2D drawing, right? All right. So just a little bit more about the trade-offs of the device. So basically what's happening is the smaller the dimensions of the metal on top of the wafer, then we have the smaller the extension of our magnetic field, B1. That gets into the whole reason why we're making this device coplanar. So it's coplanar because we want to be able to pinpoint, have a pinpoint accuracy of what we're measuring. And just like, let's say in a microwave that you microwave food inside, because of the geometry of the device, microwave field is coming from everywhere and frying whatever you're cooking. Except that at this point, we want a resonant frequency or a resonant field in a very specific concentrated area, which is why we decided to use niobium, which is a superconductor, at a very small dimension in order to accomplish this effect. Also noting that my mentor actually used copper during the same experiment, except that the resistive losses were extremely high. So that's why now we're using niobium, just like in materials such as the magnetic resonance imaging, where MRIs, where people can scan X-rays and see what's happening inside of their bodies. It's the same material, pretty much, which gives that really strong superconductivity. Now we're going to get into the fabrication process, which I think we are all familiar with. after spending so much time listening to everyone talk about it today. So let's actually get into that. So I start off with my sapphire wafer, and I give it a bath. Right? So 15 minutes of acetone, 15 minutes of IPA. Basically, what it means to sonicate is to, spin back and forth and vibrate. We got the AJA sputter deposition system, which basically puts metal on top of the wafer. And then here's a photo of me doing photolithography, HMDS vapor prime, which basically prepares the sapphire wafer for the adhesion of resist. After I spin and bake my resist at 4,500 RPM at 1,500 rand per 60 seconds, I bake it at 150 degrees Celsius for 60 seconds. Then I expose using UV exposure, which directly etches the pattern onto the wafer. And then I develop it using a 726 MIF solution for 60 seconds. And then I hard bake it, which then sets it in. And here's a picture of that. And here's a picture of me metal etching using the chlorine gas and the boron trichloride, which is actually very dangerous. And then we strip using acetone, and now we have the sapphire and the pattern device on top. And here are some really clean pictures that I took of the actual device under a microscope. And just about the applications, this can, of course, be used for electron spin resonance spectroscopy for reactive oxygen species, reactive nitrogen species. This has applications in biomedical research. I don't know why this is here. I literally said this here. Resonance spectroscopy in soil chemistry, optical characterization in defects in semiconductors, and it has big applications in optics and optoelectronics. The next step in this device, I didn't get to actually characterize this device. So the next steps will be device characterization and to measure the defects in gallium oxide. Another thing that I did not necessarily mention is what's happening at the resonant frequencies. You go on time?
We have about 1 minute left.
Well, all right.
Unless you want to stop for questions.
Well, sure, I'll stop for questions.
We have just under a minute for questions, but please give Sean a round of applause. And also remember that you can go to the posters later and ask more questions, but if you'd like to open up for questions.
Could you, for example, take this sort of device, maybe scan it over the surface of like a silicon wafer or something like that to determine properties, look for defects, that sort of thing?
So the question was, can I use this very same device on a silicon wafer to do the same process? The answer I have for that is yes, but using the silicon, you're going to have a lot more resistive losses. And the resonant frequencies that you're looking for, they won't necessarily be as resonant, if you see what I'm saying. Because really the thing that we're looking for is the spins. Those are the defects in the device. And once that microwave frequency hits the electrons and they split into those energies, the defect is once, you have photonic energy pretty much, like they light up. The electron eats the photon and it absorbs it. And that's where our resonant peaks comes in. We don't want that in our optics. We want nice flow of electrons and conductivity.
All right. Well, again, you can visit Sean's poster later. We're going to move on, stay on time. So next we have Hassan Al-Saidi. Yes, give one more round of applause. And Hassan worked with us at Northwestern University this summer as part of the Shine Resources program, and is also taking care of all of the tech as well for this room now. So thank you, Hassan. So please put this on your shelf there, and that is for the online.
All right. Which one's the laser button? Oh, shit.
It takes a minute, so when you press this, when it goes, and just wait for a second.
Okay.
All right, so if we can give Hassan our attention, please.
Hello everyone, my name is Hassan Al-Saidi and I'm here to talk to you about a Python-based Jupyter Notebook guide for X-ray diffraction techniques. So, what is the issue that we're aiming to solve? Working at the J.B. Cohen facility at Northwestern, I've noticed that most equipment is very difficult to use, especially for newer users. And that issue arises with the manual. And if we can take a picture or look at the manual right here, we can see that it's mostly condensed with information. It doesn't really let you know what step you're at unless you've thoroughly read it. And even then, the only really use that will come out of this is if you're a professional and you already have an idea of what you're doing and you can just know, oh, I'm having an issue. Let me look at page 3, which is exactly what I'm at. And also, the complexity of the instruments does not add to the ease that users will be experiencing. So how can we solve this? First, it'll be to make our own guide. To understand how those guides are made, we're going to need a technique to actually test it on. And the J.B. Cohen facility supports a lot of techniques. Those go from grazing incidence XRD all the way to X-ray reflectivity. And if we can take a look and just focus in on X-ray reflectivity, we should note that it is the perfect candidate for a technique to use to make our guide. That is because it is useful for characterizing thin film materials, and in our case, we, just as Sean mentioned, are using niobium, which is used in superconductors. And if you look at the graph at the right, you can see that reflectivity is pretty much a measure of the X-rays reflected off the surface. And just a few 3 individual variables to just remember for later on the presentation. Just one moment. The thickness of the film has an effect on how the graph looks like. The roughness of the film has an effect on how the graph slope is like. And last but not least, the difference or the ratio of electron density between the film and the substrate gives off either a line or ridges. So, moving on, we have a technique, but we don't know what we're basically doing. So we have to center ourselves and actually find a goal, just so we know when we've accomplished something and when we haven't. So the goal is to create experimental guides in Python-based Jupyter Notebooks for various types of X-ray lab experiments and updating previous versions to include more functionality and ease of use to non-students. So we have a technique, we've zoned in, now we need to choose a machine. At the J.B. Cohen facility, the X-ray reflectivity, the SmartLab Gen 2 3 kilowatt diffractometer is easily available. Also, it's fairly complex, as you can see in this little diagram over here. So we just decided to choose it. Now, the method that we're going to be using is Jupyter Notebooks. Jupyter Notebooks is well, it's usually known as a data analysis tool, but we're able to code things in it. And what makes it better than a normal PDF, because we look back in the guide, why don't I just restructure it? Well, this allows me to code things in using Python, such as buttons, sliders, simulations, everything to my heart's desire. As long as I can code it, I can put it in. So the model that we're going to be creating our guides for is me. I'm a new user. I want to check out the diffractometer. I have my own little laptop. I don't need to go ahead and buy one, or kind of your own, but I don't need to go to an office and get a specialized J.B. Cohen laptop. I can download the book from online or from a link given to me, and using that book, I can go through and little by little in digestible steps understand what's going on behind the diffractometer in my experiment while going through it in an efficient and safe manner. And just to give you an idea, user Jupyter Notebook, operational knowledge, and because of these little steps over here, we're able to understand exactly what the Jupyter Notebook model does. So, how can these steps be presented in an interactive format? We have our tool, we have our technique, we have our machine, but how exactly is this going to work? Well, each guide has an introduction, a setup, an instruction list, and data interpretation, because get your data, you actually have to interpret it. So we, at the JBCon, or me and my mentor, we created a GenTools class. It has a bunch of templates inside, and as you can see from all these different versions, we've been able to add a lot of different tools in it. So you can think of GenTools as a toolbox, and it's all hosted on your personal computer. As you can see, there's a local host. There isn't like a HTTPS, et cetera, et cetera. And so, yeah, just a little box over there. And so GenTools, acting as the toolbox, will support all these steps. And over here you can see a list, pick, GIF, general simulations, and general data reduction is what GenSims and GenReduce are. So our results, you can have your phones ready at the end. I'm going to put a QR code just so you guys can scan and actually look at the results. But for now, let's just skip this slide and look at a specific portion of the results. So if we think back to the graph presented above and the film and substrate, we can see, remember the three variables: film thickness, film roughness, and the ratio between the electron density ratio between the film and substrate. So in this specific example, I changed the film thickness, and in real time, I was able to see this graph add on more ridges, which is exactly what it should do. And because of this, as a new user, just to sum up why this is important, as a new user, I'm able to understand why my film thickness is important, or why my film roughness, properties like that are important. And again, all in real time, which compared to PDF, where you can't even click a button, this is much, much better. So if you can all have your phones out, which I'm sure some of you are, you can take a picture over here. Yeah, that was pretty quick. Or use the QR code. And I'm going to skip this slide for now, but in the acknowledgement slide, there will be a QR code, so don't worry if you didn't get it yet. And just to sum up, instructions and data can be accessed outside of the lab, all in your own personal notebook. Data analysis and reduction are all in the same place, so all in your one little notebook file. Instructions are easy to edit and modify. As you can remember, we had 9 versions, and we kept editing and modifying all of them. The guides are interactive and provide a deeper level of instruction because you can actually interact with the concepts that you're learning or using. And using Jupyter Notebooks for any application, this can branch off to many different fields. Whether you're in material science, physics, chemistry, et cetera, you're able to use these tools because they can easily be modified and the content can be changed for any field. And yeah, some of the current tools available, we have sliders. That's a button declaring itself. That's a slider that can show you the variables changing as you change the slider. That's some button output. Here's a checklist from our checklist class, and here's its output if you fail to do it. Here's the graph that I showed you. Here's a GIF, but you can't really take a picture of a GIF because pictures aren't GIFs. And here's a picture class, and you can see everything formatted, left, right, center, with pictures being changed and figure descriptions. All right, I guess any questions? I have a minute left. Hello? Yeah?
So does using your kind of like your GUI and your interface require any level of like coding knowledge or something?
Not too much. Well, the main goal of this was to make it, she asked, are you supposed, or do you need any previous coding knowledge? Not a lot. Basically, you write one sentence, for example, the checklist, you write 1, how many steps, 2, you write all the steps in one string, which is basically a sentence. You put down what's the character that you're using to separate so that the program can take that one long sentence and break it down. And what happens if the user finishes it. Oh, hey, move on. Something like that. Yeah?
Why would you use Python Jupyter Notebooks instead of like HTML and JavaScript, which is like the industry standard for interactive?
true, but Jupyter Notebooks, it's already known as a data analysis tool, but also the one up that it has is that it does incorporate HTML and JavaScript. I can talk to you about it later in the poster session on C16, but it does do, I'll talk to you more about it. It does include HTML though. He asked why use Jupyter Notebooks.
All right, well, you can finish off with it. Right. So,
throat is so dry.
all right, so let's welcome Ashley Martinez from NCI Southwest from Arizona. So yeah, you're gonna clip that maybe to your name, so you can be a good distance away. That's for our audience online. I think that's okay, but our tech person just left the room, so I don't know. Just making it up as we go. Yeah, laser pointer. There's a slight delay to the advancing, so when you click it, you want to point it that way, but it will change. Just give it a minute. And then at the end, we'll keep questions. All right, so let's give Ashley our attention.
Sweet. Hi, my name is Ashley Martinez, and I study biochemistry at Northern Arizona University. I'm part of the NCI Southwest REU, and my mentor this summer was Professor Jennifer Martinez. And today I'm going to show you all my summer research, which was trying to create a one-dose delivery system for vaccines. So real quick, what's a vaccine? It's just a substance that you put in your body to increase the antibody production and provide immunity against a virus or a disease. And so we need these vaccines because they help protect us from dangerous diseases. They help protect vulnerable, so people with compromised immune systems, elderly, kids, and they help control epidemics and pandemics. And so in order for most vaccines to be effective, they need the initial vaccine and a booster. And so a booster is just another dose of the initial vaccine that you get about a month or two outside of the initial. And yeah, it just increases your immune response. And so here on this graph that I have on the right side, it just shows that. So you go, you get your initial vaccination, and y'all probably felt it whenever y'all got a vaccine. Within the first few days, you kind of feel some side effects. That's just the increase of the antibody count within your body and reacting to that antigen exposure. And so we can see a peak on the graph on that first little hump, but it goes back down. So not all of those antibodies get turned into memory cells. So you need to get that booster to increase your overall antibody count. But some disadvantages to doing a booster is patient compliance. So the patient not coming in for a booster for whichever reason may occur, and then also having a slow rollout, so not having access to that booster. And so our solution, what we want to do is eliminate boosters by just having one shot. And so the way this would work is that we have that colored syringe, or that syringe with the colored dots, and we have 3 different colors. So the blue dot would be like your initial vaccine, the yellow dot would be your first booster, and the red would be your second booster. And so the blue dot, it would release at around 10 days, yellow around 30 days, and red around 60 days. So the big goal is to understand the material science and the creation of vaccines. More specifically, we want to, 1, do a one-shot, so time that release of the nanocarriers to mimic that booster. And then 2, we want to target the delivery to the correct immune cells. And so we're going to create these nanocarriers using material science. And some advantages to using nanocarriers is that they can hold that vaccine within, and they can protect the vaccine from a premature release or degradation. And then side note, I'm going to be using particles and nanocarriers like interchangeably. So when we create these nanocarriers, we want them to be a specific size. So here we have 3 size ranges. The first range we have is less than 50 nanometers, and so it travels to the lymph nodes, which is great, but because of its size and it being so small, you can't fit much vaccine within it. So it's not ideal. And then on the right-hand side, we have greater than 500 nanometers. And so, because it's so huge, you can carry all this vaccine within it, but it gets taken up by the macrophages, so it's a weaker response in your body overall, so it's also not ideal. So what we want to do is aim for that 100 to 500 nanometer range, and so we're aiming for that because it carries more vaccine compared to that 50 nanometer, and it gets taken up by the correct immune cells as opposed to the 500 nanometer range. And so, yeah, there's a lot of different delivery systems we could choose from. However, we're going to go with the polymer or PLGA more specifically. And the reason we're going to go with this is because it's non-cytotoxic, so it doesn't harm your cells. It's FDA approved, it's modifiable, so you can tune it, you can change its size, you can add things in it, take it away, change its stability really easily. So it's very ideal. And that's the chemical structure for PLGA. And so why PLGA? First off, PLGA, it just stands for polylactic co-glycolic acid. And there's many different types of polymer or PLGA to choose from, but we narrowed it down to these 8. And out of these 8, we decided to go with P4 and P7. And so we went with these because okay, so let's look at picture A, and we can see out of those 5 samples, it's pretty opaque, pretty white throughout, so that's great. And that's the PLGA made in water. However, in picture B, I added a buffer that mimics physiological conditions, so your body pH. And out of that, P4 was the only one that stayed consistent. It stayed opaque, it stayed stable. So since we're working with physiological conditions, P4 and P7 were able to make stable particles within physiological conditions. And whenever we measure these particles, we can see that it's stable and like it's dispersed within the buffer. But we need something like a little more specific to measure its size. So I use DLS, or dynamic light scattering. And all DLS does is that it determines the size of a particle within solution. And so these particles within their solution, they kind of free float wherever they want to go. And that's called Brownian motion. And so we have our bigger particles, and those tend to move slower, and smaller particles tend to move faster. And so the way it works is that we have our sample within the DLS, and the DLS will shine a light, and depending on the particles that light hits, there's a sensor that captures that scattered light. And so what happens is that the DLS measures that scattered light, turns it into a correlation function, which turns it into a size plot, and that size plot is what I look at for my data. Ooh, just kidding. Yeah, so we have 2 graphs here, and these are both measured by size that was determined by the DLS over the function of days. And so this left graph is the P4 particle degradation, and it has a short stability. We can see that it degrades around day 3. And then on the right, we have P4, P7 particle degradation, and that seems to degrade around day 12. And so here we reached one of our goals, which was have the particles degrade at different times. And then here is another graph, and so this is measuring its cargo release. And this is still P4, P7. And so what we see here is that its cargo release is pretty much the same. And so even though they degrade at different time points, they released around the same time, so that's not ideal for us, but we're working on it. But what we can see here is that it's a steady release instead of a burst release, so that itself accomplished one of our other goals. So what have we learned? We learned that we can create nanocarriers that are stable in physiological conditions. We were able to create a time stability of different formulations to degrade at different time points. And we can use DLS, microscopy, and fluorescence spectroscopy to allow us to understand the carrier degradation and release of vaccine. And some next steps. So creating some ELP, elastomeric polymer, for a longer stability of nanocarriers. Finalize the understanding of the release of vaccine from PLGA nanocarriers, and use some atomic force microscopy to view the morphology of these particles, so what degradation looks like. And some quick acknowledgements. I'd like to thank NCI Southwest for mentors, Professor Jen Martinez and Professor Gabe Montano, and my colleagues, Christine, Lisa, Jorge, and Matt. And I'm ready for questions.
Thank you so much. Anybody have any questions?
Was there a specific reason you chose PLGA as your polymeric nanoparticle compared to like other polymers like hydrogen?
Yeah, so
Repeat the question into the microphone.
yeah, so the question was why we chose PLGA over some of the other polymer, and that's just because it's really easy to work with. Like I said, it's FDA approved, and it's not going to harm your cells. It's supposed to go like into bodies, so that's kind of important. And then it's just easy to change and like tune its size. So yeah.
Great presentation. Just also about polymers, is it possible that potentially mixing two polymers might actually allow you to have a longer time point since they may release at different time points and create that sort of one shot within?
Yeah, so my samples that I used was P4 and then P4, P7, and so without DNA, the P4, P7 had a longer stability of that 2 months. However, whenever the DNA was added, it had a shorter stability, so we're working on seeing more of that.
Any final questions? All right. Well, great job. Thank you so much. Let's put your All right. So, last presenter of this session is Ryan Chow from KY Multiscale. You've seen the deal a few times now, but I'm going to run you through it.
That's good.
So we're going to put this on you. Remember, you're attached.
Okay. Yes.
You can put it anywhere kind of lower. Yeah, whatever you touch. All right. All right, so if we could have your attention for Ryan.
Hi, I'm Ryan Chow, and this summer I've been working in Dr. Chow On Fu's lab with J.D. Morris on the characterization of a particle-packed microreactor over flow and temperature. And so some motivation behind this project is essentially in our breath there are ketones and aldehydes which can be detected using a microreactor. And these ketones and aldehydes are seen at higher concentrations when you're sick with certain diseases, say lung cancer, COVID-19, or other various pulmonary diseases. So the idea is you can detect these ketones and aldehydes in order to detect whether or not someone has some sickness or something. And it's also very non-invasive. And so some previous work, we've done a lot of work with microreactors that have been microfabricated with silicon pillars inside of it. And we've tested how the density of these pillars affect capture efficiency, how the shape of these pillars affect capture efficiency, along with how the length of the reactor affects capture efficiency. So some more recent work is we've been using a lot more silica particles. And so, for example, we've been using cartridges so that the idea is you could have a lot more higher of a flow rate. So someone could ideally just breathe through one of these devices. So for my project, I've been using a microreactor that we're putting silica particles in instead. And so some goals for this project was I wanted to determine the transition between the mass transfer limited region and the reaction limited region. I also wanted to characterize how this phenomenon behaves over temperature and also determine and understand some of the limitations of the system some more. And so a little introduction on the microreactor I'm working with is it's about 7.7 by 4.5 millimeters, and it was etched on a silicon wafer using DRIE to a depth about 360 to 400 microns, and then a piece of borosilicate glass is bonded on top. And then the bottom left corner you'll see, or bottom right I guess, you'll see a picture of my microreactor next to a dime. So I think it is pretty small for ideally putting into some bigger system that we could bring out to market hopefully. And so the idea is we're using an oxidation reaction to capture these ketones and aldehydes. And you can see the reaction is between the amino-oxy and the ketone or aldehyde in the bottom right-hand corner to create these oximes. And so for my project, I was using PFBHA and ATM, which you can see on the screen right now, and we're coating the silica particles with it. And then, So what's happening is we're putting this gas mixture, or say someone's breath, for example, through this microreactor where this amino-oxy or oxidation reaction will occur, which essentially catches these aldehydes and ketones out of the flow, and all the other molecules will flow straight through, say oxygen, nitrogen, argon, and this allows us to pre-concentrate these ketones and aldehydes for further analysis as oximes. And so we can further analyze this using GCMS, or gas chromatography mass spectroscopy, where we're using the PID setting for the GCMS, which essentially we're just using the mass spectroscopy to filter out a lot of the noise in the gas chromatogram that we see in the top. And the gas chromatography, essentially what we're doing is we're using the differences in a temperature gradient along with the differences in polarity of the molecules in order to separate all the compounds and detect it. And you'll also see that we have TFBO-MEM, which is an internal reference that we add to the system after we've pre-concentrated of a known amount of a compound, and then we can normalize all the other peak areas to that one in order to determine how much we've actually captured. And so what I wanted to do first was I wanted to look at how the system behaves over various flow rates with PFBHA and ATM. And what you'll see is with PFBHA data, we seem to see this plateauing effect happen for acetone, say, around 10 milliliters per minute. Pentanone and pentanal, we're seeing this occur around 30 or 35 milliliters per minute. And then acetone, we're seeing it happen around more like 22 milliliters per minute. And so what it kind of seems like is when we're using PFBHA, there's this difference in where we're seeing the plateau happening depending on the size of the molecules. And so when we compare this to the ATM data, we see that acetone is plateauing even earlier than, say, 7 milliliters per minute. Pentanone and pentanal and acetone are actually plateauing at a relatively similar flow rate, where we're seeing it around 22, 24 milliliters per minute. And so what this seems to indicate is, if you remember back on the previous slide over here, is the PFBHA versus the amino-oxy. The PFBHA has that giant benzene ring with all of these fluorines on it, versus ATM where we just have a nitrogen with a couple methyl groups. And so this seems to indicate that maybe as we're increasing the size of the actual molecules, the PFBHA has more selectivity for the smaller molecules because of that big benzene ring, which is limiting the reaction with sterics. And so we can further analyze this by combining the plots into a single plot. And what you'll notice is for the PFBHA data on top, we see the ordering change as we increase flow rate. And so initially at the lower flow rates, we have it go in the order of acetone, then pentanal, then acetone, then pentanone. While as we increase flow rate, it switches to pentanone, acetone, pentanal, and acetone. So what we notice is that the actual ordering of these compounds isn't in the order that you would expect based on reactivity. And so something is happening instead, which might be a diffusion-limited system instead of a reaction-limited system. And so then we can further look at this data based on the temperature. And so what you notice is as we increase temperature, and so this is at a set flow rate at say about 45 milliliters per minute. And so what we notice is that as we increase the temperature, capture efficiency seems to scale about roughly linearly with it. And so what that seems to imply to me anyways is if the system is diffusion limited and not reactivity limited, is it could be following Stokes-Einstein's equation for diffusivity versus temperature, which essentially scales diffusivity linearly with temperature. And this would make sense as to, it would tell us that the limitation on the system is similar to a solid diffusion or liquid diffusion, which would make the most sense as the diffusion across the surface of the silica particle. And so what this also makes additional sense if we look at the ordering in the sense that we have pentanone at the top, acetone, and then we have pentanal and acetone. And this makes sense because if you know ketones and aldehydes, right, they have a partial positive on that carbonyl carbon. And so this would be the same ordering we would expect based on the partial positive charge on that carbon. And so the ones with the higher partial positive are actually getting stuck and are being more limited by diffusivity. Another thing that was talked about was this could still be the Arrhenius equation, except we could just be at a point where the temperature isn't changing enough for us to see the actual Arrhenius scaling that we would expect. So it could be approximately linear in the region we're looking at. And so we wanted to additionally look at this effect at an increased flow rate to see how that transition occurs. I didn't actually have time to look at the lower flow rate for the 50 Celsius to put on this PowerPoint, but what we do notice is that it's following what we would expect for the theoretical work for a packed bed reactor. And so essentially what's happening is, we remember at 25 degrees Celsius, some of these compounds weren't even plateauing at, say, 30 or 35 milliliters per minute, while when we increase it to 50 degrees Celsius, we see that the plateau is still going strong at around 17 milliliters per minute. So this kind of implies that as we increase temperature, we see that we would expect increased capture efficiency, but we also see the plateauing shifting more and more to the lower flow rates. And so that's it. Any questions? Yeah.
Thank you, Ryan. All right, any questions?
Yeah.
Considering the variability in where the astrum end up, well, I'd like to also point out, thank you for that presentation, because they never really, the only thing the GCMS seemed way simpler, and then as you've shown that there's so much more that can go into it, first off. But in terms of like, since there's so much variability in the ordering of those peaks, how would you handle a natural sample that has all this background in it? Like,
Right. Sorry, did you have more to that question?
No, just like what would you do with that sample of all those different, given all that variability?
Right. So essentially what's happening is, so the question was, in an actual breath sample, we're going to have a lot more variability. So how are we going to use this same method to look at a breath sample, for example? And so the idea is behind it is, if we go back to the GCMS slide, if I can get back there, is essentially, so we're using a calibration curve to normalize everything, but in an actual breath sample, we don't have a calibration curve for every single compound, and they're going to be a lot smaller. So what we do instead is we look for these compounds, and instead of using the single peaks, we're actually not filtering out any of the noise. We're going to do a full scan. And so you can use the mass spectroscopy to further analyze the data and look at what compound you're looking at. Additionally, instead of using a calibration curve, you can use a ratio between just the things, and you can assume that it's a proportional relationship, even though it's not. And essentially what you get is you get a rough idea. And so that's what most of the stuff with actual breath samples are being done right now. It's this same data, but it's being analyzed using a different method. The reason why I use a calibration curve is because I'm characterizing the actual reactor, so we do want to be as accurate as we can to look at the data. Does that answer your question?
I think it does.
Awesome, thank you. Any other questions? Cool.
All right, well, thank you, Ryan, and thank you, everyone. You all did a really great job. You should be really proud of yourselves. So now we're going to go.
Okay. Hi, I'm Ariel, and I study chemical engineering at Cornell University. And this summer, I was in an RU program at the University of Pennsylvania in the Singh Center. And my project was biodegradable phosphate sensors for agricultural use. So phosphate is a key ingredient in many fertilizers, and farmers tend to overuse fertilizer in hopes to get a good crop yield. And this overuse of fertilizer leads to a lot of environmental problems like eutrophication or the buildup of nutrients in bodies of water. And to solve this issue, we made a biodegradable phosphate sensor. Oh, no. Okay, so our sensor tests soil in situ, and that increases spatial resolution so farmers can get more data about their soil, and it also decreases the time it takes for them to get their soil data back. So, see, okay. So this is what the sensor looks like. We have 3 electrodes right here. There's a molybdenum working electrode, and a tin reference electrode, and a tin counter electrode. And then this is connected to a potentiostat, and that supplies just a constant voltage, and our sensor measures current.
And then the chemical reaction that happens at the sensor is right here. So this is what's happening at the molybdenum working electrode. Okay, so I did 3 tests on my sensor. So the first tests I did were beaker tests. And these were just in our lab and with phosphate buffer solution. And the goal of that was to map phosphate concentration to a current output. And then I started with soil tests. And these were burying the sensor 10 centimeters deep and covering it with a cellulose sponge to have that same aqueous environment as before. And also waiting 10 minutes after irrigating or pouring water on the sensor or the soil and the sensor before measuring to allow for diffusion of that water. Okay, I don't know what happened here. Okay, here it goes. So then I did fertilizer tests. And those were using the same procedure as before, but then now varying amounts of fertilizer on the soil and seeing how our current varied. Okay, so these are the results from the phosphate buffer solution tests. This is right here is what it looks like in the lab. And then this right here is our graph of our data. I did a couple different sweeps at a couple different pHs, and that's because the pH of soil can change from place to place. And then you can see that it follows a power function here, and also the pH of 8.2 is the most sensitive to different concentrations of phosphate buffer solution. And then these are the results from the soil tests. Right here is what it looks like when we were trying them. And we could actually do calculations to compare this to traditional soil tests that farmers would get. And using some assumptions about how much soil our sensor is measuring and how much water is in our sponge, we could get about a 10.5% error, which is pretty good. And then this is what our output of our sensor looks like. So we have a current versus time graph. And right here, where it's kind of just going up, is diffusion limited. And it's limited by the diffusion from the phosphate from the soil to the water. And then right here, where it levels out, is where we take our readings, and that's kinetics limited. And that's when it's just limited by the kinetics of the reaction happening at the working electrode. And then these are the results from the fertilizer tests. Set 1 and set 2 were taken on different days. So you can see that the slope here is the same, which is nice, but the y-intercept differs, and we think that has to do with differences in humidity and temperature. And we're working right now to correct this with rate laws and the Arrhenius equation. So yeah. And then in the future, the ending big picture goal for our sensor is to be able to bury the sensor in a crop field and have a drone fly over the crop field and take all of the measurements of the data for us. And then we want to expand this to other nutrients that are important in fertilizer and soil, such as nitrogen, and we want to do that with biodegradable ion selective membranes. Right now we're looking at urushi, which is a Japanese lacquer. And then we also want to come up with a really good, efficient manufacturing method for this, so we can just have a bunch of sensors and be able to put them in a bunch of crop fields. So these are my acknowledgments. This is my mentor, Liz, and this is my PI, Dr. Allen. And we got our soil from JD Recycling, LLC. Yeah, and then these are my references. So thank you for listening.
Any questions?
Hi, Sean from Florida State University Electrical Engineering, Cornell, CNFRU. I had a question about your chemical reaction. So yeah. I noticed MO, what does that mean?
Molybdenum. Okay. Yes.
I'm Ryan. or is this more of a kind of environmental thing where we're trying to monitor how much chemicals are running off from those at test?
Yes. Yes, so we want to make sure that the farmers know the fertilizer levels and how much phosphate or maybe in the future nitrogen that there is to try to curb some of this environmental problems. So it's not exactly at this point like how much is the plant getting, although that's important too, but also just trying to curb some of these environmental issues.
Okay, and then I just have one more question if you can. You mentioned that it's a biodegradable device. How far along is that? Kind of like, do you guys have like a prototype kind of thing? How long does it take to degrade?
Yeah, so we're still working on that right now. I'll go back to the picture of it. Yeah, so as of right now, this is what it looks like. In the future, we don't want to have it, the potentiostat. I don't know if anyone's familiar with a GAMRI. It's a machine that's like hooked up to a computer and then plugged into an outlet right now. We want to, and we're working on connecting this to a biodegradable battery to power it. And then we have this polymer right here, that's a biodegradable polymer. And then these electrodes here, we want to be able to make this on a like super small. So when this stuff does biodegrade, it doesn't make that big of a difference in like the grand scheme of like the soil in the crop field. So that's where we are with that. And then we're working on like better wiring methods and probably not using as much Kapton tape. Yeah. And then we're still doing studies on how long it does take to biodegrade and what if we want to use some sort of glue or something that could maybe make it even better. And we would like it to biodegrade in the time frame of a crop season. So, yeah.
Okay, thank you.
Yeah.
Is that it? Thank you very much.
Yeah.
Next we have Erica. Nope. I said somebody. Teresa? Teresa? Yep. Presenters, if you could repeat the question so that the camera can hear it after someone asks, that would be beneficial.
All right, ready? Okay. Good morning, everyone. My name is Prisa Zalmai, and this summer I worked at the University of Louisville under Dr. McNamara's advice to develop a tactile tablet for vision impaired individuals. And I go to Virginia Commonwealth studying biomedical engineering. Well, why is this project important, you might ask? Well, according to the NIH, about 40% of the blind are employed, whereas about 79.5% of the non-vision impaired individuals are employed. This is a huge gap for those who are visually impaired and for those who aren't. Hence, one of the reasons for that is because of the lack of access to higher education for the blind people, especially in the STEM fields, because of how limited access they have to like the materials and stuff. Some of the existing solutions or some of the existing technologies for the blind, we have the Braille since the first time it was invented. We have QWERTY keyboards, and we have some other types of keyboards. The only good things about those is that they're portable, that you can take them anywhere you want to. But the problem is that they're all only can only provide one line of text and are really expensive. And with one line of text, you can't really do any mathematical graphs and equations, especially in higher education. So that's a huge problem that we were trying to solve. So the ultimate goal of this project is to develop a tablet, essentially, to replicate the Braille. And so this tablet would have an array of 100 by 100 microvalves that would be pressurized using, that would be actuated using pressurized air. This is the ultimate goal. However, what I worked on this summer was I basically decided to tackle two of the problems that I had. So I wanted to design a pneumatically actuated micro valve that would have 12 braille pins, which would display 2 letters of alphabet for proof of concept. And then because when we designed our pneumatic valves, we had solenoids connected to them, and each one of them required 5 watts of power, which would be a lot in the long run. So we tried to tackle that problem too and try to reduce the power consumption in these devices. So for my pneumatic actuation design, we had an original prototype that had been worked on before. We have the PDMS layer attached to a PMMA base. The problem with that was that the PMMA and the PDMS wouldn't stick together when we applied pressure for these holes. So we tried to come up with a solution to have those stick together after pressure was applied, air pressure was applied. So the one picture to the right shows the design layout of what we were trying to do. So we have the PMMA support base, and then we have the PDMS flexible layer, which would be pressurized and inflated. And then we have the new thing that we added was the steel clamp that would also have the same dimensions as the PMMA base, as well as the holes. So when we apply pressure from the PMMA base, it'll go through the hole and it'll inflate the PDMS layer. However, one of the trade-offs with that would be that we now have to consider the thickness of the steel clamp, because then we have to see how much it'll inflate so it resembles a braille pin. The one to the bottom right shows the assembly at the end. We were able to design and send it and get it laser cut and have it come back to us. So the one to the right, the one to the left shows the steel clamp layer, and then the one to the right is our final prototype all assembled together, and air pressure was applied at the end, which I'll show the results afterwards. So we had to do some calculations. Obviously, like I said, there were trade-offs with our new design that we had to account for the thickness of the new layer that we added. And so we used this formula using MATLAB to figure out how much pressure we need to apply for our new design to have it inflate as high as a regular braille pin. So a regular braille pin height would be 0.48 millimeters, but now we had to also consider the thickness of the steel layer, which is 0.38 millimeters, so that would be our desired deflection. And then we had a Young's modulus reported for commercially available PDMS. We didn't know the exact one, so we had to do it across a range of Young's modulus. And as we can see, if we have anything between 2 to 2.5 megapascals, we would need a gauge pressure of 50 to 60 psi. How do I get this to like play? Okay, well, this is the PDMS layer inflated at 40 psi, and the results were that we could see that we could feel the bubbles, and our goal was to have the layers stick together, which they did, so that was successful. And then we had, like I mentioned before, our design was pretty successful, but it also required 50 watts of power for each one of those valves to be actuated. So these are the solenoids that we used to actuate the previous design. Each one of them takes 5 watts of power, and if we were to have it at 100 by 100 array, that would be 50 kilowatts. It's not ideal, it's not practical. We don't want that. So we came up with a electrostatically actuated microvalve design, which takes a parallel plate capacitor connected to a cantilever beam, like we can see in the picture up there. So the electrostatic force is what causes the plates to move up and down. The bottom plate would have a hole similar to what we had in our previous design, but in this case, the hole would open and close as we apply and remove the voltage. So we had to also have some calculations for that one. We had to, so our goal was to keep the voltage below 50 volts to keep it practical. So we came up with some dimensions, and we were given some of the dimensions for the material that we were using, which is the 1075 spring steel, which is 0.35 millimeters thick. And so we calculated the pull-in voltage, which is when both of the plates stick to each other or attract each other and the hole closes, and we were able to get a pull-in voltage of about 15 volts, which is pretty good, which is a lot lower to what we had. So it makes our design super promising too. And this was our design for our electrostatic micro valve. This is the design for the top plate connected to the cantilever beam. This is the SolidWorks model. Unfortunately, because of time constraints, we were not able to test these. But they were sent out and they were being cut, and I have it with me too. So if anyone wants to see it, come to my poster. I can show it to you, but it's pretty cool. So hopefully this is something we'll be working on in the near future. But conclusions, like I said, my goal was to have all these layers stick together and have them have the layer deflected at a reasonable height, which we were able to get that, and also tackle the power issue, which we were able to do. The results are pretty promising. We just need to test those. And the future work is to take the prototype to the American Printing House in downtown Louisville and get it validated by someone who is visually impaired, so we can confirm our results. But I would like to especially thank all these organizations and people here, especially thanks to Jacob Shop, who helped me a lot throughout this project, and obviously my advisor and everyone else who was involved in this. These are my references.
Questions?
I have a question. So, it seems the main problem is you need a large number of different, I guess, solenoid things.
Solenoids, yeah.
That cost 50 watts of power.
Mm-hmm.
So, what was your solution then to?
So Nathan's question was that we were using solenoids. So each one of the solenoids uses 5 watts of power, which is a lot of power when it comes to a 100 by 100 array of microvalves. So we decided to instead electrostatically actuate our microvalves, because the previous one was pneumatically actuating, so we would have to apply pressurized air using those solenoids. But now we can use electrostatic. We have the electrostatic here. So we have the electrostatic actuation design, which is what the parallel plates are for, and we use the cantilever beam to hold the plate up if the voltage is applied. Yeah.
Anything else? Thanks again. Now for Erica, is that right? Yes. Okay.
Hi, my name is Erica Cairo, and I'm an upcoming junior at Seton Hall University. And this summer, my project was titled Microfluidic Handling of DNA for Spatial Genome Research. So to start, I'll start with a little bit of background. FemtoSeq is a new microscopy method used in BME, and it's used to isolate and biotinoate tag DNA. This method is really helpful to study chromatin environment, especially chromatin at the base pair level, and it's been implemented in a lot of BME labs for things like cancer cell research. The only issue about this method is that the amount of DNA that is needed to be isolated and purified is very, very small. So any mishandling of this DNA will lead to our loss of sample, and currently we need about 30,000 cells in this method to get a good enough sample when we go through the whole DNA purification process. So to kind of combat this problem and to attack it, we decided to implement microfluidics, which is already really great for handling small volumes of fluids. And we decided to use photolithography to fabricate a device that, if successful, would be very versatile and would be able to make DNA purification a lot more sensitive, so that we'd be able to reduce the amount of cells needed from 30,000 to about 100 cells. So we've all been through like the photolithography method, so I'll probably skip this slide, but just an overview. We used a silicon wafer, and when we were able to isolate our positive features, we casted PDMS over it. To the right is what our device in fact looks like. We just have a single fluidic channel, and we bonded the PDMS to a glass substrate. So our project has three very main stages. Our first stage was to fabricate our microfluidic device, and for this we used multi-layer SU8 photolithography. Our first layer, as I said before, is just a single fluidic channel right here, and then we added another layer of herringbones. These herringbones were our mixing elements, and the idea is to discourage that laminar flow of our sample as we run it through our device, and so that we can increase our purification yield. The next step of our project is surface functionalization, and for this we want to functionalize our glass substrate down here so that we can immobilize streptavidin onto that glass. As many of you might know, streptavidin and biotin have one of the strongest affinities known to man, so when we run biotin-related DNA through this device, we can be able to affinity capture it. After that, our next step is to characterize our device. For this, we use two main methods. We use fluorescent microscopy, which is a little bit more of a broad method, and then to learn a lot more about our device, we decided to use DNA extraction, which I'll go into further detail about. And that's what our surface functionalization looks like. So our first step was our wafer fabrication. So we went into this summer already knowing how to fabricate a single layer on a silicon wafer. It's pretty simple. We were able to get pretty consistent looking channels. The only issue came when we decided to add in a second layer. We had both never really done microfluidics, both being my mentor and I, so we had a little struggle getting the clear channels that we wanted to. Our first method was to try and develop both layers simultaneously, but we actually ended up with really muddy channels. If you see on the edge of this channel these bulging features right here, this is really unusable, and this was formed because of really bad alignment during our exposure step of our photolithography. So by talking to some really great CNF staff members over at Cornell University, we decided to take another approach to our photolithography step, which was to treat each layer individually as its own entity, meaning that we just do the same steps for photolithography twice. And we ended up with these very clear channels, and we were able to optimize this photolithography step. Okay, so this is just a side-by-side comparison of what our channels look like. Oh no. Of what our channels looked like before we changed our method and after we used another approach. So after that, we were able to actually construct our device. This right here in the middle is what it looks like. You can't really see the herringbone structures from afar. They are only about 20 micrometers thick, but this is what a completed device looks like. After this step, we moved on to our surface functionalization. As I said before, the goal of this step is to immobilize streptavidin onto our glass substrate. So we first started with a glass substrate, and we coated it with Aptase, which is a silane chemical. And when we coat silicon-based substrates with silane chemicals, we're able to expose chemical groups. We exposed the amine group, and we were able to add a chemical linker in the form of an aldehyde. Using this chemical linker, we were able to covalently bond streptavidin to the Aptase, and once we covalently bond streptavidin onto the Aptase, we go back and we block all of those unreacted surfaces with inert proteins. This is to try and combat all of that non-specific binding, which is unfortunately pretty much inevitable. But then after we're done with this, we're able to flow our sample through, and ideally we should be able to capture biotin-related DNA with this. So our next step is to validate that this protocol actually works. We first started with fluorescent microscopy. We functionalized a device, which is what this image is right here, and we flowed fluorescent biotin through it. Ideally, we should be able to see these bright fluorescing spots, which we correlated to us immobilizing streptavidin in that spot. As a baseline, we also imaged a blank slide, and you can see these little bright spots, which is the non-specific binding that I mentioned before, which is unfortunately inevitable. But we were able to see that vaguely our functionalization protocol worked. So we moved on to the next more intricate validation, which is DNA, which we use DNA gel extraction and DNA gel electrophoresis, which I'll explain a little bit more. But for this step, we first started with a DNA ladder. And for anybody who's not familiar with this, a DNA ladder is basically a premixed collection of DNA of multiple lengths. We don't need all of these lengths, so our next step is to run this DNA ladder through a process called DNA gel extraction. We go in through our DNA ladder, and through a multitude of steps, we're able to pull out different lengths that we would actually like to use. So when we pull up our 2 lengths, we're able to either biotinylate it using a literature protocol, or we can leave it non-biotinylated. For example, my mentor and I, we biotinylated a 1,000 base pair length of DNA, which basically means it's the DNA length made up of 1,000 base pairs. And we also pulled out a 500 base pair DNA length from our DNA ladder, and we chose to not biotinylate it, just so that we can have a mix. We then take this DNA and we combine it. And when we combined it, we ran it through our already functionalized microfluidic devices. So we should be able to only pull out our biotinylated DNA. And then we collected the flow through that came out of the microfluidic device. Once we collect our flow through, ideally this flow through shouldn't have any of that biotinylated DNA, as I mentioned earlier. Now, for the actual experiment, my mentor and I went through this entire process and we pulled out different samples from the entire protocol, and we ran it through a DNA gel extraction. A quick overview of what DNA gel electrophoresis. You basically put your sample through in these wells up here, and you run a current through it. And this is going to pull the DNA across in this downwards motion. All the heavier DNA is going to end up here, and all the lighter DNA of the shorter base pairs is going to end up down here. To start, we put our DNA ladder through this DNA gel electrophoresis, and we did that because we already know exactly where our DNA is supposed to end up, because this is our baseline. And then we added that combined DNA into another lane. So our combined DNA should only have 2 lengths of DNA. So this would validate that our DNA gel extraction actually worked. And then we took our flow through from our microfluidic devices, and we also ran it through a lane. Ideally, we should only have the non-biotinylated DNA, and that's why this experiment would be really helpful to characterize our device. And then just to see what we could learn, we took some DNA ladder and we ran it through our microfluidic device, and we ran it through the gel electrophoresis. We just wanted to see about how much non-specific binding we're actually getting at this stage. Now, the really cool thing about this is that we can actually take this gel that we used during the electrophoresis and we can image it and quantify the different bands. We run it through a microscope, and they look at the intensity of the bands, and they can correlate this to the amount of DNA contact that is specifically in a specific band. And we realized that this is actually a really great method that we would definitely be using in the future to characterize our device. Unfortunately, the numbers that you're seeing on the screen right now just shows the very lower limits of our device use, because we weren't able to set up a full engineering system of what our device can actually do. In the future, what this would look like is we would set up a multitude of syringe pumps so that we can implement oscillatory washing for our device. This is basically swishing our sample around in our device so that we can capture as much DNA as we can. But that is in the future works. Okay. Yeah, and these are my acknowledgments. Special thank you for the CNF staff that helped us with our photolithography step, and my mentor, Jack Crowley, and my PA, Dr. Warren Zipfel. And I'd be happy to take any questions.
Hello, my name is Giancarlo Solano. I am with Montana State University, RU. I wanted to ask a question, or more so that if you could specify what you meant by targeting the microfluidic channels one by one. I wasn't exactly sure what you meant by that, and how you said that you went from having a poor design due to poor contact alignment, but then you then mentioned that you took it a step one by one. I was wondering what you meant by that.
Yeah, sure. If this would go faster, that would be great. It is not. Okay, well, as I'm waiting for this to go back to the slide, what I meant by going back and forth, are you talking about this slide right here? Okay, so the question was specifically how we went from our first method of photolithography to our second one. So when we were trying to add the 2 layers, trying to do multi-layer photolithography, we didn't go into the summer knowing exactly what that process would look like. So my mentor pulled a literature protocol for doing 2-layer photolithography, and the orange steps that you can see here, where after we expose the first layer with a contact aligner, we spin the second layer. So we're trying to develop the 2 layers at the same time. So we do a final developing at the end, and then we should have our 2 layers perfectly fine. But the only thing is that it wasn't giving us any channels that we could actually use. These are really muddy, and it's kind of like if we want our layers to be on top of each other, what this is showing is that our layers are like this. And you can't run a sample through that because you wouldn't really collect anything. There would be spillage. It just wouldn't work for a microfluidic device. So that's why we decided to just do the 2 layers on top of each other, which basically means we spin our photoresist, we expose it, we develop it, boom, we have 1 layer. And then once it's all clean and dry, we add some more photoresist and we do the whole process again twice, just kind of like pretending that the first layer isn't there. And we were able to get these really clean channels. Yeah.
Anyone else? Let's thank Erica and all of our speakers one more time.
Hello, my name is Zainab Ismail. I'm a physics major at St. John's University. I'm part of the CNF RAU program for the summer. My mentor was Giancarlo D'Orazio, and my PI was Sadaf Sobani. This summer I've been working on printing functional gas diffusion layers for carbon dioxide reduction reactors. Our motivation for this project is that while we constantly burn fossil fuels to extract energy to use in major industries, what we're not taking into account is how much carbon dioxide we're releasing into the atmosphere and how much harm it's causing to the environment in the form of climate change. So our goal is to
try to recycle carbon dioxide back into those same exact chemicals and fuels we derived them from by using electricity as our energy source. We do this using a carbon dioxide reduction reactor. A generic 4-compartment CO2 reactor consists of 2 gas compartments and 2 electrolyte compartments. The device is constantly being pumped with CO2 and electrolyte. We have 3 electrodes and 1 ion exchange membrane. The black square on the right side is the anode, where water oxidation takes place and releases electrons, which pass through the ion exchange membrane, the yellow square in the center. Afterwards, going through and passing onto the cathode, which is usually any porous membrane covered with a catalyst. And what happens on the cathode is that you have the carbon dioxide meeting the electrons, and the carbon dioxide is reduced into the products that we want, the hydrocarbons like methane, ethylene, carbon monoxide, and these products are then pumped through to the gas chromatograph to get quantified. Our specific device uses instead a 3-compartment design, 1 gas chamber and 2 electrolyte chambers. And all these pieces, the 3 chambers, were made by an SLA printer by another person in the lab. The anode we use is a platinum mesh, and the ion exchange membrane is a Nafion ion exchange membrane. And the main focus of our project is producing the cathode. And the cathode is, usually it consists of of carbon paper or any porous membrane sputtered with a catalyst. Okay, my role in the project instead is to produce our own gas diffusion layers using a 3D printer called the NanoScribe. And why we want to do this is because we want it to make it more customizable. And the carbon paper, although it works for a lot of other reactions, it's not very stable in the CO2 reactor. So what we want to do is print out these gas diffusion layers, which are about 10 by 10 millimeters and 400 microns thick. Afterwards, we would print the adapters, which are basically supporting pieces to help us mount the gas diffusion layer into the cell. And then we would coat the gas diffusion layer with copper and incorporate it into the already made reactor. And afterwards, we would run the cell, and using the gas chromatograph, we would quantify the gases that we produced, as well as using a potentiostat to collect data like the IR drop, and as well as the cyclic voltammetry scan. The tools that we use, the most important one is the NanoScribe tool, which we use to print the layers. It utilizes a femtosecond near IR laser that sweeps across the resin and cures it with 2-photon lithography. It has a resolution of less than 1 micrometer, and the resin that we used in this experiment is IPS resin as well as the IPQ resin. The second printer we use is the the Objet 30 printer, which is a polyjet printer that prints UV curable polymers that are very similar to acrylic. The resin that we used is the VeroClear resin. This printer is just used to print the secondary pieces that we need. And the other tools we use is the AJA sputter machine to coat the gas diffusion layer with, and the SEM to help analyze our gas diffusion electrode. The general workflow for the NanoScribe printer is we create a CAD model and generate an STL, and using Describe, our slicing software, we would slice the STL, and we would prep the resist and load it into the printer. After the print is done, we would unload it and clean our sample using PGMEA and IPA, and then we would inspect the sample. To get more acquainted with the printer, we did some related research. We did contact angle prints, which is, we printed 5 millimeter by 5 millimeter flat prints of about 200 micron thickness. And we would just take contact angle measurements and use it to make 3D models that would help us predict whether the sample is likely to flood or not. Other prints that we did are proximity effect prints. We just printed microchannels onto a wafer and manipulated different functions to see how we can minimize the proximity effect. And lastly, we tested a new glass resin called GP Silica for applications in microfluidic devices, like, for example, the gas diffusion layer. Going back to the main project, we created several designs, but first of all, we generated a full-scale GDL that's about 10 by 10 millimeters and 400 microns thick. It was too computationally intensive, though, because Describe Slicer can only handle files about 2 gigabytes, and our design, our full-scale design, in its lowest quality was 6 gigabytes. So we had to formulate another design. What we basically did next was we took a 16th of the original size of the layer, and then made one STL file and multiplied it over multiple times with overlap to create a full-scale layer. And we also have a support beam on the back of the layer to just strengthen it a little bit more. And we use our first GDL sample was printed with this design. Specifically, we used a 16 by 16 array, and each of these blocks are about 625 by 625 microns, and the whole layer is 100 microns thick. As you can see here, it's not supposed to be looking like that, kind of like a triangle. It's supposed to be like a full square, a full dark square. The layer itself was peeling off the support beam and off the wafer. So what we tried to do next is that we generated another design. We generated a 2 by 2 array and layered them on top of each other. Each array was about 100 microns thick, so we layered it 4 times. And we printed out a sample using the IPS resin. And this is the results that we get after development. The sample was not only peeling off the wafer, but the layers weren't adhering to each other at all. So we started questioning the suitability of the IPS resin that we've been using so far. And originally we chose it because it was our freshest available resin and that it was not sensitive to overdevelopment. But we see that we had to make some sort of change, so we changed, for our next print, we printed with the IPQ resin, and this took about 25 hours to complete. And as you can see, there was no uneven discoloration or no separation of the layers whatsoever. Although it looks dark in the picture, it's actually supposed to be a transparent sample. Afterwards, after developing it, we removed the sample off the wafer by soaking it for 30 minutes in IPA and sonicating it for about 10 minutes. And then we placed it on a hot plate for 20 seconds and then a cool plate about twice, and it just popped right off the wafer. Afterwards, we attached the gas diffusion layer to the adapters we had printed earlier using the Objet 30. We glued them together and used a UV light to make it stick, and then we sputtered them with an AJA sputter machine with about a thickness of 245 nanometers. And then we incorporated it into the rest of the cell. And unfortunately, our gas chromatograph was not working, so we couldn't exactly get how much of the gases we were producing or quantify that data, but we did have a potentiostat, and we got this graph. Specifically, this is a cyclic voltammetry scan. What it's supposed to tell us is that how much you manipulate the potential and you see how much the current is changing. Ideally, you want to see several peaks on the graph to see that there's an actual electrochemical reaction taking place. As you can see, we don't have any actual change in our current until about negative 1.2 volts, and then you can see a little curve. So that lets us know that there is some sort of reaction taking place, but there are some issues. And while consulting another lab, they said that there must have been some sort of problem with copper adhesion. It wasn't adhering well to our sample, and maybe trying using a different metal to help it adhere better. And we also discovered that it has a very similar IR drop to a conventional gas diffusion layer, and that our cell actually did not flood. Our conclusion is that through the lengthy process of designing the layer, printing it, and running it, we were able to produce a layer that has a very similar IR drop to a conventional GDL on the market. And our next steps would be to try to coat our printed layers with a hydrophobic coating of Teflon. There was time constraints, so we couldn't do that. What we would want to do ideally is cover it with a hydrophobic coating and then sputter it with copper and perform further analysis using the SEM and see if that helps with the copper adhesion. And then we would run it again with a working gas chromatograph to get more data. These are my acknowledgements. Any questions?
Do folks have questions for Zena? Sorry, trying to see the room.
I have a quick question. I'm Ryan. I was just wondering, how long did the IPS prints take you?
It was about the same time. Basically how long, in comparison, the IPS resin samples took to print. It was about the same, about 25 hours.
Was it the same print?
Yes, it was the same exact print.
Thank you.
Other questions? I have one. What do you see as the future of this reactor if you get everything to work in the gas chromometer? Is it going to be on top of a smokestack or in water pipes, or what do you see?
The question was, where do we see the the cell being in the future, whether we use it on top of like a smokestack or in some other application. So far, it's still in academic realm, and we haven't really thought about it yet, and it's still a very small-scale project.
Thank you.
Thank you.
Other questions? All righty, thank you, Zine.
Thank you.
Thank you, folks, for staying. You now really are officially on break until the next session starts. Thank you.
Thank you.
So you can just leave it.
Well, the other, yeah, go ahead. Watch. What I'm going to do is also keep track, and then I'm going to, not to make it, we have 1 minute left, so the 7-minute mark, very quietly, I'm just going to do this, and as long as you don't go like 10 minutes, you know, you'll see if it gets really, if it's like at 9 minutes, just start standing up.
Should automatically start. Just click anywhere.
Okay. Yeah.
It should automatically.
You got it? Great, Jessica, by the way. James, you're gonna do great.
Leslie.
Leslie. All right, I think we have one more, right?
We have 5 people in this section.
So James, you're going first.
Do you want me to, go out there and tell people that the session starts now?
Yeah, maybe. Well, I think they just announced they have a little break, so they probably.
It looks like the last edit was made to it.
Yeah, we had a break, and that was it. Come on back.
The 2 minutes, it's over now.
So James, you're gonna go first. Okay. Then Christina. Okay. And then Wesley. Good. And then we have Giancarlos and I put my own photo on. So good one. And then the fifth one is Maisel. We're looking for Giancarlos and Maisel. Do we know anything about Giancarlos and Maisel? I just saw them out there. See them in here. Oh, yeah, you're at Betty.
Oh, right now?
You're in this group, yep.
Oh.
We're waiting on you.
Sorry.
That's okay, we got one more. Maisel?
Hello, hello. Nervous as usual. Huh? Nervous as usual. Yeah. The good time is going to be after. Oh, yeah?
which does what? The tab one.
Yeah, try that once. There you go. Not bad.
Cool.
Okay.
Okay. Yes.
Right here. All right, everyone, we're going to get started. Thank you for joining us today. We've got James Gow up first, and he's going to share his presentation.
Hi, I'm James, and my project is on the development and characterization of fusogenic porous silicon nanoparticles for siRNA delivery for the treatment of retinal neovascularization. Okay, so some of the background. So proliferative diabetic retinopathy and diabetic macular edema are prevalent eye complications, and that cause blindness due to elevated glucose levels. So those are two pictures of a PDR and DME, and the current treatment is using anti-VEGF antibodies. So VEGF is vascular endothelial growth factor, and they target that specifically, and these are monthly intravitreal injections in the eye. The problem is repeat injections run the risk of inflammation, infection, and hemorrhage. Okay, so the goal is to develop a nanoparticle therapy for the in vivo delivery of anti-VEGF siRNA to the retinal neovascularization as a novel extended treatment for both PDR and DME. Nanoplatforms have the potential to increase drug bioavailability and sustain drug release, which also reduces the number of required injections and thus mitigating negative side effects. I worked on loading calcine using hydrocyclic silane into porous silicon nanoparticles. So calcine and siRNA loading is around 20 to 30%. And the problem with this method is that there might be some salt crystals in the reaction mixture, even after washing it multiple times. So it's hard to image the particles. The method using cyclic silane might result in a cleaner sample. And in the calcium silicate method, the encapsulation of the particles is mainly physical trapping, whereas the cyclic silane is mostly electrostatic forces. So this is a new methodology that's in the process of being made, and it also refers to previous research for other applications. So calcine is a fluorophore analog for a nucleic acid, the anti-VEGF siRNA, and this is used before using real siRNA. The silanes used are butylsilane and diazosilane, and there's 3 different approaches to loading porous silicon nanoparticles with calcine. So the first is just adding porous silicon nanoparticles with calcine and adding calcium chloride, and then having porous silicon nanoparticles with calcine and a silane in an organic solvent. And then the third is porous silicon nanoparticles added to silane, and then washing it, and then adding calcine later. So first I did characterization of my samples. I used dynamic light scattering, DLS, and FTIR, Fourier transform infrared, but there's some issues with my butyl sample, but I did get some data from my diazo sample. For DLS, I characterized the size and the charge. So the size for normal porous silicon nanoparticles is 217.2 nanometers, but the peak of the graph for my my diazo sample was 535.2 nanometers. And the charge for the zeta potential of the silicon nanoparticles should normally be around -20 millivolts, but after altering it, it changed to 13.2 millivolts. So these are my FTIR and TEM results. So FTIR is an analytical technique used to measure absorption of the infrared radiation of the sample material versus wavelength. And then the TEM is used for, it uses transmitted electrons to create an image of the particles. So those 4 images are all at 6.5K magnification. And on the left side is cyclic silane modified porous silicon nanoparticles. And on the right side, there are unchanged nanoparticles. So, and there's a scale bar at the bottom right of each of those, but it's pretty small images. So I did a 24-hour study for release of the calcine and I recorded at intervals of 2, 4, 6, 8, 12, and 24 hours. And I used the ID5 absorbance to measure the absorbance. And I converted that absorbance into concentration using a standard curve for the original calcine solution. And then the graphs shows that the concentration of calcine released over time. And after reaching a certain point around 6 hours, they both plateau. For the preliminary release study, it seems that both that the diazoxylane initially released more than the butyl, but then they both just level out. And then for future directions, I would like to use siRNA instead of calcine, so using the real deliverable in the experiment might show more accurate results. And using an eye chamber instead of centrifuge simulates the flow of a real eye, so it's more accurate as well. And those are my acknowledgements.
Anyone have any questions for James?
Could you go over one more time, the role specifically of adding the SINE as well, beyond just the calcine and the porous nanoparticles?
Can you repeat your question?
Yeah, in terms of the role of why you have all three of them, you have the nanoparticles, obviously the calcium encapsulating, and the role of the SINE.
So for this one?
Yeah.
Okay, so the role of the nanoparticles is to be the deliverable. So it will be encapsulated inside of a lipid for delivering into the cell. The calcine is to simulate the siRNA, and the silane and the calcium chloride are just ways of introducing that calcine into the nanoparticles. Okay.
Any other questions? All right, one more round of applause.
I've never used the clicker before. Which button is it? Okay. Yeah. Oops. Oh. Okay. And is there a laser pointer? Okay. Thank you.
All right. I'm going to let Christina introduce herself. Tell us about her project.
All right. Good morning, everyone. Thank you for giving me some of your time this morning. My name is Christina Villalba, and I'm a current undergraduate chemistry major that lives in San Diego, California. I'm representing the San Diego Nanotechnology Infrastructure, or SDNI program, and today I'm going to be presenting my research on SARS-CoV-2 enzyme, or MPRO, detection with a matrix and sensitive nanoplasmonic platform. So some of the overarching discussions that I wanted to cover today include colorimetric rapid disease biomarker screening, just what they are, why they're important, as well as nanoplasmonic materials. Then I wanted to go into two main topics that I wanted to drive home today that are peptide-induced fractal assembly and thiolated PEGs. Lastly, I wanted to cover my personal contributions to this project, including my results, and then wrap it up with the future directions that I'm hoping to take, or I would take if I had more time this summer. So to begin, what is colorimetric rapid disease biomarker screening other than a mouthful? In my own definition, I just like to describe it as virus detection that's conveyed through a change of color. And you might be familiar with a common type of colorimetric screening, which just so happens to be involved in some pregnancy tests. So you may notice on that figure over there, we have two blue lines. One of them is way darker than the other, and that's just a colorimetric signal to detect pregnancy. So it's particularly helpful for two main reasons. It is competitive against polymerase chain reaction, or PCR testing, which is kind of the current gold standard for virus detection, and also enzyme-linked immunosorbent assays, or ELISA, which are expensive, they're time-consuming, and they require quite a bit of training for operators to be able to interpret them. If you've ever had to pay out of pocket for a PCR test, it can be quite pricey for many working Americans, ranging anywhere from a couple $100s. So we're hoping that this process is going to eliminate or at least challenge some of those issues. So now I wanted to transition into going into some of the basics about nanoplasmonic materials. So these materials are very interesting in the sense that they interact with light much more efficiently than any carbon-based dyes. And then this trait is pretty much due to a localized surface plasmon resonance, or LSPR band, in the visible region that's very sensitive to traits like size, shape, and dielectric environment. As you can see to the figure to the right, these are modeling silver nanoparticles in particular. I use those in this study. And you can see how they range from a series of different colors based off of their size or how they move through electric fields. Common nanoplasmonic materials do include the silver, like I mentioned, but also include gold, and they're usually found in spherical shapes, but they come in other varieties as well. So how does all of this background information come together? Well, the two main topics that I wanted to cover today include peptide-induced fractal assembly and thiolated PEGs, which I'll cover in a minute. So in peptide-induced fractal assembly, you have these nanoplasmonic structures or nanoparticles that are in solution, and we're also dealing with something called a peptide, which is just a string of different amino acids that would be used to create a protein. So when this peptide is cleaved by a protease, or something that an enzyme that attacks peptides, it does so at a certain link within those amino acids. So you can kind of think of them like beads on a chain. So picture you have a pair of scissors and you cut it at a certain space in between these beads. Well, when that happens, the nearby nanostructures, they kind of spark off into these new structures, and they form these kind of like snowflake-looking structures over here. That then produces a color change, so you'll go from something like a yellowy color all the way over into the indigo violet section. It's very easy to see, so it's pretty clear to see if you've got any virus present. The only thing about this methodology was that it wasn't able to function in various media, so instead we came up with doing an adaptation and instead focusing on thiolated PEGs. So with thiolated PEGs, it's a very similar process to the peptide-induced fractal assembly, but instead we're going to be focusing on the anchoring groups that those PEGs have, which would be the thiol. So in the figure over here, you can see this sort of squiggly line in an anchoring group and the squiggly line in an anchoring group, and that's just representative of the PEG and the thiol group that we're focusing on. So you're going to have this cleavage over here, just like I mentioned in the last slide. And when that happens, the pieces that are detached after the cleavage, they start to interact with these aggregated particles. So in this case, it would be the silver particles. And when that happens, these particles are going to disperse or disassemble, and they're going to basically be free-floating in this biological media. And when that happens, you'll get the color change that we were seeing over here. So it'll go from either blue to yellow because they're starting off as aggregated, and they're going to be dispersed in yellow. Some of the advantages to this were mainly what I talked about in the last slide, which include their reliability in a multitude of biological media. So we were able to stray away from just focusing on studies in water and instead go into things like urine and blood, bile, etc. So now kind of going into the meat and potatoes, more into my results for this project. One of the things we wanted to investigate with the thiolated PEGs was their size in particular. So just a little bit of background information first. You might have heard me mention dissociation and aggregation in the past slide. So
aggregation occurs at an absorbance of around 620 nanometers, and dispersion occurs around 400 nanometers. So when I'm referencing absorbance as a ratio on this y-axis over here, I'm just taking the fraction between these two absorbances. And then also on the right side, you might see that 20K, 5K, 2K, and so on. Those Ks just stand for 1,000. So 20K, for example, is just 20,000 grams per mole for that peptide. So very, very long chains of these PEG molecules. Our results show that as we neared the 1K mark, that's when we reached optimal dissociation. So we're starting off pretty low down here with the black, moving up with the yellow, and then we're shooting up all the way over here with green. I also chose to do a trait or a variety that was lower than 1K, so with the 0.5, you can see we're decreasing in those rates as well. Another thing we wanted to investigate with this project was studying the dissociation rates with varying PEG composition. So instead of using thiol as the anchoring group, we went ahead and studied things like lipoic acid, alkene, and hydroxide. But very quickly, you can see that all of those varieties pale in comparison to what we studied in the last slide. So it just goes to show that thiol was very crucial in this dissociation step. Lastly, for future directions, if I had more time this summer, I would have loved to investigate the effects of nanoparticle shape and orientation. Everything we used was spherical shape and silver over here, but they also come in varieties like nanorods, nanocubes, zinc oxide, alloys, etc. The list just goes on. And we're also hoping to employ this type of methodology in studying other health crises, like maybe gingy pain activity in mice, because it's been recently studied that there's a link between gingy pain and Alzheimer's disease. Then I just want to take a couple seconds to acknowledge the copious amounts of help I've had this summer. It's been very tough, but I wouldn't have been able to do it with my mentors, and particularly Dr. Yves Thériault, my mentor every day in the lab, Dr. Maurice Ritou, and thank you all for giving me some of your time this morning. Are there any questions? Sure.
So what were some of the difficulties you experienced with some of these, I guess, applications of these things?
Okay, so the question was, what were some of the difficulties that I experienced this summer? And I could go on with so many, but so unfortunately, a lot of my undergraduate journey has been online. So this was my first time stepping into a professional lab. And my first week involved so much pipetting and to the point where I was trying to get like half a microliter into like a 384 well plate. So I definitely learned how to spot that tiny amount and also work with like very small amounts of reagents, because sometimes these materials can be pretty pricey. Yes?
So were you able to test like efficacy and things like that in terms of like relative sensitivity, or is that something that's going to work in the future?
Okay, so the question was regarding were we able to test efficacy in the study? I believe we did. If I'm answering the question or approaching it correctly, I think the efficacy that we studied was pretty much with this PEG size. So we were trying to see what is like the optimal parameters, at least in that regard. But I'd love to go further in depth and then just do like cross-relational studies and see what's the perfect recipe for this association.
One more round of applause for
Awesome.
All right, hello everybody. My name is Wesley Chu. My home university is at University of Arizona, and this summer I was working at the Shine RU at Northwestern University. My project's on the development and fabrication of silicon nanostructures for mechanobactericidal applications. So just a quick overview of my presentation today. I'll go a little bit of background of what are mechanobactericidal surfaces, why should we care about them, and then my research goal, which is to identify optimal process parameters for creating some of these surfaces for future studies. And then a little bit of my methodology, which mainly involves electron beam lithography and reactive ion etching. And then my results, which consist mainly of SEM image analysis, and then some conclusion and next steps. So first off, there's obviously bacterial infections and diseases caused by them are a big problem, specifically in food safety and medical device and implant realms. This is exacerbated by the formation of bacterial biofilms on these flat surfaces, which increases their survivability and further exacerbates problems with superbugs and antibiotic resistance. So one of our questions is, how do we prevent the formation of these biofilms, and how can we kill these bacteria? So studies of naturally occurring bactericidal surfaces have actually revealed detailed nanopillars. One of the big earliest examples is on insect wings, specifically in cicadas and dragonflies, where they noticed that you could study these wings, and as a bacterial cell attempts to settle on these nanotopographies, the cell is actually lysed as it tries to adhere to the different pillars. So synthetic biomimetic nanostructures have been explored, but mainly in very unstructured arrays with non-specific etching. What this means is they don't really have much patterning, specific patterning done. They'll perform etching and kind of just hope for the best, kind of tweak those parameters and be like, all right, we got an array. Kind of like this feature shown here, where you have a lot of different pillars here, but it's not very uniform. And the exact mechanism of this bactericidal activity and the effectiveness of different nanofeature geometries remains relatively unexplored. So my goal is, how can I create some of these more ordered nanoarrays in order to study exactly what geometries will provide the most bactericidal effectiveness, right? And how do we create those in a very controlled manner? So my research goal is to establish a lot of these optimal fabrication parameters to create an ordered nanopillar arrays for future mechanobactericidal studies. So I'm going to be fabricating some nanostructures with geometries that have been shown in literature to have bactericidal effectiveness, and then considering the patterning and etching parameters to achieve a high level of control. So quick overview of methodology, there's three main steps. The electron beam lithography and reactive ion etching consists of the fabrication steps, and then the SEM, I use SEM for most of my imaging and characterization. So I'll dive into each of these a little bit more now. So first off, electron beam lithography. If you guys are familiar with photolithography, it's very similar. You'll have a resist layer on top of our substrate, except in this case, instead of using light, we're using an electron beam. And the main advantage of this is that we can get a much higher level of resolution. So our beam spot size can be down to maybe 5 to 10 nanometers. And this is really important because we want to create these really small nanofeatures and nanopillars that have been shown to have this activity. Specifically for electron beam lithography, you can see here, it's pretty similar. Just have areas that are exposed, and then we develop it. We wash away the non-exposed regions, and this will prepare us for our further etching. In this case, I use an HSQ negative resist pattern. One of the main things for this is that the optimal parameters vary based on the pattern, right? So whatever pattern you have, the exact parameters that you need to get your end result that match up your initial design really depends on the pattern, right? You can change the interpillar spacing, you can change the feature diameter, and these things will all affect what kind of parameters you need. So in my case specifically, I'm focusing on the dose, right? So you can see in this figure here, you have underexposed, overexposed, and properly exposed resist features on your pattern. You can see that since obviously development is based on solubility, depending on how much electrons per unit area that you're shooting into your resist, that will develop it a certain amount. And so I will be varying the dosage across these different things and finding the optimum dosage. And so for reactive ion etching, this is just a quick overview. We're accelerating ions into our substrate to etch into our actual substrate. In this case, I'm using silicon. This is kind of a continuation of my figure here. Obviously, we have a resist here. After etching, we'll actually etch into the silicon on the bottom. And then we commonly use SF6 and fluoride chemistry to take advantage of that, which is what I'll be using. And my main goal with this is to identify an anisotropic etch recipe that provides clear pillars at this specific scale and for these patterns. And for the last part, SEM imaging, I'm using SEM to image my resist after my patterning from electron beam lithography, and then image my etched pillars and measure their height as well. So since this is largely exploratory, a lot of this will be kind of just saying, hey, there's our feature diameter, for example, match up what we input. For electron beam lithography, the main advantage is that you can just have a CAD design, import that, and then it should raster exactly what you want onto your substrate. And then I'll be evaluating mainly qualitative stuff, and then future work will mainly involve more quantitative analysis. So onto some of my parameters I'll be using. So you can see this is the design. So for the interpillar spacing, I had 100 nanometers in between them, and then various feature diameters. These are kind of just some ranges that were established in literature that have shown to have some bactericidal effectiveness already. And so for my electron beam lithography, I'll be varying the dose from around 500 to 3,500 microcoulombs per centimeter squared. And then for etching, I was able to identify 3 etch recipes for the scope of this project, varying the oxygen flow rates and pressure from a base recipe, establishing how that will affect our etching into our final nanopillar geometries. On to results. So all of my results pretty much consist of SEM images and then measuring through the SEM exactly what my feature designs look like, in this case for my patterning analysis. And here you can see the measured diameters as well as the intended diameters of each of these patterns from 50, 75 to 100. From here we can see that we were able to identify an optimum dose that gave us clear patterns that match up with what we intentionally designed. And so this graph actually goes through the specific optimum doses that we identified for each of the feature diameters on the x-axis. And this shows that the optimal dose decreases with a larger feature diameter. And this is kind of what we expect, right? Because as we have more dense patterns, for example, we have a larger feature diameter here, you have more scattering as you're exposing with your electron beam. And that means that you'll develop it with less dose in terms of that specific feature. And as for our etch analysis, I tested recipes A, B, and C. Unfortunately, recipe B had pattern collapse in which our pillars kind of just fell over and became very non-ordered. So they're not shown here. But for A and C, you can see for A, we have relatively straight pillars, which is what you want to see. For anisotropic etch, obviously we want to etch just vertically. So we have these straight pillars across these 3 varying feature diameters. For recipe C, however, we can see we have a little bit more isotropic etching as we have a wider sidewall angle here. You can see specifically on recipe C for the 100 nanometer features, we have a bit of an angle here in terms of it's more of a cone rather than a pillar. So in conclusion, we were able to identify a proper exposure dosage for a few different feature diameter patterns. And we were also able to identify an anisotropic etching recipe for generating these nanopillar arrays. So some of our next steps would mainly be to actually test the bactericidal effectiveness of these. I didn't have access to any biological samples for this project, but that would definitely be the next step to say, hey, we identified these things in literature. Can we now test them and make sure they actually work? And from then on, study more patterns and different etching recipes. There's been a wide range of different studies that have kind of explored different types of spacing, different feature diameters, and also for etching, can we maybe maximize our etch rate while maintaining our anisotropic profile? And so a big kind of gap within that literature, kind of building off of this, is a systematic review of what types of nanofeature geometries correlate to the strongest bactericidal effectiveness, right? So a systematic review of that, such as a design of experiments where we have a factorial design, where we can maybe explore 2-level factorial design and identify which specific parameters have the strongest effect on bactericidal effectiveness would be the main next step. But yeah, thank you. Any questions? Yeah.
Yeah, so for your applications or proposed applications, what sort of etch depth or aspect ratios were you looking for, and what did you achieve?
Yeah, so the question is what kind of etch depth or aspect ratio was I looking for within my methodology, and which ones did I achieve? For this, if I can go back, maybe. I don't have the heights on here, but they are on my poster. I think the aspect ratio was around 3 or 4. It also depends on the specific diameter, obviously, here. And then in terms of literature, some of the ones that I've identified were specifically around that range as well. But a lot of it really is, you can obviously vary the etch time as well to achieve those aspect ratios. And in this case, I was able to reach around, I think, 3 or 4, and then it could probably etch a little bit more to go even further. But that's also one of the things, there wasn't a big consensus within literature either into exactly what height. It seems like there's kind of a discussion of maybe a sweet spot where you don't want it to be too shallow or too deep, and trying to find that area. So that's why I mentioned that's one of the definitely big steps in the future. Is there another question in the back? Yeah.
So I know traditionally cicadas are known for having like the bactericidal nanopillars.
Mm-hmm.
Those are usually cone shaped.
Yeah.
Is there a reason for going for the more like cylindrical geometry, like in pattern A? Like, did you guys hypothesize that maybe that would have more bactericidal effect than the traditional cone shape?
Yeah, so that's something that I wanted to try exploring as well. Shape, like you mentioned, is definitely something that might be a factor as well. But that's just one of the, kind of going back to, one of the big gaps in literature is there's not big consensus on exactly which ones are the most important, right, and which ones will have that effect on the bactericidal effectiveness. But that's definitely something to be explored in future etching recipes as well. That's also something I struggle with in terms of, can we really actually get control over how much the sidal angle is, what is that conical shape, and how can we achieve that? Yeah.
I also had a question on the bactericidal effects.
Mm-hmm.
So basically, do you and your team consider maybe how with this design, how effective would it be at, say, harming the cicada or harming a human? Because I'm sure this is all be
Mm-hmm.
used to test on humans
Mm-hmm.
later on. So what was that like?
Yeah, so the question was, obviously the end goal is to use this in a human context, and did we consider kind of what effects this would have on the human body? So one of the interesting things that literature has actually shown is that because of the size differential between bacterial cells and mammalian and eukaryotic cells, this will actually only kill bacterial cells. So it's been shown to actually not have any detrimental effects on mammalian cells. And in some cases, there's actually been studies on encouraging growth. So that could also be an issue in the context of like medical implants where you're encouraging growth where you don't want it. But I don't think the technology has really reached that stage of maturity yet to really consider the exact implications inside the human body. Thank you.
Yeah.
Yeah?
Yeah.
Sure? You can correct me.
No, it's perfectly fine. Okay. Right. Good. Okay. All right. Okay. Thank you.
All right. Excellent. Thank you, everybody. Giancarlo is going to introduce himself and tell us about his project.
Hello, everyone. My name is Giancarlo Solano. This summer, I went to Mount St. Anna State University to work with my mentor, Dr. Andrew Langley, to find alternative developers in photolithography. As you guys may know, photolithography has many applications that can be used. And I'll say this, my project is kind of a step back from typical applications. It's more so just looking at the development of photolithography. So, as everyone may know, just general overview, photolithography is a microfabrication process used to create micro or nanoscale patterns with light-sensitive material, also known as photoresist. One of the many common applications of photolithography is specifically in semiconductor manufacturing, and a lot of the devices we use are consisting of manufacturing semiconductor manufacturing devices. One of the main issues with photolithography is that it can be dangerous due to the use of harmful chemicals such as tetramethyl ammonium hydroxide, otherwise known as TMAH. So here are some examples. I think this convention has shown us that there are a multitude of uses with photolithography. But my research question for this summer was, can the results of standard TMAH development with NR9 1500py photoresist be replicated using safer, non-aqueous developers? Obviously some keynotes, obviously commonly used photoresist developer. TMAH is also incompatible with some substrates and wafers because it is an extremely corrosive base, and TMAH is extremely toxic for humans, and alternatives would decrease hazards in the workplace. Here's a general overview of the process. I've been aware that everyone has a different kind of approach to the photolithography process, but this was the one I specifically utilized over the summer. So over here we just have the natural coating the wafer with the photoresist, applying a soft bake for adhesion of photoresist. We apply the UV light to induce a chemical reaction. Then we have a post-exposure bake to decrease the solubility of the exposed photoresist. And then we apply the developer, which is the main step I'm focusing on, to create the exposure pattern. And then finally we observe the final exposure pattern. So here are some of the dangers of TMAH. Over here we have the general hazard pictograms that are usually in most of the TMAH SDS sheets or safety data sheets. And some of the dangers, if exposed to, include failure of neurotransmission in the body, otherwise meaning failure of brain signals being sent to certain organs. And that directly may result in respiratory and cardiac failure. Additionally, since it is a corrosive base, we might deal with severe chemical burns and severe nerve damage. Wu et al. Reported that TMAH exposure could result in death within less than an hour. So for the methodology of this experiment, it was just basically revolved around using preliminary results to further inform other experiments, and some of the experimental parameters that we changed were exposure time, post-exposure bake temperature and time, development time, and development solutions, and a lot of the characterization was made with the optical microscope and the scanning electron microscope. The developers I was using this summer were acetone, isopropyl alcohol, and heptanone, which are all significantly safer developers than TMAH. Although flammable and might irritate skin, they are far less dangerous than TMAH. Here's just a quick overview of some of the tools that I used this summer. This was a plasma asher to clean my substrate. I used this to spin coat the photoresist. I use these for the thermal steps, and this was the ABM contact lens tool for exposure. And now getting to the results. So acetone proved to be too strong of an organic solvent for the photoresist. For most of the features, a lot of the issues that were dealt is that it was either dissolved or hollowed out, as shown as this box feature below. Then this is a general chart for isopropyl alcohol, where we see just general success rate, or just general success with a lot of these post-exposure temperatures and exposure times. Isopropyl alcohol, although able to develop exposure patterns, these exposure patterns were not ideal due to some of the streaking that occurred. The image over here shows some of the streaking that we can see over here. This is because isopropyl alcohol was not strong enough to dissolve the photoresist in the unexposed areas, so it caused these streaking effects. Now, for the most successful developer I used this summer, it was heptanone, providing some success rate in the 160 to 170 degrees Celsius region with between the 50 to 50 second exposure time region. It essentially provided good exposure patterns that were comparable to that of standard TMAH processing. For the lower temperatures, they were entirely dissolved, and higher temperatures had damage resist. So for some optical microscope imaging for the standard TMAH process, over here we just have a line scale of micron widths. This is just to show which is the smallest line feature that can be produced with this exposure pattern. This area is the silicon wafer, and this is the photoresist. On the right, we just have another image of a 2 micron line width scale, just to show just how it might look at a close-up angle. And just to remind everyone, a lot of these micron features are extremely small. Over here we have a hair strand compared to some of the micron line width features. And moving forward, these were the results that I was able to obtain with heptanone. Over here we have the 7, 5, and 4 micron line width features. And then over here we have the successful line width features from the 4 to 10 micron region. And some of the optical microscope image analysis included observing line width, edge roughness, pattern uniformities, and pattern deformities. So in this image over here, we can see that although there is uniformity amongst the line width, we can observe some edge roughness on the edge of these exposure pattern lines. And we can observe sort of pattern deformities amongst the exposure pattern with these line cracks on the photoresist. Moving forward, this was also another issue I was encountering with some of my results, is that there was a lot of dissolved photoresist in some of the areas, and essentially were deformities that caused issues and made an unideal exposure pattern. And here are some of the more successful exposure patterns that I was able to create. Over here we have no noticeable deformities, and over here we can observe that although there's no deformities, We have a consistent line width, but there is edge roughness. Moving forward, these were some of the standard TMAH SEM images. This is essentially what I was trying to replicate on the nanoscale or microscale. And this is the results that I was able to obtain. So when observing some of the SEM image analysis, we were trying to see if the angled edge was present, if there was photoresist smoothness, or if there was any edge roughness present. Just a quick thing about Enter-9 1500 PY photoresist. It is used for processes such as liftoff, which required that angled edge. Liftoff is just a cheaper way of doing etching, and it essentially just allows you to create a metal-based pattern. So here are some of the comparisons between the standard TMAH process and my process. Although we can see some deformities and not so much of photoresist smoothness, we can see that there's relative angle similarities, showing that there's some comparable features between these exposure patterns. Another thing that I wanted to point out was the consistency in the angled edge that was made or through this process. And my final recipe for the heptanone development was just sort of a pre-clean, step 1 being a pre-clean, step 2 being a spin coat at a 5,000 RPM for 5,000 RPM per second acceleration with a 30-second spin coat for 1 micrometer thickness. Then we have a soft bake step for 150 degrees Celsius for 1 minute. And we have exposure with no filter for 40 seconds with an expected intensity of 14 milliwatts per centimeter squared. And then we have a post-exposure bake ranging between the temperatures of 165 degrees Celsius to 170 degrees Celsius for 1 minute for the most optimal results. And lastly, we use a development with for 30 seconds using a heptanone puddle development technique with a spin coat at an RPM above 3,000 RPM, an acceleration of 3,000 RPM per second. So some of the conclusions I was able to deduce from this experimentation was that there are developers such as heptanone can be used for useful applications such as liftoff or Enter-9 1500 PY negative tone photoresist, in that it also can create comparable results. Some of the future directions that I would like to take with this research is heavier characterization, of course, and also improving the quality of the exposure pattern through a change of parameters and testing various other organic developers and another negative tone photoresist, and testing other exposure methods such as projection exposure. And I'm going to skip over the next slide real quick. Here are my references, and I'm open to questions.
Anyone have questions?
Back on that slide where you were displaying like the array of your results, I noticed that the one that was labeled number 2, it just looked like really different from the rest.
Oh.
Can you explain some of the reasons for that?
This one?
No, it was a little bit like before that. I think it listed like, yeah. Yeah, that one.
Oh, okay. So your question was, what exactly do these images mean? Well, at least to this right, this one looks different. So this one was essentially just a non-successful exposure development. A lot of the issues with photolithography, or at least when you're trying to find a new development method or changing certain parameters, there's always things that are essentially unpredictable. So this is one of those things. I wouldn't exactly be able to tell you why this occurred, but I did just want to point out that although this was something that did not work, we did have some functional exposure patterns from the 4 to 10 micron line width scale. So, yes.
Is there any particular reason you thought that heptanone worked the best, and any qualities that you think could inform future developers?
Okay, so the question was why I thought heptanone was an ideal developer. So essentially some of the issues that I wanted to point out, I didn't want to include images because they were just, some of them were entirely just ruined. Generally, one of the main issues with acetone was that majority of the exposure patterns were either dissolved or hollowed out features. This is typically what an exposure pattern would look like under an optical microscope, which is why I didn't do any further SEM imaging. And then over here, we dealt with streaking with isopropyl alcohol because it just wasn't a strong enough solvent to properly dissolve the photoresist in the unexposed areas. So the reason I wanted to exactly point maybe future researchers with this is with heptanone is because it created the most comparable results to that of TMAH. When comparing these exposure patterns, we can see that there's some similarities with no evident deformities that can be compared in these exposure patterns. So that's specifically why I wanted to specify the use of heptanone.
All right, that concludes our session for today. Oh yeah, here you are. Are you here? Yep, come on up.
I'm glad to. Thank you.
We have one more.
Okay. Okay, cool. That's good.
All right,
Thank
Phil's
you.
gonna share his presentation.
All right. Good morning, everyone. My name is Masil Malem. I'm representing the University of Connecticut. And this summer I've been doing research at Duke University as part of the RTNN, Research Triangle Nanotechnology Network. So the main thing that we explored is what's known as RIR Maple, and that's a novel deposition technique for perovskite thin films. So I know you guys heard a lot about perovskites throughout like this entire conference, but basically we're just dealing with like an ABX molecule. A and B are organic or inorganic cations, whereas the X is just a halide. Usually the A is +1 charge, the B is +2 charge, and then the halide is -1. For us, we're working with methylammonium lead iodide for the thin films that we're deposing, and then we're doing also organic 2D on 3D structures. So first, I'll talk a little bit about RIR Maple and explain how it works. The most common or the industry standard in terms of growing perovskite thin films is spin coating, also known as spin casting, which is like a type of chemical vapor deposition. RIR Maple is a type of physical vapor deposition. So specifically, this is kind of like a schema of what our process looked like. We have a target composition that includes the perovskite precursor, as well as DMSO, dimethyl sulfoxide, and then we combine with that a solvent matrix. So solvent matrix that we've been using is MEG. And what physical vapor deposition does is you're shining a laser at the target composition, and then you're making it evaporate, and the material goes up to the substrate and starts forming on the substrate a process called annealing, and the annealing can happen at a variety of different temperatures. So what we're doing that's a novel, or what my professor did that her contribution that is novel, is the RIR part of Maple, and RIR stands for resonant infrared. And what that basically means is the laser is fine-tuned so that the wavelength matches the wavelength of the molecules and the bonds in the solvent matrix. So the reason that's important is because once the radiation is shone at the composition target, the solvent matrix, MEG, exits out of the vacuum pump, whereas the organic material is traveling unscathed to the substrate because the wavelength of the laser matches the wavelength of the solvent matrix, not the wavelength of the material composition. And why this matters is it allows us to make thin films that are of equal performance, but at a fraction of the perovskite precursor that is required to perform spin casting or spin coating. So the first thing we did in terms of characterization is SEM and EDX characterization. This is just super brief description of how it works, because a lot of people have been talking about SEM, but I feel like it's important to sometimes go back to the basics. Basically, we have an external stimulation. For SEM, since it's scanning electron microscopy, we're using electrons. We're shining electrons at the sample. It kicks out an inner shell electron, and then an electron hole is created. So this is called an incident electron or a secondary electron, this one right here. And once that is detected, it gives us typography images such as this one and this one, so regular SEM images. Those are determined based on the secondary electron that's kicked out of the sample. But what also happens is after this inner shell electron leaves, an outer shell electron can hop into the inner shell, and obviously when that happens, it releases a lot of energy in the form of characteristic radiation, and once that's detected, it gives us EDX images, which is energy dispersion X-ray spectroscopy, and that tells us exactly what the sample's atomic composition is, because the distance from the outer shell electron to the inner shell electron is characteristic of specific elements. But what can also happen when the radiation is released, the characteristic X-rays, they can also kick out yet a third electron. People don't call it a tertiary electron, but they should, and that is known as an OJ electron, which is this one right here. But OJ spectroscopy is very expensive, and instead of doing that, you get very similar results with XPS, or X-ray photoelectron spectroscopy. And for this one, we're using X-rays, as the name suggests, instead of electron beams, such as with SEM, and it allows us to calculate or determine the elemental composition of a sample throughout the thin film. So we used XPS on a variety of samples, really two types. One is thin films, and that's where we're looking at the top 15 nanometers of the thin film and seeing what its composition is. And the second one is we're using 2D on 3D perovskite systems. They're called heterostructures, and for that, they're 200 nanometers, and we wanted to see the interaction between the 2D structure and the 3D structure and the interface between them. And for that, we had to do what's called sputtering. For that, we use argon, and we're basically just destroying the sample and collecting data at each layer of the sample as far as we want to go. And we'll talk a little bit more about that. So first of all, we wanted to see whether the thin films grown by maple, again, saved a ridiculous amount of precursor material, just a fraction of the material required for spin casting or spin coating, and we were wondering whether that would compromise the halide distribution as well as the atomic concentration of the thin films. And from the data, it seemed that the answer is no. The iodine, you want it to be kind of distributed throughout the sample, kind of randomly, evenly, and that is true for all the 4 samples that we tested. This one is spin cast, and then this one is maple, and these 2 are also maple. And if you remember earlier, I said there is an annealing temperature after the organic material, could be inorganic too, but for us it was organic material starts to evaporate and forms on the substrate. That can happen at 75 degrees Celsius, 50 degrees Celsius, or 25, and these are what these samples show. So 75, 50, and 25. So halide distribution was virtually unaffected by the deposition technique in terms of atomic concentration and mass concentration. So I included atomic concentration at first because that's what I found in literature. Usually people use atomic concentration to compare, but I felt like mass concentration told a little bit of a better story, so I included that as well. So you can see here, the red is iodine, that's the X, the halide that we're using. It's at 40%, 38%, but it was higher for spin casting, and kind of the same for 25 degrees annealing temperature for RIR maple. It wasn't substantial enough for me to make any significant conclusions from it, but I just wanted to include it in there. And like, if people have questions, or we can talk about that a little bit more. And yeah, these are just the SEM pictures of what we're looking at, translation from EDX to SEM. And these are methylammonium lead iodide. So methylammonium would be the organic part, because these are hybrid halide perovskites. There's an inorganic and organic component. Our organic component is methylammonium, and inorganic is iodine. Okay, so that was the first part of the project, just comparing maple versus spin casting in terms of halide distribution, atomic concentration. The second part is we're making these structures called heterostructures. They're made of methylammonium lead iodide and phenylethylammonium lead bromide. So the methylammonium lead iodide is known as a 2D perovskite, so you have repeating units of lead iodide or lead iodine, wherein bulky organic cations are introduced, and you form a 2D structure. That's what thin films usually are. That's what perovskites are. But we're combining that with a 3D structure that allows us to get better performance, but also more resilience and less degradation over time, specifically for moisture resistance, because there is hydrophobic bonds and molecules in the organic part of the 2D structure. So specifically, we wanted to see the interaction between the halides of the 2 different perovskites that are in these heterostructures, so the bromine and the iodine, and that's what XPS or SEM images up top, and then EDX images at the bottom, because they tell us specifically what the elements that we're looking at are. So this is the same exact spot except we're zooming in at different angles. This is 20x, 35x, and then 50x. The green is the iodine, and then the red is bromine. As you can see, there was kind of like even distribution of iodine, and then the bromine sits on top of it, which was kind of what we expected. And we wanted there to be a little bit of an interaction between the two halides at the interface, which is kind of present. So more specifically, there is upward migration of the iodine, but little down migration of the bromine atoms. Cool. So this is just XPS data. Quickly go over it to support the findings that we had in EDX. Basically, you were interested in the bromine and the iodine. This peaks before that. This is the sputtering that I was talking about earlier. So I can answer more questions about this. I'm pretty sure I'm out of time, but I appreciate you taking the time to listen to me. And yeah, be happy to take any questions. Great question. And so the question was, what governs the distribution of the two different halides in our heterostructure, the bromine and the iodine? And the answer is we don't know. We're not sure. We investigated it at 3 different temperatures, and it was virtually unaffected between the 3 of them. So I can tell you that the annealing temperature of Arabian maple does not affect it, but we're still not positive exactly on what has that influence. But yeah, future works. Other questions? Cool. Thank you so much.
All right, thank you, everybody. What an excellent round of presentations. Great job. I think next group's probably already coming in. Right? So 11 o'clock? So if you need, we're moving right along this morning. If you need a restroom break, probably do that quick. But otherwise, next group's coming in. And please, if the audience has questions, presenters repeat the questions so that the camera can hear it.
Yeah, of course.
Whenever you're ready.
Awesome. All right. So my name is Jackson Violetel. I'm a senior at the University of Notre Dame, and this summer I participated in the Singh Center for Nanotechnology REU at the University of Pennsylvania. My faculty advisors were Dr. Sue Ann Bidstrup-Allen and Dr. Mark Allen. My project focused specifically on cathode nanofabrication for increased aluminum air battery power. So a little bit of background on where we see this technology being utilized. Agricultural drones are used to gather sensing data and improve farming efficiency. They show extreme promise for revolutionizing agriculture, but they lack in one major area. Battery technologies only allow agricultural drones to fly for approximately 20 minutes. Aluminum air batteries, if implemented in agricultural drones, would extend the lifetime and the flight duration to up to 1 hour or 60 minutes of flight. So it's a very exciting and promising technology. So a little bit of background, again, on what are aluminum air batteries and how do they basically function. So as the name suggests, aluminum air batteries utilize both aluminum and air. On the anode side, we have an aluminum anode that's oxidized in order to initiate a flow of electrons. On the opposite side, however, we can't leave it open to air. That wouldn't be great for battery function, and it would ultimately create quite a mess within the drone itself. So to solve this problem, we create a porous cathode structure that allows oxygen to selectively diffuse while keeping the contents of the cell inside for function. So again, the cathode is what we're focusing on. It's a porous structure with often a catalyst on the inside layer to facilitate oxygen reduction. And so when we're talking about drones and specifically battery usage in drones, there's a couple factors that I think are important to consider and discuss. So looking at the current batteries used in agricultural drones, lithium-ion batteries are very high power but relatively low energy. And so what this means is that their high power allows them to function at very high performances. They can take off well. They're able to distribute power to lots of different sensors, cameras, and communication technologies. As previously mentioned, lithium-ion battery drones have relatively low energy, which means that they cannot sustain a flight time for further than 20 minutes. Aluminum air batteries, on the flip side, are very high energy and relatively low power. And then what this means is that aluminum air battery drones can fly for a very long amount of time, but they don't supply the necessary power to allow the drone to function in the way that we need it to. So current state-of-the-art technology for use in aluminum air batteries is a platinum-based cathode. These platinum cathodes allow the cell of aluminum air batteries to perform at performances of a lithium-ion battery, or in some cases even higher. And this is great, this is very exciting. And so the reason we don't implement this technology, though, is the cost. Platinum is a very costly and hard to manufacture metal, and so creating nanostructures with platinum keeps us from implementing this technology, as I said, because of cost and the manufacturing techniques necessary. So not only do we need to implement higher power cathodes, but now we also need to cut cost. So there are two main constraints on the project that we've now discovered. So there's a couple different fabrication techniques that I specifically explored in order to overcome these two criteria of both power and cost. The first fabrication technique that I explored is called just single layer electrodeposition. And so this utilized electroplating of a single metal on top of the carbon cathode. So I explored silver, a smooth copper, and then by changing current density, a rough copper on the surface. Moving from there, the next sequence in the linear progression of fabrication was a multi-layered cathode. And so as the name suggests, a multi-layer is a single layer of, in this case, copper, with a secondary layer on top, both electroplated in sequence. The third fabrication technique that I explored was alloy electrodeposition. And again, as the name suggests, this was an electrodeposition of two metals simultaneously to create an alloy on the surface. Lastly, and the technique that we were most excited about, was plasma vapor deposition of silver specifically. In short, what this technique involves is sputtering a material using a high energy plasma environment to create a very uniform and controlled film on the surface. This makes for good science because we can easily control and we can easily quantify how we're fabricating these cathodes. So looking at the power performances of the cathodes that we previously discussed, we see that by and far the plasma vapor deposition, the two values on the far right of this figure, show the highest performance and the highest promise for use in aluminum air batteries, and specifically in agricultural drones. So following the natural progression of the project, we chose to focus on the plasma vapor deposition as our method for increasing power performance in these aluminum air batteries. So from here, what's the next step? What do we do to take this technology from being on a lab bench to being used in an actual drone in agriculture? Well, naturally, as all scientists do, we start in a small scale. We started with a very controlled system, a 1 by 1 centimeter footprint that we could easily control and work with. What I wanted to discover is how far can I push this cathode that I just made? How well can it, as you'd say, handle the heat, right? So to discover that, I increased the surface area of the aluminum. I kept the cathode the same. I increased the aluminum by 3 times to see at what point the cathode would start to cap out. Where does it plateau in performance? And so by running these tests, by increasing the surface area of specifically the aluminum in this battery, I went from a previous power of 112 milliwatt that we previously saw to now a 210 peak power in the aluminum air batteries. And so this is really exciting. So we saw not only can we create low-cost, high-performance cathodes, but now we can also utilize scaling techniques to get all the juice out of these cathodes that they really have. And so as I talk about the future of this work and where we're looking to go next, some of the things that we're looking to explore are creating ultra-high surface area porous cathodes. And so the main way that we're going to do this is to use plasma vapor deposition, again, to co-sputter, and then selectively remove just the copper. This ultra-high surface area, we hypothesize, will increase catalytic function and subsequently power performance. So with this, I'd like to acknowledge mostly my graduate mentor, Young Hung, my 2 faculty advisors, Dr. Suan Bidstrup-Allen, Dr. Mark Allen, and the grants and funding sources that made all of the research I did this summer possible. So I'd love to hear all of your questions and to discuss my work a little further with you, and I thank you for your time. Yeah.
Could you please go back to your last slide? Yeah, so my question to you is the ultra-high surface area of course silver cathode.
Yes.
Is that going to allow for a higher flow of current from the cathode to the anode?
Yeah, so current wasn't mainly a limiting factor. We never capped out current within the silver, and so I believe by changing the volume, so we're etching out some of the volume by creating pores, I don't believe that will have a significant impact on the overall current distribution, if that answers the question.
Yes, and I did have another one.
Of course.
Were you guys actually considering this, maybe putting this type of battery onto the drone as a payload?
Yeah, so this will be the main battery source in the drone. And so what we're looking to do is completely replace the lithium-ion batteries. As I mentioned, both because of cost restraints, these lithium-ion batteries are approximately $73 per 20 minutes of drone flight. So as you could tell, that's not very practical when corn doesn't sell like gold. So it's not like we're generating that much money. And so yeah, we're looking to completely replace the lithium-ion batteries as the main payload on the drone.
Any other questions? Thank you, Jack.
All right, thank you.
Next up, we have Maria. I think you have to point it at the middle of the screen.
The middle of the screen, okay.
That work? Jackson, what works?
I spammed it.
Okay. Okay. Well, hopefully this doesn't pose too much of a problem. Okay, well, my name is Maria Bambrick-Santoyo. I'm a junior at Yale, and I was at Duke this summer working on p-type doping of methylammonium lead tin iodide by charge transfer. So methylammonium lead tin iodide is a halide perovskite, which is a class of materials with a shared crystal structure of the form ABX3, which is shown on the screen. And they're promising for 2 reasons. One, they can be easily made by solution processing methods like spin coating. And 2, they have promising device applications. So, for example, in just 10 years of development, solar cells with perovskites have reached over 25% efficiency, which is not really matched by any other material. So the second half of my project is electrical doping. So doping is the introduction of defects to tune electrical properties of the material. And doping has enabled most of today's semiconductor technologies, including solar cells to transistors to LEDs. So it'd be natural to think, can we dope perovskites? However, doping in perovskites has proven challenging because of compensation from intrinsic defects. So essentially, when you add a dopant molecule to the perovskite structure, it'll rearrange itself to compensate for that change, leading to a net zero effect. So one way I'm hoping to get around this is through doping by charge transfer, where instead of a molecule being incorporated into a crystal lattice, it sits on the surface or at a grain boundary and accepts or donates electrons, therefore tuning carrier density, conductivity, and mobility. So in order to choose a dopant, we have to think about the energy levels of our perovskite. So for p-type doping, which is what I focused on, the lowest unoccupied molecular orbital should be below the valence band. So in other words, the LUMO level should be, which is the lowest energy state that can accept an electron, should be below the valence band to make it energetically favorable for this doping to happen. So I looked at two different dopants, large organic molecules, F4-TCNQ and F6-TCNNQ. F4-TCNQ has previously shown successful doping of this perovskite through charge transfer. However, in that study, the films didn't have complete coverage of the substrate. So while they were effectively doped, they weren't suitable for devices. And additionally, I looked at a new dopant, F6-TCNNQ. So that leads to my main questions, which are, if we change the film morphology of the dopant with F4-TCNQ, is it still effective? And can we design a better dopant with F6-TCNNQ? And so how I determined whether or not these materials were doped was by making use of the Hall effect, which I'll talk about a little bit later. So starting with an experimental overview, it all starts with deposition and characterization of my films. So I make the films via spin coating. So the perovskite precursors are dissolved in a solvent and put on a substrate that spins very rapidly, flinging off the excess solvent and leaving just the perovskite to crystallize. And the crystallization is finished with annealing. So once I made these films, I could characterize them. So my first characterization was X-ray diffraction, which looks at the crystal structure of your material. So while there are variations from pattern to pattern, they all show peaks where there are expected peaks for this perovskite, which means that the crystal structure is preserved even among incorporation of the dopants. So I also looked at SEM images to see how the morphology of the film changed. Yeah, so at the top you'll see top-down images, and then in the bottom panel you'll see cross-sectional images. So first I looked at the undoped samples, and you can see, well, there is a uniform coverage of the substrate, and for when I added F4-TCNQ, the substrate looked pretty similar in terms of morphology and shape, but the grain size doubled. And then upon adding F6-TCNNQ, upon adding F6-TCNNQ, there were pinholes, large pinholes in the film, and it completely disrupted its morphology. Okay. So once I characterized my devices, I could move on to once I characterized the films, I could move on to preparing the Hall devices, which was the bulk of my work. So it starts with patterning the Hall bar, so essentially taking a blade and scratching off the excess perovskite, because I mentioned, they are soft materials, so you can scratch them off to make that pattern there. And then depositing gold contacts using thermal evaporation and a mask. And then this is, up until that point, everything has been done in a glove box because tin is very air sensitive. And so I encapsulate it by lining epoxy around the edge of the device and placing a secondary glass slide on top so that I can take it out of the glove box. Connect sockets so that it can be measured externally. And then I can move on to the Hall measurements, which make use of the fact that under the presence of a perpendicular magnetic field and current, electrons will move perpendicular to both of those. So you can imagine 3 axes. And essentially, if you look at my device here, that means that if there is a magnetic field coming up through the device and a current applied long ways across those 2 electrodes, the electrons will collect on one side or the other of the device. And when you measure that voltage difference, you can extract carrier density, conductivity, mobility. So the electrical properties that we're looking for. Specifically, these are very highly resistive samples, so I used AC Hall measurements created by 2 coupled rotating magnets to compensate for some of the noise that comes from the resistive samples. So this is an example of one of what the Hall measurements looks like. At the top, you have the oscillating magnetic field, and the bottom shows the response of the resistance across the sample. And so the alternating magnetic field allows the signal to be distinguishable from the noise. So we can fit a background to this curve, and then the oscillations are the response signal from the magnetic field. And then from that, we can extract the electrical properties. So these are the results of my Hall measurements. I have conductivity on the left and carrier density on the right, comparisons for undoped and doped with 0.2 molar percent of each dopant. So as you might notice, F4TCNQ in both cases did increase the value. So conductivity increased by about an order of magnitude and carrier density by about half an order of magnitude, which tells me that even with this preferred film morphology with complete coverage of the substrate, it was still an effective dopant, so one step closer to using this in devices. However, with F6TCNNQ, the conductivity didn't really change and the carrier density seems to have decreased, which is definitely not a sign of p-type doping. So my thought as to why this might have happened is, if you remember the completely disrupted film morphology with the huge pinholes, I think that might have had an effect. So to summarize, I fabricated, characterized, and performed AC Hall measurements on thin films of methylammonium lead tin iodide with and without the two different dopants. I found morphologically that F4TCNQ doubled the grain size and F6TCNNQ produced large pinholes in the films. And based on the Hall measurements that I did, F4TCNQ does dope this morphology of methylammonium lead tin iodide, but F6TCNNQ does not yet effectively p-dope this perovskite. So a natural next step would be modify the film deposition conditions to see if I can form uniform films of the perovskite with F6TCNNQ. But more broadly, this really opens doors for other future research, including varying the concentration of the dopants to see how the effects change based on the quantity of dopants, and then carrier-resolved photo Hall measurements, which will take these parameters under illumination to understand both majority and minority carriers, which are very important for further down the line applications in solar cells. So that's the end of my presentation. I'll take questions.
Questions?
Yes?
What would you say the shelf life of these films are?
So in the glove box, I did XRD of the films the very beginning of the summer, and then basically like 9 weeks later. And when in the glove box, the XRD patterns didn't really change at all. However, the encapsulation that I showed with the epoxy, while it does extend the life of a perovskite compared to if it were exposed to air, the epoxy still does actually degrade it a little bit. So with the encapsulation, that is reduced to around 2 weeks. Oh, and also the question, which I forgot to repeat, I think, was how's the shelf life of the perovskites? Yeah.
Did you potentially consider using other encapsulation methods, like doing like SiO2 to thermal evaporation directly onto the perovskite, and like rather than having the epoxy of the perovskite layer with just creating a glass layer on top of it than under vacuum?
So the question was if I considered other encapsulation methods, including just creating a glass layer on top of the perovskite. Yeah, so that is something that was considered and is currently being worked on now in the lab. Very similar method, but instead of placing the glass on the epoxy, just placing the glass directly on the perovskite and then trying to coat the edge with epoxy. So that is technically challenging, but we think it might extend the life of the devices. So that might be a direction that the lab goes in the future. Anybody else? Thank you, Maria. Next we have Rachel.
Hi, my name is Rachel Chan. I am an upcoming junior chemical engineer at Villanova University, and my project is investigating the electrokinetic behavior of cement-based and alternative cementitious materials. As a forewarning, the formatting was changed recently, so if it looks kind of weird, I apologize. So our project's goal is to make the production of concrete, which is made of all these materials, more environmentally friendly. Specifically, what we're aiming to do is achieve either partial or complete replacement of Portland cement, whose production contributes about 7% of the world's CO2 emissions. So what we're trying to do is use something called supplementary cementitious materials, or SCMs, in replacement of a Portland cement, with addition to chemical additives and pore solutions, in order to improve the production and durability of our blended concrete slurries. So I just mentioned a pore solution, so I'll quickly explain what a pore solution is. So in the process, if you mix cement with water, a process called dissolution will immediately occur. In that process, ions from your cement will disperse in our solution. That kind of like soup of ions is what we call the pore solution. So when we partially or even completely replace our cement with our SCMs, what we do, we have two possible outcomes of how these SCMs interact in our pore solution. One, if we have proper conditions, our particles will experience appropriate rheology or exhibit stable motion in the solution. However, if they do not have proper conditions, they will agglomerate, meaning that the particles will all clump together and form and will impede the flow of our slurry, which is something that we do not want to have. So in order to recognize how well these mixtures act, what we have to do is measure something called their electrokinetic behavior, or specifically is measuring their zeta potential. So what zeta potential is imagine you have a particle with some surface charge, whether that be positive or negative, and you submerge that in an ionic solution. The first thing that will happen is ions will form around the surface of your particle. And as the ions form, you'll create boundaries around that particle. At the outmost boundary is where you can measure your zeta potential. And that zeta potential can be affected by how strong your charge is of your surface charge of your particle, or if your particle has a coating, which is usually a polymer that forms around the surface of your particle if you use chemical additives in your solution. So the zeta potential itself can have either a positive or negative value depending on what's your surface charge of your particle. What we're looking at more is the magnitude of the zeta potential. So if you have a magnitude of 30 millivolts or above, that is considered a stable zeta potential, meaning that your particles will not clump together and impede your flow. That would happen, however, if you had a zeta potential of 20 millivolts or below. And there are multiple factors that can affect this zeta potential, such as the pH or conductivity of your solution, as well as what is your solid concentration of like what particles you're using, as well as if you use any chemical additives. So my method so far has been using the Malvern Zetasizer and a reusable cuvette. Our cuvette is our sample holder, which uses DI water as well as pore solution samples. And what we do is we place the particles that we're using in those solvents, and we sonicate it for 15 minutes in beakers. We take that sample out, put it into the cuvette, and then the cuvette into the Zetasizer, whose software will measure 6 measurements of the zeta potential per sample. We also measured the pH and conductivity of our sample using 2 different external probes. So as I said before, we used 2 different solvents, the DI water. These are the concentrations that I used for the DI water solvent. Later on, we actually made our own pore solution, which had a pH around 13.5. That is reflected in literature values of native pore solutions in Sloman slurries. So that was pretty good. And these are just the chemical composition that we had. And in our actual experiments, we did dilute it further with DI water because it gave us conductivity values that were reflected in literature, which is what we wanted. This is the chemical composition of all the particles that I used. As you can see, there is a wide variability in the different oxides of each particle. This will all play an impact on how these particles interact in our pore solutions, so it's an important factor to keep track. Oh, oops, sorry. So here are my zeta potential results of those particles in straight DI water solvents. So you can see that the silica flower, which is that maroon one at the bottom, experienced the most stable behavior with a zeta potential result of above 30 millivolts throughout. The opposite was true for the class C fly ash, which is that purple one, who experienced aggregation in the DI water solvent. We attributed that to its calcium ion concentration or chemical composition, as well as the pH and conductivity of that solution. And then on the right figure, you can see we plotted zeta potential versus conductivity, and we see that as the higher conductivity you had, the less stable your solution was, being reflected by a lower zeta potential. So that just goes to show that conductivity does in fact impact our zeta potential. Here is the zeta potential pH and conductivity of our particles in the pore solution that we made. So you can see majority of our particles all experience aggregation with the very low zeta potential results. This table will then show us which kind of which solutions we need to use chemical additives in order to improve their stability in the solution. And from this table, we can see that all of them really need that chemical additive to impact their behavior, with the exception of the silica flower, whose zeta potential was quite larger than the rest. So what we did was we experimented with silica flower in different pore solution concentrations, as well as different DI water concentrations, and that is reflected in this figure. So again, you can see that general trend of lower conductivity you have, the higher zeta potential was reflected, and opposite is true. If you have higher conductivity, you have a lower zeta potential. So what we're trying to optimize is having higher zeta potentials. Here we used a different material called Class H cement, and as background, this is not an SCM, this is actual cement. So what we can see is we also use these with additives. So the additive here is called sodium glucoheptanate, which is a retarding additive. And you can see that as our weight percentage increases, the actual stability of our solution increased. However, as we further increase this weight percent out, it actually decreased all the way down to -4 millivolts, showing that our particles experienced aggregation and our solution was overall unstable. So therefore, that reflects to us that although the SGH does help our solution, it can only improve it to a certain point, and therefore we know like how far along that line we're going to be at. We also tried a different additive called a superplasticizer, whose commercial name is Daxad19. And again, we see that general trend of if you increase concentration, your stability also increased, but again, it only increased to a certain limit. So again, that shows that although these additives do help improve the stability of our solutions, it again only does it to a certain point. Here are some of the scanning electron microscope images that I've done. These are two of the particles that I've worked with. So you can see that they have very different particle shapes, and that is an important factor to consider when working with these particles, because particle shape can impact how well or poorly these particles interact in our solutions. So it's just a good fact to keep track of these. Some future work, what we're going to do is more zeta potential measurements. Again, especially with the zeta potential measurements of our solutions with the additives, with our SCMs. We'll also be doing complementary tests, such as seeing what kind of particle sizes we're working with. We were going to do a filtration procedure, but which I started, but we had some trouble trying to optimize that procedure, so we could not finish that. And we'll also be doing adsorption tests of our additives using UV light. So these are my acknowledgements. I would be happy to take any questions at this time.
Questions for Rachel? Okay, thank you again. We have Benjamin.
Hi, I'm Ben Sampson from the University of Kentucky. I'm an undergraduate there, and that's also where my REU was hosted. So my work is a compositional analysis of historic and prehistoric pigments. And to do that, we developed methods for using X-ray fluorescence spectroscopy, which is a form of energy dispersive spectroscopy. And we did that to compositionally analyze pigments in ceramics and paintings. These XRF techniques that we developed were applied to Native American pottery fragments from the southeastern and southwestern United States, as well as to modern paintings, because unfortunately we cannot find any historic paintings to analyze. But they were a good stand-in for historic paintings. And then a little bit of background on XRF EDS. So in XRF EDS, a high energy X-ray beam is fired at the specimen, and that beam excites the electrons in the atoms of that specimen. And then once those electrons return to their ground state, they release a characteristic X-ray of that element. And this is sort of similar to SEM EDS, which uses an electron beam instead of an X-ray beam. So some pros to this in this particular machine, that allows we have a higher compositional accuracy than one would normally see with SEM EDS. Also more convenient measurements because we don't have to pull a vacuum for our samples. That also helps because these are historical artifacts and they're very porous, which if you're familiar with SEM EDS, that can be a problem if you're pulling a vacuum and it's constantly outgassing. And perhaps the most important part of this machine is that it has the capability to create large area maps, which is also helpful for looking at historic artifacts, which can be fairly substantial in size. However, some downsides for this are lower spatial resolution. I believe our minimum spatial resolution was around 5 microns. And the inability to detect some lighter elements, particularly like silicon and aluminum, because the X-rays are going through atmosphere and also through the detector windows, which are beryllium, and that blocks out some lower energy X-rays. And here are the samples that we analyzed. From left to right, the first one is a pottery fragment from the southeastern United States. This fragment features a slip, which is a clay slurry, which is applied to the outside of the pottery partway through firing. And this is significant because it means there's a different composition on the outside of the fragment than on the inside. And also features temper, which is a hard material which is dispersed throughout the pottery, and that helps during firing to prevent shrinkage and cracking. And also you can see the pigmentation on there, that red pigment. And then the next specimen we have is a piece of pottery from the southwestern United States. Again, this pottery has some similar features such as a slip, temper, but additionally this has 2 different types of pigments on it. As you can see, there's a red pigment and a black pigment as well. And then moving on to the paintings that we analyzed. We have a modern acrylic painting. This painting features some mixed pigments and also some undercoating, which can make identification of the different pigments challenging. And then finally, we have an oil painting, and this features a lot of the same sort of mixed pigments and undercoating, but with the addition of some scraping on some of the features, which will be shown later. Sorry, it isn't switching back. There we go. All right, so this is the first of our specimens. This is, again, the southeastern pottery fragment. You may notice that the manganese and calcium figures are mislabeled. Those labels are actually swapped. Sorry about that. So in the dark blue image in the top right, that is a map of iron composition across the pottery. As you can see, there's a very good correspondence between the red pigment and the iron This indicates that this is probably some sort of red ochre, which is just Fe2O3. Then moving on to the light blue image, which is actually calcium. As you may be able to see, that shows there's a high level of calcium in those white flecks on the surface. And those white flecks are the temper that was included in there, which is believed to be some form of crushed shell. And then in the map of calcium in red, you can see that it's sort of an inverse of the light blue map. And that shows that there's a lower potassium concentration in the crushed shells. Also, you may notice that slight dark splotch in the middle of it. That's not relevant. That's actually an adhesive that was put on there by archaeologists during the preservation of the artifact. And then in the final map, which is of manganese, you can see that there's some sort of flecks on there. Those have not been identified, but if you notice in the optical image, they sort of correspond to some of those darker spots. So that's probably the material that contains manganese. Okay, so moving on to the southwestern ceramic fragment. As you can see, the first of, I should probably mention that this fragment was not able to be mapped in our XRF EDS because it has a very sort of curvy geometry, and we weren't able to get a proper focus on that. So these are just point scans. So the first of those point scans is of the bare ceramic. As you can see, you can see that there's some calcium and iron that shows up in there. But if you know about the composition of clay, there's a lot of aluminum and silicon in there. And you do not see the peaks for that because those X-rays are blocked by the atmosphere in the chamber as well as the detector window. And then our next spectrum is from the black pigment. It's sort of similar, except that there's perhaps a little bit more iron in there than the bare ceramic. Unfortunately, there's not any known historic pigments that can, black historic pigments that contain calcium and iron, which leads me to believe that this is some sort of carbon-based pigment. And of course, the characteristic X-rays for carbon are much lower energy than any of these, so it will be impossible to see these on there. And then the final spectrum is of the red pigment. As you can see, it has a very high iron peak, indicating a higher iron concentration. Much like the red ochre from earlier, this is also probably red ochre. Now moving on to the first of the paintings. This is the modern acrylic painting. So there, as you can see, we have the compositional maps much like the other ceramic, and we have a few identified pigments. So the first of them is lithopone, which is a mixture of barium sulfate and zinc sulfide. And as you can see in those bottom three maps of barium, sulfur, and zinc, they tend to correspond fairly well, leading me to believe that those elements are contributed by a common pigment, namely the lithopone. Next, there's titanium white. As you can see, there's a very strong correspondence between the regions of the titanium map indicating a high concentration of titanium and the wider portions of the painting, leading me to believe that this is titanium white. And then, as you can see in the manganese and iron map, the manganese is shown in red and the iron is shown in blue. And there's sort of a mixed purple color in portions of the painting. And where that color is brightest, you can see that there's a sort of brownish color. And also in the regions containing primarily iron, there's also a small manganese content. It's just difficult to see in this particular image. But that leads me to believe that it's some mixture of umber and sienna, and the manganese content of those can vary, which is potentially a reason why there's two distinct compositional regions in the manganese and iron map. And in this blown up image in the bottom right, That's just showing some of the technique with undercoating and mixed pigments. As you can see, there's some sort of brown pigment underneath the brighter red-colored pigment as well. Moving on to the final painting, this is a modern oil painting. This one has a few different pigments identified, the first of which is gypsum, which is sort of an off-white color. And as you can see, portions of the painting which are off-white correspond somewhat well to the map of calcium on the right in red. The next of these is potentially orpiment or realgar. Those are arsenic sulfide compounds. Unfortunately, those are, though if they are present, they're present in the painting in very low amounts, so it's difficult to show up here. Moving on to iron, so there's possibly red or yellow ochre in here. Those are essentially hydrated and anhydrate versions of iron oxide. That is believed to be the source of the iron in this painting, mostly just because the red and yellow areas correspond well to the areas that are rich in iron. And again, with titanium white, the areas which are very bright in titanium, in the titanium map, correspond to areas that are optically bright in the painting. And also with this blown up image, you can see the scraping that was mentioned. These are the windows that are painted on the leftmost building. You can see how there were layers of paint, and then some of those layers were scraped away to provide that visual effect. So works cited in acknowledgement. Yes. So any questions? Yes.
Why was the project done? Was it a museum requesting that?
So EduSlab, the REU organization that I've been working for, the goal of that is to provide these sort of expensive pieces of equipment for use by archaeologists, and so the goal of this project was to develop methods for doing this sort of analysis, if that answers your question.
I have another question.
Yes.
Did you find anything surprising or not what you weren't looking for when you did this analysis?
I was surprised by the amount of pigments that we were not able to identify. So there are a fair amount of pigments that are lower Z, so they produce lower energy characteristic X-rays, which of course are not observable on this particular piece of equipment. So that was surprising to me. Yes.
So one thing I was wondering, would like a major application of this be for like really old specimens where you can't actually like see the pigments that are left?
Yes, that was an application that was considered. Unfortunately, because of the low resolution of this, the piece of equipment that we used to do this, which was XRF EDS machine, that's not entirely possible. So SEM EDS might be a better candidate for that.
Any other questions? Thank you, Ben.
Thank you.
Our last presenter is Dane.
Okay, cool. I'm Dane. I go to Amherst College, and I did my REU in the iCal lab at Montana State over the summer. And I'm going to be talking about biotrapping bacteria and the impact that has on biocorrosion. And I'll get into what biotrapping means in just a second. I'll just give a quick little overview of biocorrosion first. I don't know why the aspect ratio is messed up, but that's okay. So we're all familiar with corrosion. It often results in the structural failure of whatever system you're looking at, and the structural failure usually stems from the formation of these very small micron scale little pits or holes that you can see here forming in the surface. The bio part comes in when you have microbes or bacteria present on or around the material surface that you're looking at, and they can interact with the surface in such a way that they affect the corrosion process, and we call this microbially induced corrosion. This happens with like ship hulls, oil pipelines, gas pipelines, stuff like that, all sorts of things. And the cost of corrosion annually in the US is estimated to be around $1 trillion, which is like 6% of the GDP. It's a crazy amount of money. So there's a lot of interest in corrosion research going on right now. Okay, so biotrapping. So what does biotrapping mean? Essentially, the idea here with this experiment is we apply a monolayer of net positive charges onto the material surface. The idea being that the bacteria that we're looking at carry a natural negative charge. So there's going to be some sort of electrostatic attraction between the bacteria and the material surface such that the bacteria are confined onto the surface. They can still move around laterally. They can slide around like a hockey puck, but they're kind of confined on that surface. And this is what biotrapping is, and that's kind of the gist of the experiment. So we apply this layer of positive charge and kind of see what happens. The actual material that we're interested in is 1018 carbon steel, which is a low carbon steel. It's very popular. It's used in a bunch of different industries. We use these little circular steel coupons. We use 6 of them for the experiment. I won't give like a whole overview of the steel production process, but one important thing that I want to point out is manganese sulfide inclusions. So during the steel production process, towards the end, you add in some alloying elements, one of which is manganese. And the idea with manganese is you add it in there to scavenge up sulfur impurities in the steel. These sulfur impurities arise during the production process, and they're really bad for the structural integrity of the steel. They just make it a lot weaker. So you add in this manganese, it scavenges it up, and you end up with these manganese sulfide inclusions. And these little inclusions are also, they're not structurally sound. It's much better than just having this free-floating sulfur all around in the steel. But these inclusions are often the site of localized corrosion, and that's how you end up with those very deep pits and holes like you saw earlier. We use this chemical with a really long name to get the layer of positive charge on there, and we do this to 3 of the coupons, and we leave the other 3 untouched so that we have a functionalized group and a control group to compare throughout the experiment. And lastly, the bacteria we used, just a note, they're an anaerobic bacteria, which means they don't use oxygen to survive or grow. Instead, they're what's called a sulfate-reducing bacteria, and I'll get back to that later in the presentation. Okay, so before doing the actual corrosion experiment, we can do some preliminary analysis of just the clean, polished steel surface in the SEM. Just the one thing I want to point out here is these little features that you see here. Those are those manganese sulfide inclusions I was talking about. This is the same area. This is a 20 kV beam, electron beam over here on the left, and a 1 kV beam over on the right. You can see that higher energy beam can penetrate deeper into the surface, so it's it makes these manganese sulfide inclusions much more obvious. But you can see the 1 kV, they're not actually like these hollow holes how they look in the 20 kV. They're really filled. Additionally, we can do EDX analysis. This is really nice because if there's something that we're looking at in the SEM and we don't actually know what we're looking at on the surface, we can just run it through EDX real quick and get the elemental mapping. You can see here's a close-up of one of those manganese sulfide inclusions. Sure enough, super strong manganese signal, super strong sulfur signal, some oxygen on the fringes, which is actually really interesting. But after the preliminary analysis, we can do the actual corrosion experiment. We put these coupons in the bacterial medium for 2 weeks or for 13 days, and then we take them out and we can look at them in the SEM again. So here are some post-corrosion SEM images. On the left here is a control sample, and on the right is a functionalized sample. So those functionalized samples are the ones with the positive charge applied to them. One of the big observations right off the bat that we noticed is the level of biofilm buildup. So you can see, so here on this control sample, These little guys, those are the individual bacteria. They're like 2 microns in length. This background here, these are the corrosion deposits that they create, and then this glossier looking stuff is the biofilm from the bacteria. And we see right off the bat a much thicker, much more built up biofilm on the functionalized surfaces, which kind of makes sense because you have that electrostatic attraction, more bacteria on the surface leads to a thicker biofilm. So that's kind of what we were expecting. Once we're done looking at images of the bacteria and the biofilm and the corrosion deposits and everything, we want to look at the actual steel surface itself. And the way we do this is we strip it using a chemical called Clark solution. That gets off all the biofilm, all the corrosion deposit and everything. So we can just look at the steel surface. This is just kind of a nice illustration of, so we went back to that same area from before, after corroding on the same sample. And you can see how these manganese sulfide inclusions, they really start turning into these deep pits. And that's why they're so critical to really accelerating the corrosion process. Okay, so one of the big things we noticed after stripping is, so here's again control on the left, functionalized on the right. These holes just look really similar, but these are 2 different samples. What we notice is if you see kind of this very shallow, like general divots here on the functionalized sample, this is general corrosion. We see a lot more of this on the functionalized samples than the control samples. Again, kind of makes sense. You have more bacteria present, trapped on that surface. You will kind of expect to have this more kind of shallow, these widespread kind of divots on the functionalized surface that we don't see on the control. On the flip side, however, we can look at the actual localized corrosion. So we can actually look at those individual pits and holes. And when we do that, we can do some pit depth measurements. The way this works is we use EDX again for this, so we can take an EDX measurement at the bottom of a pit and one at like the surface of the sample. And we can look at the intensities of those X-rays, and from that get the path length. That is the path length from the bottom of the hole to the surface through the steel. And from that, you can do some trigonometry and get the actual depth of the pits. And what we notice is there are larger pits and deeper pits on the control samples rather than the functionalized samples. So kind of the opposite of what we see with that generalized corrosion. And what we think is going on here is those extra biofilm layers that we saw on the functionalized samples, that extra biomineralization actually begins to serve as kind of a protective shield or protective layer in between the steel surface and the bacterial medium. So early on in the corrosion process, you get all this kind of general pockmarking, general corrosion that you see on those functionalized samples, but then you get this biofilm layer built up and built up and built up, and you end up with kind of a protective layer that is slowing down the corrosion process, severely hindering it, and maybe even stopping it completely, so that those control samples end up with much worse pitting overall. And yeah, this is just super kind of early preliminary looking at this kind of stuff. There's a lot more to look at. We have like 1 million images and a bunch of data, but this was kind of the extent of my summer project. I want to thank everybody up on the screen here, especially my advisor, Recep Avci, and my mentor, Brett Davis. And thank you guys for listening.
Questions for Dane? Okay, thank you again to everyone who presented.
All right. Hello, everyone. My name is Jordana Mazer. I study chemical engineering at the University of Buffalo in New York. but I had the pleasure this summer to do some material science research at NC State, which is a part of the RTNN network. And, all right, so you guys have probably heard by now what a perovskite is, but for our sake, a perovskite is, we're working with single crystals in the chemical formula ABX3. Specifically, I worked with methyl ammonium lead bromide. So methyl ammonium is the A, which is a cation, and then the lead is another cation, and then 3 bromides. And like I said, this lab works with the single crystals because in technology, and there's certain devices and chips that need a single crystal as part of the layering and part of the device. But the problem is that to grow these single crystals, it's very tedious. There's strict requirements, and it's very hard to integrate into the devices. So if you grow it, for example, there's something called the inverse temperature method, where you can grow it outside of the lab and then try to integrate it into the chip. But that has been very difficult. So this lab thought, hey, what if we can just grow the crystal on the chip, then we don't have to worry about integrating it. Is it gonna work? Oh, no.
Which one?
We go back.
The computer's having trouble loading your slides. It's unresponsive.
All right, well, I think I can start here. Oh, there we go. Okay. So this lab developed a method called the Universal Co-Solvent Evaporation Strategy, where you take the chip, you put the solvent, the solution containing, for example, the methyl ammonium lead bromide, and then when it evaporates, the crystal forms. There's a whole paper published on this, and right there. And there's 2 methods to increase the success rate of this strategy, because when you have multiple metals, it creates a heterointerface, which changes the drying behaviors, because different metals have different surface energies, and the surface energies can affect this evaporation rate, and as a result, you won't get that uniform crystal, that single crystal. So one way they decide to play around with it and see if they can increase the success rate is solvent engineering. So again, these images are all from this paper they published on it. Basically, the idea is if you take your solution and then you change the composition of that solution to maybe slow down the evaporation rate and get that more uniform crystal formation that way. I focused on the surface functionalization, which is not as properly researched as the solvent engineering was. And you did have these self-assembled monolayers. So here's that heterointerface I was talking about. When you have this silicon substrate with the gold layering on top that a lot of these pre-patterned chips have, the heterointerface affects the drying behavior because, again, different surface energies, it's going to have a different rate. So what this lab hypothesized is let's get 2 self-assembled monolayers. Let's get a monolayer that will bond really well to gold, a thiol, and a monolayer that will bond really well to silicon, a silane. And then if this blue layer and this new red layer, if those monolayers have the same surface energy or similar surface energies, then it'll minimize the difference between the 2 metals. So the idea is let's grow these single crystals on these layers instead of the metals in hopes to minimize that rate. So how I did this was manually make a bunch of silane monolayers and then make a bunch of thiols, which this is the whole list. And using these 3 methods, either spin coating, drop casting, or a solution bath, almost like dip coating, but I only wanted the top layer to have that layer, so we just called it a solution bath because we just put the substrate into a solution in hopes that it assembled that way. And then we got a uniform layer of all of those substrates, all those monolayers on that previous list. And then so again, we want to minimize the surface energy difference between the gold and the silicon. So one way to measure surface energy is to measure the contact angles, and then that can be converted into surface energy. So my goal was to take the substrate and take this treated substrate with that new layer with the monolayer, and then measure the contact angles. This is just a software I used to show you. right? So you can have a very high contact angle, or if it's very hydrophobic, or you can have that lower contact angle if it's hydrophilic. So this is so we did this with everything, right? Every monolayer we created, every self-assembled monolayer, we measured the new contact angles, and the goal was to compare to see, is there a silane that has the same contact angles as the thiols? And if theoretically, then that'll minimize that surface energy difference to get more uniform crystals. So this is just to show that, again, that higher contact angle means it's more hydrophobic. And the OTS is an 18 carbon length carbon chain monolayer. And then the OS is 8 carbon. So it's the same functional group, same head group, but it's just the only difference is the carbon length. So this was just a good sign that things are going well, because the higher carbon chain had a higher angle for all those 6 chemicals we tested. Because we wanted an array. For the contact angles, we wanted an array of different solvents, so we tested 6. This is again for the thiols. That was the silane. So for the thiols, again, the longer carbon chain had higher angles for all the different solvents we tested for contact angles. That was a good sign. And then this was another test I did. Because you saw those 3 methods: spin coating, dip coating, drop casting. Every paper has a different recipe, right? For all those self-assembled monolayers, there was dozens of different recipes, and I only had time to do 1 or 2 per. But this is just an example of, let's do 2 different concentrations in the solution bath, and I found that the higher concentration had a higher contact angles, which suggested better assembly, and it was more consistent with literature. So in an ideal world, I would have been able to get the most ideal recipe for every single monolayer. But unfortunately, because I had so many and I was doing everything by hand, that was pretty difficult. But unfortunately, I only had time to do it for OTS. But basically, in an ideal world, I would have tested maybe 2 or 3 different recipes for every self-assembled monolayer. There we go. I also did some AFM just to get some characterization of it. As you can see, these are the thiols. These all look the same. That's obviously different. What is this showing? It's basically just showing that gold is giving it a lot of features. So like I said, the thiols we want for the gold, but it's very hard to get just like plain gold plates to do research on. It's pretty expensive. So we took glass, and I think it was through a vapor phase, we were able to get someone to just do a very thin, like 18 nanometer layer of gold for the thiols to bond to. So very thin. So that's just showing that all these features come from the gold, not the glass. And then, there we go. The silicons, almost all of them are the same pattern. PFDTES was the most different. Due to time constraints, I didn't have time to take an image of PFOTES, because if you know anything about AFM, images take a very long time to make. But in an ideal world, again, I would have had time to do another image of PFOTS and just see, is it the fluorine that gives it different features, or is it just, am I not getting proper assembly? So RMS roughness, through AFM, we're also able to measure the roughness. And if you can compare here, every treatment has a higher roughness than the control, which is good, the SI or the gold. There we go. Okay, so one more thing with the RMS is the silicon and the glass have almost identical roughness, but the thiols have a much higher roughness than the silanes, and that's again just showing that not only the features, but the roughness is coming from the gold layer, because glass and silicon seem to be almost identical in many different aspects. All right, now we can get into the final conclusion. What we wanted to start with was find a thiol and a silane that have the most similar surface energies to promote single crystal growth of these perovskite crystals. So we found 2 pairs. Octadecane thiol and trichlorooctyl silane seem to have the most similar. These are both 18 carbon chains, so not so surprising that the 2 18 carbon chain lengths had the most similar surface energies. We also had 2 of the fluorinated ones, a fluorinated silane and a fluorinated thiol that again had the most had pretty similar. And so for the future, we're gonna, so first, as mentioned, I don't know if you know anything about North Carolina, but it's very humid. I have no idea if by the time I measured these contact angles or took the images, I have no idea if they degraded or not. I don't know what the shelf life is. So do further characterization, maybe be able to take images of the surface and see is it degrading or not. Because self-assembled monolayers, they can wilt. It's not always going to be perfectly standing straight. But also, assuming that my self-assembly was perfect and the recipes worked out fine and they're ideal, then we would get started with the patterning of the layers and to see if this actually works. If these pairs are actually what it takes to increase that success rate of crystal growth. And acknowledgements. Thank you.
So we have a minute for questions for Jordana. Do we have questions? Yes.
What was your favorite part of this research project?
What was my favorite part of the research project? I mean, finally making these graphs was pretty exciting because I was able to get through like one column a day or like a week. So it took me all summer. I finally being able to see all of this together, all the RMS, all of these, because this isn't automated yet. You have to physically cut out the 15 centimeter by 15 centimeter substrates, then make the solution, and then let it sit for sometimes up to 2 days to assemble. So that was time consuming. Also, getting trained in AFM was pretty cool as well.
Thank you. Next up we have Rudy.
Oh, it works pretty well. Did I really? So good afternoon, everybody. My name is Rodolfo Cantu. I'm a mechanical engineering student at the University of Texas at Austin. My PI this year was Dr. Amal El Ghazali, and my mentor was Ludovico Cestarolo. My project was on the design and fabrication of magnetic elastomer-based soft actuators. So the motivation for a project like this really stems from the fact that there's been a lack of haptic interface technologies. We've explored audio and visual for the past century, and we've kind of neglected some really cool interfaces, such as a magnetically actuated touchscreen phone, something that would deflect upward and you would be able to sense with your fingertips. So think of your phone that's capable of coming up and presenting a physical touchscreen device, or presenting a physical keyboard or braille for accessibility. So developing these thin films for the haptic interfaces is the motivation for this, but something like this, although it's not far from fiction, does require us to kind of prove the concept a little bit more. So the focus was more so on actuating a cantilever beam to kind of show that doing something for a thin film would not be so hard. So the device design is really two components. It's the magnetoheliological elastomer, which is just a fancy word for an elastomer with magnetic nanoparticles embedded within it. It's an MRE for short, and integrated magnetic controls. These are micromagnetic controls made of various magnetic metals. And we have a concept here which shows you just how this deflection is done. We have two different magnets magnetized in different directions. You have one that is out of plane or perpendicular magnetic anisotropy. This is a circle. And you have one that is in plane, pointing in plane, and this is an ellipse. So these two kind of dig into the elastomer and deflect it downward. We had three main objectives this summer, and it was the fabrication and characterization of magnetic controls, the fabrication of the thin magnetic elastomer, and the integration of these two. The first one, which is the fabrication and characterization of these controls, we developed a simple photolithography process which was fabricated on a silicon wafer. We spin-coated two different resists and soft-baked, exposed with a contact aligner, developed, descummed, and then sputtered in the various layers using a sputtering tool, and soft-baked and lifted off. So the two geometries, we created multiple 10-millimeter dies that we would sample using VSM, which is vibrating sample measurements. These gave us magnetic measurements called hysteresis loops, which we'll get into later. and atomic force microscopy, which is AFM profilometry. So these are the different dyes that we created. Each one was 10 millimeters. We did this to optimize the different shapes that we'd be using in the final design. So you can see that we did 3 micron all the way up to 100 microns for the circles, and we did 3 to 15 to 15 to 50 for the ellipse. So the characterization of the circles, if it works, gave us these hysteresis loops for the various sizes. And for the hysteresis loops, what we're trying to focus on is the x-intercept and the y-intercept. The x-intercept tells you the coercivity, which is essentially what the strength required is to flip the direction of the magnetization. And the remnants is the y-intercept, and it tells you the strength left over after it's been magnetized. So you could see that at 5 micron sized circle, we had the most optimal, highest coercivity and highest remnants. We want it to be the highest because we want to have a strong magnet that doesn't flip easy. We want them to keep their magnetized direction and their strength. For the ellipse, we did something different. We checked the magnetization in plane for both the short and long direction, and we wanted them to be very different loops of the different sizes. So this is because we wanted to stay magnetized in the long and not turn to be magnetized in the short. So if they have different hysteresis loops, it just tells you that it's not going to flip over. So we found that 3/15 long ellipse was the perfect size as we move forward for experimentation. We also verified these samples using an AFM and found that there is a liftoff process, not so much error, but something that just comes after. These are residual metals caused from the process, and they kind of look like Batman ears. But we were able to cut them off using argon ion milling. And these are the parameters for that. And you could see after milling, we were able to get a lot nicer shape from the geometries. After finding the optimal sizes of these two geometries, we needed to find the spacing, or at least the spacings that we would test for the final design. And we used COMSOL multiphysics simulation to look at the spacing between the ellipse and the circle at various sizes. So we tried 0.5 all the way to 4. And this simulation just tells you the magnetic flux of the two circles, and the contour plots tell you the strength of that flux. So you can see that at 1 to 2 micron, you have a lot nicer coupling, and you have no pockets, there's no divots, there's nothing. So we thought experimentally we want to test 1 to 2. The next step of the project was the fabrication of the thin magnetic elastomer, which was tricky, but we found a process involving 2 different elastomers of different weight percentages, vortexing for a few minutes, mixing in 6% volumetric iron nanoparticles into the matrix, vortexing for another 3 minutes, sonicating for an hour, and spin coating onto the resist at around 7,500 RPM for 120 seconds. And this gave us a thin magnetic elastomer of about 2 microns, which is very difficult considering the nanoparticles make everything really messy and clumpy. So the final part of the project was the integration of these two things, which was the actuation controls and the elastomer. We knew the sizes of the magnetic controls, and we knew we could make the elastomer. All we needed to do was figure out a way to fabricate the cantilever into it and deposit these microcontrols. And we did this by developing a very long process, but it's patterning the IMA magnet and then patterning the PMA magnet at a varied spacing, patterning a platinum frame to make a well, which we would then deposit the MRE into, depositing titanium and photoresist, exposing the area for the well, and argon milling through the MRE, and then finally xenon fluoride etch under it to make the cantilever or beam freestanding. So we finished the 3 masks and actually completed the steps for most of this fabrication process, but we were not able to get to the 4th one. We did do the calculations for the beam, though, and we found that for the cantilever, because we didn't want the displacement to be more than the well, because then it would hit the bottom of the well. So we found for the cantilever, 40 to 60 micron length was essential, and for the simply supported beam that we'd be testing, 40 to 100 was good sizes. We designed a mask as well to experimentally test these cantilevers and beams. And you can see here that we have the short well and then the cantilever and the circle and ellipse at varied spacings. And those are veneer marks and fiducials for the contact alignment. The next step was to magnetize these magnets, or at least make a plan for it, because something this small is very difficult to magnetize, even though it takes very little field. And so for the PMA, we had a coercivity of 1,000, and for the IMA, we had a coercivity of 250. And so what we wanted to do was magnetize the one with the higher coercivity, because it means that it won't flip once you magnetize it in the other direction. So you magnetize PMA first, and then you magnetize the IMA, and you're left with the final design magnetized. And we'd have to do magnetic force microscopy to verify the magnetic moments of these. The conclusions are that we found optimal spacings, optimal sizes for the two different microcontrols, and we're able to characterize them. We simulated the spacings between the IMA and the PMA magnets, and developed a process to finally integrate them into a cantilever and test deflection. So the next steps would be to integrate these two things and then finally test the deflections of the cantilevers. And these are my acknowledgements. Question?
Do we have questions for Rudy?
No questions. We got one.
Given the materials and the schematics that you had to draw up in order to perform the study, how do you think that using this technology, how accessible it would be?
Okay. So the question would be that, let's say we were able to develop this into, like, let's say the final product, which is like a thin film, how accessible would it be? So the reason that this project was kind of developed is because these magnets are very easy to make. They're very cheap, low cost, and they require almost no power. So I'd assume that if you were able to develop a thin film, like haptic device, it'd probably sell very cheap and be very accessible.
So I have to say I've been listening to your reports all summer, and this is the first time I've thought about the fact that what you're talking about is a thin film that will go onto a cell phone. Is that what you're?
Mm-hmm.
And then when you activate it, it would sort of pop up.
Yeah, so you'd be able to program it. Yeah, different magnets, and they'd all, because they're microscale. So it's mainly for Braille, but yeah.
So it would be something a thin, like you know.
Something that you could incorporate, yeah, into like a touchscreen phone, or yeah.
What happens when you're a theater major? It takes a while for things to go all the way to the top. Do we have other questions for Rudy? Okay, thank you very much. Next up we have Alexander. Yes?
Yes.
Sorry.
All right, so can you help me with the setup?
So just forward on through to your next slide.
How do I apply this? Should I apply it here?
Actually, no, that's a little bit too high. The best thing is to take your name tag off.
Oh no, how are they gonna know who I am?
Know who you are.
I know they won't.
Just leave it there and then
Who am I tie?
right to your top.
Oh, like that interview in the beginning of The Incredibles. Yeah. All right.
There you go. And then don't wander too much, but the camera's looking at you right here.
The camera, as far as I can tell, has a view roughly to here.
All right.
So I might reference a little bit.
You wander all you want. There you go.
I checked. I did check the camera. I'm trying to keep an eye. I'm trying to keep that in mind. All right, everyone. I'm Alexander Harden. I spent my summer at NAU, Northern Arizona University, working on constructing exciton Hamiltonians of polymer chlorosome nanocomposites. It's a mouthful, but it'll make sense later on. My mentors, that were grad student mentors, were Jaime Diaz and Asara Sosa. I worked mainly with Jaime. Inez Montano was in charge of the research project, as well as Dr. Gabriel Montano, but I worked mainly with Inez. I also worked a lot with Isaiah Raspet, who is currently here in the audience and will be following me up to further explain some of the stuff I have at the end of my slides. So to start out with, I'd like to start by explaining what photosynthesis is and what a natural chlorosome is. So in nature, photosynthesis is extremely efficient. It's many times more efficient at what we call light harvesting than what current solar voltaic technology is, like 2 or 3 times more efficient. So current technology, 20–30% efficient at the most. This sort of technology would be close to 90, 95, 99% efficient. in terms of collecting that light energy and transferring it to somewhere where we can actually use it. So in nature, we have these things called organelles called chlorosomes in certain bacteria. These chlorosomes basically contain what are called chlorophyll molecules, which you may have heard of in high school chemistry at some point. And what those chlorophyll molecules do is they absorb photons of light. And then those chlorosomes just capture all those photons and then transfer them down. Essentially, they capture them in these what we call aggregates, which I'll explain in future slides. Transfer them down through these proteins and through more chlorophyll molecules that are contained within here to the reaction center, where it gets converted into chemical energy. We could use this to make new forms of solar energy. We could also use it to drive new kinds of chemical reactions if we wanted to. So the main focus of my research is actually on the synthetic version. So B is the synthetic version, A is the real world version. This is just another representation. Dr. Gabriel Montano and his group at some point made these things, and essentially they just have the chlorophyll molecules contained within in what we assume to be the same structures as are found in nature, and they have a polymer on the outside just to contain the whole thing in the right shape. So let's see, I'll move on. So what happens to the light? What's the first step in the process? Well, the first step in the process is a chlorophyll molecule will absorb the photon, and it will be converted essentially into energy, and that energy is contained within the orbital of the electron. So it'll go from the highest occupied orbital, where the electron currently is, to the lowest unoccupied molecular orbital. So that's the next step up in energy it can take. Energy is quantized on this level, so it has to match exactly that jump from HOMO to LUMO. And then from there, it's transferred from one molecule to the next through that chain. So an important thing to mention here is Foister theory. So in Foister theory, there's an analogy between a molecule emitting a photon and another absorbing it. So one way of modeling that interaction is using what we call the transition dipole moment. And it's a dipole, it's an electronic dipole associated with that transition from ground state to excited state, from that HOMO to that LUMO. The TDM can be used to calculate interaction with a photon, but in this case, we're using it to calculate the interaction between the molecules. So basically, it's like the electromagnetic energy required to change the state of the molecule. So we can use that to get that interaction value. And so it depends on how well their spectra overlap. So the better their absorption spectra overlap, the better those gaps in energy overlap, the better they'll interact. So for closely spaced molecules, though, the dipole is just approximation of something we call the transition density. And the transition density captures the full structure of the molecule as a charge density. So these are charges. Each of these little dots is essentially a charge that we're modeling within these molecules. And so we just have to use the electronic interaction, the Coulombic interaction between those charges to get the interaction values. So the interaction between these molecules depends on the angle and the distance between them. Here I've done the angles. So I have two molecules. This one in the front, I'm going to call it the front because that's easier. That one is rotated around all three axes separately, and we get this three-dimensional plot here that shows what those interactions look like, how strong those interactions are. On the top, you can see this sinusoidal wave, and that's from it just rotating around one axis. And so it doesn't really depend. So if this molecule is aligned vertically, that's the dipole direction. So twisting it that way doesn't matter that much, but twisting it around this way will, because that'll change the direction of the dipole more. So the x and y don't matter that much. The z and y don't matter that much, but the x changes it substantially in a sinusoidal pattern. Moving on to distance dependence, we have the two arranged what we call tip to tail based on the dipoles. And we take them and we just move them further away. This is a 1 over r to the 6th dependence, I believe. 1 over r to the 6th, 1 over r to the 3rd. It is two terms in there. And so that's what gives us that fall off there. So it's really important that we get our structures right when we do these calculations. So what can we do with that? Well, we can use that then to build what's called a Hamiltonian. This Hamiltonian allows us to model that energy in the system, model the whole system as energy. So along the diagonals, we have what we call the vertical excitation energies. Also, it's the same as the magnitude of the transition dipole moment. basically just how big is that gap between the HOMO and the LUMO. And then on the off diagonals, we have the interaction terms. That's what I was calculating in those previous slides. So we can expand this up into however big we want to make it. And we can use this to do all sorts of fun calculations using quantum mechanics. So we can get how the energy moves through the system over time. We can modify it to fit more natural conditions, that sort of thing. And I'll show you some of that in the next slides. So, yeah. But first, I'll talk about what are these chlorophyll molecules that we have. So we have 4 separate chlorophyll molecules. I've highlighted the differences between them. These are the molecules that are present in Dr. Montano's systems. So there's C, D, E, and F. And what I did was I basically made these molecules in 3 dimensions. I did some calculations to try to see how well my values match up with experimental data. So they sent off solutions of these molecules to get tested. And these are if you're familiar with the absorption, molecular absorption like UV-vis spectroscopy, this is the frequency of light, wavelength of light that they absorb naturally, and these are the calculated values that I obtained. You can see that for experimental purposes, for calculational purposes, these align pretty well. Quantum chemistry, computational chemistry is not always the greatest, but these, if you look, the patterns kind of line up, especially these peaks, the dashed peaks and the highlighted peaks here with the labels. So I calculated that, and then I arranged them into the structures that I showed you before. So you saw that there were the tube structures, that green tube. This is a more abstract view of that. I believe I used the one on that side there, the C, and just built that using computer code. Just took those molecules essentially that I calculated and just duplicated them along that tube to make that shape. And you'll see what that looks like in a moment. So coming back to that Hamiltonian, so we can build that shape, and then we can calculate its properties, how that energy moves through the system over time. So let's go back to just those 2 molecules for a moment. So we have one pair of molecules at 15 angstroms apart and another at 20. And what this graph shows is the probability of the energy being on the first molecule versus being on the second. So what we do is we assume the first molecule has absorbed a photon, it's got the energy, and the other one has not. And then over time, we can see they basically just switch places in terms of probability. So at this point, there's a 100% probability it's moved to the second one, so we know it's on the second one and not on the first one anymore. And we can see that just moving it by 5 angstroms changes things a lot. So specifically, I used the Lindbladian master equation solver through QTIP, but I'm not going to go into great detail on that because I don't know that much about it. So I built a 256-membered system. This is the same type of plot before, but it's that tube with 256 molecules. And so that's what it looks like. It's just a bunch of squiggles. We can't really tell much of what's going on. So I made a 3-dimensional model of that. This is supposed to be animated, but the conversion process kind of broke it. I can show you the animation later if you want. But on the right, we have the animation of the probabilities over time. So it's what you would see is you would see it spiraling upward through the tube, essentially, and spreading out. And the lights are just how probable the energy is to be there, how likely it is to be located on that molecule. So it's not necessarily the results that are most important, but what we can use this method for. So I basically constructed this whole method of building these systems from the beginning, from the structures of the chlorophyll molecules and some spectral data. And we can model the movement of energies in large pigment systems. We can generate many configurations of pigment systems very quickly. And we can model many different systems, different structures for the systems very quickly as well, compared to many of the previous methods. And we can also modify this by later putting in a sync model. So we can model how we can remove the energy and actually use it, for example, like what that interaction would look like. We can include models of disorder, basically like small variations in the system quantum mechanically. And we can model the environmental interactions with the system. So I didn't include those. Isaiah will actually talk about that, open quantum systems. And I think that's where I leave it.
Do we have questions? questions for Alexandra. We have time for 2. We've got 2, so go ahead.
Yeah, so on one of the slides you showed like the different absorption graphs. What was the difference between the dashed lines and the solid lines?
Yeah, I had to glance through that. I wanted to isolate them, but for time I couldn't, and also put arrows on them. But this is what the spectra looks like when they're all in the tube together. This is them freestanding. So the calculations on the computer are done with individual molecules freestanding. There was actually a presentation earlier, I think today or yesterday, where the presenter actually mentioned specifically diluting it substantially so that you can kind of get an idea of what the molecules look like when they're on their own. And that's what this is. That's what I'm comparing to. That's the dashed line.
So can you kind of model like exciton transfer, let's say like with transrectal chromophores, compounds, say like triple membranes of bacteria, or I guess like what are the potential applications?
Could you repeat that again? I'm sorry.
Yeah,
That was quite a lot. I'm so sorry.
Sorry. So like you mentioned that this is for chlorophyll molecules, correct?
Right.
Would this be applied to other molecules like transrectal chromophores?
Right. So these methods are generally applicable to chromophores. The transition density method has been used for carotenoids, other compounds. In theory, yes, you could. And also the CCSD methods that were used to get these energies, the transition energies, and do all these calculations should also apply in those scenarios. I'd have to know the specifics, and I'm not a complete expert on this, just undergraduate research.
Okay, thank you.
Thank you. I was going to hand it off.
How do I get to my presentation?
Yeah, I think so.
I don't know how. I don't know how.
Just forward.
Okay, okay.
Just keep going forward. Yeah.
I put you all the way back. You have to go through my spare slides. Perfume department.
Okay.
There you go.
Hi.
Okay, Isaiah, go for it.
Hi, I'm Isaiah. Coming from the NCI Southwest REU at ASU. I'm a computer science student, rising senior, studying at NAU. And my project is simulating open quantum dynamics through quantum algorithms. So I'm going to break down my title for my presentation, and I'm going to start with what an open quantum system is. So a quantum system is any system that's small enough to be governed by quantum mechanics rather than like more traditional physics. So that's they're affected by things like entanglement, superposition, and quantum coherence and decoherence. And it involves like actual like random chance compared to like what we're used to with larger things working on a larger scale. So an open system, which were the graphs that Alex showed us, those are not affected by the environment. They the closed systems are useful for modeling certain things, for understanding how these systems would interact if they were isolated in an imaginary world with nothing, and that can be useful. But we can also simulate the environment by opening up the system and allowing for environmental noise to affect the system, and that does change the graphs that you'll see very, very significantly. And so a dynamic system is a system that changes over time. So if you can see that equation over there, that H sub s, that's the Hamiltonian that Alex gives. And that equation, it describes the state of a quantum system over time. And what my project was to take that system and break it down into what you see there, which is a quantum circuit. That larger blue box is a quantum circuit that can be run on a quantum computer. And what's interesting about this is with a quantum computer, you can create an actual analog of a quantum system rather than using the master equation, which does some math that I don't understand to create those sinusoidal graphs. What this will do is, if you run this circuit, it will, at a certain time step, it'll give you an exact location of energy in the system, as if that system were to actually have run in the real world. I have these pictures of different systems changing over time so like you more understand what a quantum system is like. So at the bottom I have a man walking. This is a very simple system to describe. If you know his speed, you know his direction, and you know an amount of time that has passed, you'll know where he'll be, right? With the apple, there's a lot more factors involved, right? You have no idea what the state of the apple is going to be in 10 years if you don't know the state of however far out you need to propagate to get the state of that apple. So I'll be talking about quantum algorithms now, specifically quantum computing. So in traditional computing, the point is to manipulate data in hopes of getting some specific outcome. You do that with bits of information, which are those zeros and ones, that binary that you see. And those are run through what are called logic gates, and you'll get some exact output. And what's important about, a very important concept in traditional computing is replicability, right? If you run an algorithm once, you want to get the same outcome over and over and over again. That's not true in quantum computing. In quantum computing, if you run an algorithm once and then you run it again, it's not necessarily going to give you the same result. And you don't want to do the same types of calculations on a quantum computer. So in the traditional computing, I have that. It's called a 2-bit full adder. It takes 2 bits and adds them together. On that quantum circuit there, that is a circuit that will entangle 2 qubits. I don't know if you know what entanglement is. It's where you take 2 particles, and if you measure the state of one, you will know the state of the other. And what this does is it puts 2 qubits in that entangled state. If you measure one, you will know the state of the other. How quantum computers do this is with a qubit. A qubit can be at any state between a 0 and a 1. It's represented by that sphere called a Bloch sphere, as opposed to a classical bit, which is either 0 or a 1, which is why I had this power symbol here. That's actually what it is. It's a 0 and a 1. It can be either one of those. It can never be in between. But with a quantum, with a qubit, which is short for quantum bit, it can be at a state in between those, which allows you to carry a lot more information in a single bit. What's also a product of it being a quantum system is once you measure it, you lose a bunch of, don't lose a bunch of information about the system, but it will collapse on one state. So if that qubit is in what's called the plus state, where you can see that 0 plus 1 over root 2, it will, at the moment you measure it, either be a 0 or a 1. It won't be at any state in between. So there are a lot of different applications for quantum computers versus traditional computers. A quantum computer can do some things much faster than a traditional computer can, and this is a picture of a supercomputer, which they take up warehouses, right? And then a quantum computer looks like a cool gold chandelier thing. And it requires very specific conditions to work, and even with these very specific conditions, currently quantum computers aren't able to stay coherent systems for a super long amount of time. It's like you need to finish your calculation in a few milliseconds, otherwise the information will get corrupted. So we're still working on that sort of thing. But what's important is that we are able to use them at this point. So some examples of problems that traditional computers would be better at are any arithmetic. A quantum computer is terrible at doing math. It will give you a random output, and you don't want that if you're doing math, right? It's really good at factoring large numbers. Some aspects of AI are better on quantum computers, while some aspects are better on traditional computers. And this is speculative, simulating quantum systems. They might have some insight into how open systems might work. So now I'm going to bring everything together with the simulations. So here's that equation from earlier. Basically, the process that I go through is I get a Hamiltonian from Alex. I do some manipulation of that Hamiltonian to get what's called a unitary matrix. This unitary matrix is similar to a Hamiltonian that it represents the state of a quantum system, but this time that quantum system is in the form of quantum circuitry, quantum algorithms, rather than the representation of the actual physical system. And then that unitary matrix can't be actually directly run on a quantum computer. What you have to do is break that down through what's called rotation decomposition, where you have these gates here. If you can see the RZ, It'll rotate that qubit that you see along the z-axis and change the state of the qubit that way. Yeah. So where I ran into a lot of problems here were the library that I was using to do the rotation decomposition is written in a language that I'm not very familiar with, called Haskell. It's not my favorite language in the world, and it also was a closed source, meaning that I couldn't access the source code and verify what it was doing. And it was doing some things that I found kind of seedy, like normalizing the information that I put into it. And how am I going to get a time-dependent graph from normalized data, right? So that was one of the main hiccups that I ran into. But it still did output the correct shapes of graphs. It was still giving me some information that it was along the right lines, but that's where I ran into the most problems. So yeah, that's what I did in my presentation. Here are my acknowledgements. Any questions?
Do we have questions for Isaiah?
Sorry if this isn't super relevant, but I was curious, why would quantum computing be better than traditional computing?
Oh, okay. Have you heard of Shor's algorithm? No. Okay. So actually what's really crazy right now is in a lot of pathfinding problems, it's actually really useful to input randomness even in traditional computing so that you can be sure that you are like finding that fastest path. So what a quantum computer can do is probabilistically like run through every possible path from one point to another point, and then what Shor's algorithm does is it destructively interferes any path that isn't the correct path, and then will output just the path that you want. So it's like beefed up parallel programming where you can just run everything at the same time. Alex, you had something?
Yeah, could you go back to the Hamiltonian and maybe point out the diagonal and off-diagonal terms again, just because I don't think it was clear on that.
Did I do that?
Yeah, you did. You had it. Sorry, you can't.
On yours?
No, on yours.
I don't know where
Not giving your presentation.
Where is this?
You probably could, though. Yeah, there, right there, the HS, right there.
Oh, okay.
Yeah,
So what was the question? Or the request?
Just so that anyone can see it again, just more clearly.
Oh, right, yeah. There is you have the...
His J's are my V's, and the V's are the same. He just has those squiggly ones instead.
Oh, I see.
Yeah.
Got it.
Any other questions? Curious about quantum computing?
Yes. Question for clarification. So is a qubit essentially like a superposition value between a 0 and a 1?
It doesn't have to be, but most of the time, yes. Yeah. Yeah, that's why it's got that sphere representation. There's some like weird things with the qubit. Like you don't have to. It's got the 0 and 1 there. You don't have to measure on that axis. Like if you were to switch to that 0 plus 1 over root 2, you can measure there and be sure that it's in that superposition. So yeah, there's a lot of like weird things you can do. Like if you were to take a qubit that's in along like the z-axis straight up and down, and then measure it in the plus axis, you would get either a plus or a minus. Yeah.
Okay, thank you. And last but definitely not least, we have Jeanette. She now has to go through Alex's and Isaiah's.
Yeah. All right. Is that laser pointer? No, it's not. Okay. That's a laser pointer. Okay. All right. So I'm Ganesh Pedersen. I did my work this summer at Montana State University, mainly under Jordan Baker and Dr. Wataru Nakagawa, on the optimization of wire grid polarizer characterization. So the first thing I want to talk about is what a wire grid polarizer is and why we want to characterize them. So just some background on polarization for anyone who may not be familiar. The polarization state of an electromagnetic wave is basically the way the electric field oscillates over time. So here we've got an electric field going in the vertical direction, so we have vertically polarized light. And light, being an electromagnetic wave, has polarization. So there's many different types. We have linear polarization, we have circular and elliptical as well, but the most relevant one for this presentation is just linear polarization, which you can, again, direction of the electric field. So what polarizers do is sort of take in light and filter it to simply one polarization state. So here we have randomly polarized light. The electric fields are going in a bunch of different directions. And the polarizer only allows light with a horizontally oscillating electric field to pass through. Now, wire grid polarizers do that exact same thing. We have light coming in, and light of a single polarization state is let through. The difference is that wire grid polarizers actually reflect the orthogonal state of light because they're made of aluminum wires. And that's useful for things such as transmissive scanners, which our lab's working to build. But before we do that, we need to understand how these polarizers work and how well they actually function as polarizers. And we also want to know that for different incidence angles of light. So we want to know how it behaves when the light comes straight in, or at an angle, or at an even more oblique angle. So to do that, we have this characterization setup, which basically consists of a tunable laser source around 1550 nanometers. So this is infrared. We put our wire grid polarizer in there, and we have detectors that measure the transmitted and reflected power from the polarizer, which again are in orthogonal polarization states. Then we have some cleanup optics to ensure that we can actually know what input polarization state is going towards the polarizer. So we have an initial cleanup polarizer just to clean up the light from the laser. We have a half wave plate, so we can change the polarization of our light if we want to. So we can, say, see how vertically polarized light interacts with the polarizer as well as horizontally polarized light. We have a pickoff beam splitter, which allows us to monitor the laser power over time. And basically, if there's any fluctuations in what the laser is putting out, we'll know about it, and we'll be able to normalize it out. And we've got a final cleanup polarizer just to be extra certain that we know what's going towards the polarizer. And again, you'll notice that our polarizer can rotate around the vertical axis here. And that means that we can measure it for multiple different incidence angles. So what we end up getting is a graph like this, where we have our, in this case, transmission efficiency as a function of our incidence angle. Now, you might think that we just get this by measuring one single power measurement at every single incidence angle. And it would be nice if it was like that, but unfortunately, it's way more complicated. Each one of these data points is actually an average of 41 different data points swept over many wavelengths. And the reason we need to do that is because the polarizer substrate actually leads to some interference effects that are dependent both on wavelength, as we see here, but also on incidence angle, since if we change the angle, we change the path length through the substrate. So what we end up getting are these power oscillations that are roughly sinusoidal, although you can't see it with this sparsely sampled data. But we get that as a function of wavelength and incidence angle, meaning that we can't really trust incidence angle measurements directly. We need to take averages. And this works great. Like, we get really good graphs from this, but the problem is it takes a long time. Each one of these full wavelength sweeps takes around 3 or 4 minutes. If we're taking 21 of those, that means we need to spend an hour just to get that graph. So my project this summer was working on how we optimize this. How do we make this faster? Like, can we collect less data here? Now, the first thing I looked at is, again, we have 0.2 sample spacing here. First thing I looked at is removing that pickoff meter that I mentioned, which monitors the laser power. And the reason behind that is because we also get interference effects from the pickoff detector, which are actually around double the period of those from the measurements through the polarizer. And that means that we actually have to sample a wider wavelength range, and we also just have to consider 2 oscillations instead of 1. So if we're able to remove this, we'll be able to have more flexibility, and we'll be able to sort of play around more with what we actually sample and our spacing between samples. And I'm not going to talk about our process doing that here, just because for the sake of time. But we did a bunch of tests, did some measurements, normalizing to the pickoff measurements and not normalizing to them. And we basically found that our laser is perfectly stable. Not perfectly, but pretty darn stable. Like, the differences aren't more than 1% in most cases, or all cases. So we ended up removing the pickoff meter. And that allows us, again, to just play more with what we actually sample. So now we need to decide how many samples we want to take and at what rate. So again, the whole point of this is to get an average that roughly matches the known average. So in this case, we have like a highly sampled sweep. And we want to just take a subset of that and say, OK, how close is our average? So if we take 10 samples, we can space them in a bunch of different ways. We can put them there, or we can put them there, or we can space them twice as far apart. So we've got just a ton of different options here for just even if we want to say we only want to take n samples. So to restrict this, we ended up just looking at some theory, taking less than two samples per period, and only sampling an integer number of periods. But essentially, we narrowed this down to a certain number of combinations. The issue here is that even when we have a certain number of combinations of sampling rates and sample spacings that work, or number of samples and sample spacings that work, we still have a bunch of different starting points on the sweep that we can use. So we could start there, or we could start there, or we could start there. So what we ended up doing is basically combing over this entire sweep with, in this case, 10 samples spaced uniformly, and seeing what the difference in the average of those 10 samples was compared to the full average. And that ended up giving us an idea of like, OK, what's the average error if we take this number of samples at this spacing? And if we combine all that data, do that for a bunch of different data sets, we get this graph, which basically tells us, OK, if we take X number of samples, on average, how much error can we expect? And what's the maximum and minimum error we can expect? So this is the average, and then the error bars show max and min. You'll notice we have two lines for a high signal state and a low signal state. Those basically denote, like, if we have the majority of the light being transmitted through the polarizer, that would be our high signal state since we have a ton of signal. And you'll notice the error is just less due to there being less noise, or no, the noise not being as apparent due to the higher signal. So you can see that even for a very small number of samples, our average error is actually not that bad. And you can see it decreases sort of monotonically as we take more samples, as we expect. You'll also notice that our previous process, which I had showed initially, is better than all of these new ones. Of course, we have a trade-off between how much we sample and our accuracy. But even still, we have pretty comparable results, which is very promising. And it basically means that we're taking more data than we actually need. So what I ended up doing is basically creating this table of a bunch of different sampling protocols that our lab could use, depending on how accurate results we want. So say we want to have a really quick and dirty idea of how our polarizer works. We can just take 4 samples, and we're not going to be super accurate, but we'll still be pretty close. And we'll have shaved off 90% of our time. Like, so we take that graph down from an hour to just 6 minutes. If we want a better idea, but still not as accurate as usual, we can maybe take 15 or 26 samples. So basically, we have a bunch of different options now that allow us to get pretty good results without needing to spend nearly as much time on actually collecting data. So just to summarize, our previous protocol is quite lengthy, but we were able to remove the pickoff detector and remove one oscillation that we didn't really want to deal with. That allows us to change the number of samples we take and the spacing between samples. And we found results comparable to our previous protocol. And again, we had that trade-off between accuracy and time, as usual. I do want to note that that graph I showed last is actually a bit inaccurate. We didn't take into account that the oscillation period actually depends on our incidence angle. And because of that, the optimal rate that we sample at is actually going to be different at different angles. So if we look into that more, we'll actually probably be able to get our error down even more. But even still, our results are pretty comparable. And I just want to thank the NSF, the RU program, everyone at my lab group at Montana. And thank you very much. I'm open to questions.
Do we have questions for Ganesh?
I think everyone's tired. Yep.
So this was funded by the Air Force, probably? What was their interest?
I was never actually told. I don't think I'm supposed to know that. So.
Yeah, it's controlled information, I'm pretty sure. Yep.
You did a pretty good job with your presentation. I think I don't have a question. I just want to say it was very straightforward the way you presented it.
Thank you. Thank you very much.
Good job.
But yeah.
Yeah, thank you very much.
Anything else?